All right. Good morning. Welcome. It's my pleasure to be the first to welcome you to the fourth edition of the Quantum Science Center Summer School. My name is David Stewart. I'm the managing director of Purdue's Quantum Science and Engineering Institute. Our institute sits in Discovery Park District, which is one of many centers and institutes here at Purdue. It lies under our Office of Research, which is led by our Executive Vice President for Research, Dr. Karen Plout, a role in which she has served since January of 2023. Dr. Plout oversees a $2.8 billion research enterprise at Purdue. She is responsible for university-wide strategic initiatives and bringing together researchers and resources to drive interdisciplinary discoveries with societal impact, very in line with what the Quantum Science Center does as well. She joined Purdue in 2010 as Associate Dean for Research in the College of Agriculture and later became Dean of the college. She earned her bachelor's degree from the University of Vermont, master's from Penn State, and PhD in animal science from Cornell, followed by postdoctoral research at the National Cancer Institute. She then joined the faculty at the University of Vermont before coming to Purdue. She's published approximately 100 papers and has received funding from NIH, NSF, NASA, and the USDA. So with that, it is my pleasure to welcome Dr. Karen Plout to provide some opening remarks this morning.
Thank you very much, David. I appreciate it. There we are. I apologize that I'm on Zoom, but I have a cold and thought rather than give it all to you that I would greet you by Zoom. So I just want, on behalf of myself and President Meng Chang, welcome you to the Purdue Quantum Science Institute. I think you got a really exciting program. You've brought speakers from around the world to speak about quantum science. I apologize. I think with all of you working together, there's no doubt that the future of quantum science will expand rapidly. I would like to thank the Department of Energy and Oak Ridge National Labs for their support of the Quantum Summer Science Center, the center, as well as the school and their leadership in the area of quantum science. I want to thank Purdue experts, as well as all the people from other universities and industry for presenting at this conference and really helping train the next generation of students. Quantum technology is critical for so many areas, whether it's finance, national security, computing, healthcare, and many more areas. And with your wonderful lineup of speakers, you'll have the chance to explore many areas of quantum science. What's so neat about these kind of meetings is you bring together expertise from so many different areas around the country and world. It's exciting to have other universities here together. It's not only industry, it's not only academia, though. You also have industry partners as well as national labs such as LANL there. And you're all working together to enhance R&D across quantum science. And this is how you really make gains in the field. It's by bringing together a technology and a science ecosystem that builds on the individual strength that really opens new collaborations and facilitates the ability to maintain open dialogue and exchange with researchers from partnerships in the network. Last, I think one of the most exciting parts about this is your ability to develop new talent in quantum science. And this is an area we need to continue to grow and expand. I think I'm talking to the choir when I talk about how much we know the field of quantum will grow, and we need the workforce and able to do that. So both training undergraduates and graduate students is really important. I wanted to bring up that Purdue recently made a $100 million commitment to an effort called Purdue Computes. As part of that investment, there's a significant upgrade in Burke Nanotechnology Center. And as part of that expansion, there's no doubt that our capabilities in quantum computing and quantum science will expand. The commitment to Purdue Computes also includes investment in new faculty lines, of which some of them will be for quantum science and quantum computing. I think the opportunities in quantum continue to grow. It's exciting to seeing everyone get together to talk about the latest science and grow those opportunities. And I challenge each one of you, especially the students in the audience, to take the time to expand your knowledge, to explore ideas for the future, ask questions, learn new things, explore areas you're less familiar with, and of course, talk to new people and meet new people. It's the interaction with others that often leads to bold new ideas and new interactions. And really, for the students there, you're the next generation of quantum scientists and quantum engineers. You're going to make transformational breakthroughs. That time is here for quantum, and you will be leading some of those technology of the future. So I just want to say thank you so much for coming in person or online, and have a great meeting. It's an exciting day for quantum science. Thank you very much.
Thank you, Dr. Plout. At this time, I will introduce someone who in this room needs no introduction, Professor Sasha Baltaseva, who is a distinguished professor of electrical and computer engineering, leads the Elmore Center, Frontier Center for Quantum and AI, and is, of course, the Quantum Science Center's workforce development lead. So please welcome Professor Baltaseva.
Thank you so much, David. David is the boss here, and everything is hinging on David, so thank you very much. So let me say a few words and welcome, first of all of you to our 4th edition of our summer school. And so what I want to say is that school is always about learning. And learning for us means not only learning from the experts and PIs and professors that you're going to meet, but also learning to come up with new ideas. And we will try to foster and facilitate that by exposing you to lectures that actually merge different disciplines. So not only quantum science and engineering and technology, but we are going to have lectures that merge quantum with optics, with chemistry, with sensors, with machine learning, and we'll ask all of you to come up with new ideas. So this is, again, the event which is really the centerpiece of our academic year. And we are very proud that for the Quantum Science Center that is co-led by Oak Ridge National Lab and Purdue, the privilege of hosting the school is here on campus. And that's, again, give us an opportunity to bring a diverse set of people. So from students and graduate, undergraduate, postdocs, and professors on all different, from all different departments. We are also bringing researchers from national labs. Of course, this is our lead, the Oak Ridge National Lab, and you will see what's going on in the labs and how it's different or similar to what your career choices might be. We are bringing people from industry. You know, quantum is a very, very interesting area of science and technology, because the research and development in this particular area is happening simultaneously at the same time at the universities, national labs, and industry. So we are working hand in hand, and it's up to you to decide which one of the 3 you're going to join. We will have engaging, motivating, great panels to discuss quantum science and technology, emerging areas, but also career choices. So prepare some very, very good questions for our panelists. And we will ask all the presenters to be part of the panels. So when you hear the talks, in addition to questions, think about panels and what's coming next. So we just want to proceed, right? The last thing I want to mention is that school is not only about learning. School is also, and very much so, about networking and building your connections. Build your connections for life. It's very important because as a young researcher, what you usually want to do at conferences or schools like that is to connect to big people. You know, we have founders of companies, we have big professors, and you want to chat and you want to say who you are and what you're doing, and that's fantastic. That's what the school is for. But keep in mind that you also have to build connection with your peers and build your network. For a very simple reason, because your peers, your classmates will grow with you. You know, maybe you will end up in academia, maybe your friend will end up in a big company, you know, in 10, 15, 20 years. If you want to establish a collaboration, or send your postdoc for a great job, you'll just you call up, you pick up the phone, and you connect to someone that you connected to in a summer school 20 or 10 years ago. So keep this in mind and build your network and build your connections. And we have a summer school, and summer means fun. So I hope that you will also have fun with all the extra events and panels and discussions and evenings and dinners that we are having. So with that, I would like to present the next speaker. And the next speaker is our Deputy Director of the Quantum Science Center, Dr. Vivian Zapp, and she will introduce both our leadership, the QSC, and the research that is going on in Quantum Science Center. With that, Vivian, the floor is yours, or rather the screen is yours.
Okay, thank you very much. As usual, I start with, can everyone hear me, see me? Okay, I can no longer hear anyone else, but that's okay.
Yeah, we're still here.
Okay. Okay, so firstly, apologies, I couldn't make it in person. I was here last year and I enjoyed it very much, and I wish I could join you, but here I am. So I'm Vivian Zapp. I've recently become the Deputy Director of the Quantum Science Center, and I'm located at Los Alamos National Lab in the High Magnetic Field Lab. So in my talk, I'm going to introduce the Quantum Science Center, and then because we have many excellent speakers who know far more than I do about a number of topics, I'm going to plunge into a particular topic, and I'm going to talk about topological magnetic systems, which is maybe, I don't know, 1/6 of the QSE. And then right after me, you'll hear from Yang Chen, who also works on some of the other topological systems, and from Mike Manfra and so forth. Let's see. If I could give one piece of advice, if I could go back in time and redo my entire career, I would ask every question, or maybe most of the questions that I wanted to ask at every stage of my career, especially when I was very young, because this is your big chance. So that being said, if somebody asks a question, I have no idea what the format is, so maybe Ed will notify me. So, okay, so all right, when it comes to quantum computing approaches, there's a lot of them. It's sometimes hard to keep track of what they all are, and they're variously leapfrogging each other in progress. So, but I mean, very broadly, we could say that there are some that now exist in commercial companies. They're not yet, the full-scale quantum computers we want, but they are being pursued commercially. These include superconducting approaches, such as most especially transmons, cold atoms, trapped ions, and then photonic approaches and quantum dots are also getting there. But then there's the approaches that are still in the science discovery phase. And these have the hope to overcome the roadblocks that the others are facing in a different way. So these are farther behind, but they may be the turtles that win the race. We don't know yet. These include topological approaches, molecular spins, defects in semiconductors. But you could say the latter two are reaching maturity when it comes to quantum sensing. So whereas people are still trying to figure out how you can make a quantum computer out of them, they are effective quantum sensors at this point. So where is quantum computing now? Well, we don't have the fully functional quantum computers we want yet, which is why we're investing all this time and effort. But we are reaching some low-hanging fruit. So particularly when it comes to simulation, quantum computing systems have become effective simulators for some magnetic spin systems and other sort of simpler physical systems. Particularly in Ising spins, they're starting to even outperform, some other theoretical approaches. But there's the not yet ripe fruit of simulating more complex systems, correlated electrons, complex chemical systems that you will hear about later. Also, high energy physics, the makeup of a nucleon and so forth. So we need additional scaling to perform such realistic simulations. And then, of course, the ultimate goal is general purpose gate-based quantum computing. So there's many bottlenecks, which is the fascinating science we're addressing here. Of course, the big one is decoherence, loss of quantum information, and closely related gate fidelity. In other words, the chance that a given manipulation actually does what you want it to do to your quantum information. These need to increase by a few orders of magnitude. And we need to scale everything to larger sizes. Where we're making great progress is in developing algorithms. These algorithms also are inherently addressing all of the above when it comes to error mitigation, error correction, and so forth. Okay. We have seen dramatic growth already. So this plot is already dated. It's from 2021, probably. But this shows that we saw exponential progress in the coherence times, in other words, the time that quantum information survives in the system, in the last 20 years, over 5 orders of magnitude. This is specifically this is mostly superconducting approaches and a few photonic / superconducting approaches. But we still have a ways to go. And so the plot on the right is intended to indicate that we need to scale up from the little picture you see at the bottom to the one at the top. So we need, many more qubits for universal quantum computing. So there's many different approaches to quantum computation, sensing, and communication. This is an eyeball slide. So there are, in broad swaths, there's atomic approaches, there's superconducting approaches, it's approaches based on magnetic spins, topology, photons, and any such plot will not be complete. And then this at the top are the corporations, at the bottom are a small fraction of the research institutes engaged in this effort. So the Quantum Science Center is mostly focusing on the ones that I've put in gray. And where we're most unique is probably in the topology, but we also have very strong efforts in cold ions, some efforts in trapped ions. Everybody's working on superconducting approaches. We have some excellent approaches to semiconducting defects and photonic approaches to quantum computing. So, of all of these approaches, which one's going to win? People keep asking. So I don't really understand that question because I don't see that we need a winner necessarily. We're used to thinking of classical quantum computing as having a winner. So one technology, the silicon-based approach, leapt so far ahead of all others that none others could compete. And then because it was so far ahead, it was then modified to do all kinds of different things. But if you look at most other things in life, if you go into the hardware store and you buy a single all-purpose tool, you will curse it for the rest of your life. So really in most things, you need many different tools. And if I had to bet, I think that's where quantum computing is going, because each approach has its pros and cons. Some are better for quantum computing, some are better for some kinds of algorithms, some are better for communication, and some are better for sensing. So I suspect they're all going to find their niche in the final technology. Then again, I hope somebody's going to let me know if there's a question because I can't hear the room, but okay. So the Quantum Science Center, I'm going to briefly overview it, is one of 5 DOE-sponsored National Quantum Initiative centers. The National Quantum Initiative also encompasses other things besides the DOE, like the NSF and other agencies. But within the DOE, the main focus is these 5 centers. And our center, the Quantum Science Center, is focused on sort of the large science challenges as compared to the other centers. So as with all large projects, we are divided into 3 thrusts. Thrust number 1 is focused on new materials, particularly those with topological properties, in the hopes that topology can overcome this problem of noise and decoherence that plagues many other approaches. Thrust 2 focuses on algorithms and software. This includes topological approaches, but it also includes more broadly expanding our portfolio of algorithms towards future quantum technologies, so that ultimately we can not only do general gate-based quantum computing, but also apply these to predict new physical and chemical behaviors. And then thrust 3 is nominally on sensing, but a big part of this is to tackle the big science problem of dark matter. So by exploiting the unique sensitivity of quantum sensors, the hope is to make a dent in this problem of covering the whole spectrum of dark matter detection, and more generally to develop novel sensors to explore the previously unmeasurable. So, right now we're approaching the end of our first 5-year time period, and the National Quantum Initiative is being considered in Congress for 5 more years. I can't legally tell anybody what to tell their representatives or how to vote, but certainly right now this is what Congress is considering in their budget. So this will determine whether the centers and also more broadly the National Quantum Initiative will get 5 more years. So. Okay. So the Quantum Science Center is very broad and very complex. So we've attempted to describe, what happens in the different thrusts. So in the thrust 1, it's focused on the topological materials. We have loops going between theory and experiment, prediction and measurement, and these then tie into quantum algorithms. So apologize for all the many words. So coming over to the second one, we have quantum algorithms that are being developed for quantum applications, and we're attempting to deal with error mitigation, optimization, and the constraints of the various physical devices that we're implementing. And then over on the right, we then apply this to quantum sensing and apply it to some of the big science problems like dark matter. So, okay. And then, briefly, this is our leadership. So we have many people attempting to create coherence across this large center. Of course, Travis Humble, who couldn't make it today, is our director, located at Oak Ridge National Lab. Notably, Sasha Boltaseva, I think we should put her up here in the top, is doing tremendous efforts in her own science project directions, as well as in workforce development, to put together schools such as this one. So. Okay. This is, you can probably tell that this is something we put together for our funders. This is an eyeball slide of the different institutions that are involved in the Quantum Science Center. So we have 4 national labs. Of course, it's led out of Oak Ridge. We have 3 industrial partners. We have many more industrial partners, but we have 3 with which we have, more agreements and direct collaborations, and 10 universities now, with the most recent addition of UC San Diego. Our 3 technology partners are Microsoft. So Microsoft has a focus on topological superconducting quantum computing. Also, we're working with them on algorithms. So for example, QSC helped create the Q-sharp language. Cold Quanta, now known as Inflection, is working on cold atoms. And again, we have various collaborations with them, both to develop their technology and to explore how we can use it for science discovery and to circle back to the next generation of quantum computing. And then with IBM, we're collaborating with them on various algorithms, error mitigation, but also to simulate spin systems and nuclear systems using their technology. Okay, so that was my sort of broad overview. Then I was going to plunge into the subject of topological quantum computing, specifically in magnets. So here's a quote from Das Sarma. This is also already dated. This is from 2022. I think we've gotten significantly farther along than what he's summarizing here, but his point is that topological quantum computing is a different approach to quantum error correction that sort of intrinsically improves the stability of quantum information. However, the problem with topological quantum computing is that we don't have any topological quantum computing as yet. So this is a science challenge that we are tackling. So there are sort of three major approaches to topological quantum computing. I think you're going to hear about all of them today or in the school, but I will focus on the third one, which is spin liquids, specifically KITIF quantum spin liquids. So let's talk about what that means. And so let me go back for a moment. So of our three different topological approaches to quantum computing that we're considering in the QSE, the quantum Hall effect, the superconductors, and the spin liquids, the third one is primarily a magnetic approach. So what my next slide tries to do is summarize the different magnetic approaches to quantum computation. So spin liquids live at the intersection of the topological approaches and the magnetic approaches. So when it comes to magnetic approaches, there's those based on individual spins, such as magnetic defects, spins in molecules, spins in quantum dots. But what I'm going to talk about is a collective approach. So we care not about one spin, but the power of what spins can do when they form, large-scale collective states. So I will talk about topological excitations in quantum spin liquids. Okay, so when you have collective patterns of spins in magnetic materials, so these are magnets consisting of atoms, each of which contains a magnetic spin. Often the interactions between the nearest neighbors will compete. And this creates complexity in your final pattern of spin systems. So you can get, this is an example of skyrmions. You can get all manner of very complex patterns as the system attempts to solve the problem of competing information. But when it comes to topological approaches to quantum computing, it's the excitations that are the key. So it's not the ground state, but the excited patterns that emerge and that are more mobile and can be manipulated compared to the ground state. Okay. So magnetic frustration, so the classic picture people show when they talk about magnetic frustration is the triangle. I think this problem was considered about 1 year after antiferromagnetism, maybe just a few seconds, but it was published 1 year after antiferromagnetism was discovered. Okay, so if you have spins that want to lie opposite to each other, well, what happens if you put them on a triangle? And this lies at the heart of many different magnetically frustrated systems. The frustrated lattice that we're going to talk about is the honeycomb lattice. But the first thing you might notice when you look at the honeycomb lattice is it's not actually frustrated when you just put simple antiferromagnetic spins on it. So to get the honeycomb lattice frustrated, you need something called a KITIF interaction. So Alexei KITIF is still around, still active. So this was proposed only as recently as 2006. And I'm going to go in depth on the KITIF interaction, but here's the Hamiltonian of it up on top. And I mean, basically you have three different you have three different bonds in this lattice, blue, green, and red, pointing along three different directions. And each spin is interacting along each of these bonds. But you see the superscript, alpha, beta, gamma. What the superscripts mean is the direction of the spin, so the quantization axis of the spin. So the spin is interacting along a different spin axis for each bond. So the spin might interact along the blue bond with its x, along the green bond with its z, and along the red bond with its y direction. This is what gives this model its complexity, because those three directions, of course, do not commute. The result is, I don't want to say a big quantum mess, but it certainly feels that way. This model does not order in any classical sense. So let's go in more detail. So let's so the Kitaev interaction it's kind of like an Ising interaction. So here up top is the Ising interaction that just connects two spins along one axis. So this is the z component of one and the z component of the other. But of course, spins have x, y, and z. So the Heisenberg interaction connects the spins along all three axes. The Kitaev interaction is somewhere between these two. So it's employing all three axes of the spin, but only one at a time. So along one bond direction, as I mentioned, it uses one, along the other bond direction, it uses the other, and along the third bond, the third. So the net result of this is a spin liquid. So the ground state of the system is actually singly degenerate. There's a single solution to this problem. But the problem is that the single solution does not commute with anything that we know how to measure. And so that's why we call it a quantum spin liquid. So there is a solution, but any attempt that you make to measure it is going to give you quantum fluctuations because you're coming in with some non-commuting operator. Okay. All right. So I'm not going to go in huge depth on all the different kinds of quantum excitations because this is only a 40-minute talk, half of which is over. I'm going to give a brief overview and then give citations. So what happens when you, I'm going to go also in a little bit more depth on this, but here's the broad overview slide. So you have your spins. They can be treated as bosonic in this model. And then they effectively fractionalize, which is another way of saying you can think of there being a particle in the system. The particle is not a spin, but some pattern of spins or some pattern of some component of the spins. And these patterns can be treated as fermions, or you can further divide them up into non-abelian anyons, which I will tell you what those are in just a moment. So the key is the excitations out of the ground state, which we call quasi-particles, which you can think of as having these different kinds of statistics. And then the key of these non-abelian anyons is you can braid them. So let me tell you in a few more slides what that means. Okay. So in 3 dimensions, we only have 2 kinds of particles. We have bosons and we have fermions. So a boson means that if you exchange 2 bosons, so I replaced x1, x2 with x2, x1, you get back the same state. But of course, with fermions, when you exchange 2 particles, you pick up a phase, so you get back the negative of the state. These are the allowed particles in 3 dimensions. But if you go to 2 dimensions, you can have an arbitrary phase. So if you exchange your 2 particles, you pick up a phase, and moreover, the sign of the phase depends on in what direction you exchange them. So if you make them move around each other in a clockwise direction, you pick up one phase. You move them in the anti-clockwise direction, you pick up the opposite phase. So this is the general case. This does not exist, as far as we know, in real life because we live in 3 plus delta, perhaps, dimensions. But in a magnet, you can create a quasi 2D systems, and then you can have quasi particles that take on these anyon statistics. But anyons can be further divided into abelian and non-abelian. So abelian anyons are the ones I just described that just acquire a phase, and these commute with each other. It's the non-abelian anyons where things get really exciting because they do not commute. So in fact, if you braid two non-abelian anyons around each other, you do not simply get a phase, but you actually have to, apply a matrix to the state to get an entirely different state. So you have to do a unitary transformation in the Hilbert space. And each braiding of these non-abelian anyons is non-commutative. So, classically, it's like an actual braid. So it matters in which direction you braid, and it matters the order in which you do the braiding. And the history of how you did your braiding then gives you a whole different state of the system. Okay. So, why do we care about braiding? So coming back to quantum computing, after you've done a bunch of braids, you end up with a state of the system that is different than you had before, but the state is very robust because it involves the entire state. It's a many-body system, and it's very difficult to perturb it. So if you allow for this very vague classical analogy, if Daenerys Targaryen stored information in the pattern of her hair braids instead of in the location of individual hairs, this is far more tolerant to, let's say, wind noise, because undoing the braid requires undoing the whole collective state of her hair and not just moving a single hair. So this is the concept of topological stability, and this is what we hope to exploit for topological quantum computation. So if you were to construct a topological quantum computer, it would begin with an initialization which creates pairs of non-abelian anyons, then applies a circuit that variously braids them, and then a final readout that needs to look at the collective state of the system. So at this point, I have not derived the details of what these non-abelian anyons are in the magnet. At this point, I give you citations, because whereas it's actually not that complicated, you could do it in a 40-minute talk. You just would not be able to do anything else. So these are some of the overview papers on topological quantum computation in general. And then this paper is the Kitaev quantum spin liquid specifically. There's about maybe 10 pages that covers most of it. So this is where you would find the details. All right. So as far as where is, let's see, I'm not sure exactly how much time I have left, but so where is this field? So when it comes to Kitaev quantum spin liquids, we don't have any yet. Well, we might have some. We're trying to figure out for sure whether we actually have a Kitaev quantum spin liquid. So we definitely have magnets with spins on a honeycomb lattice. There's many crystal structures that form honeycomb lattices. We're pretty sure that we have these Kitaev interactions. So if you look at any two spins, you know that this interaction exists, and it may even dominate in some systems. But what we don't have is definite Kitaev quantum spin liquids. The challenge is that in addition to these Kitaev interactions, there's all the other interactions. So in a given magnet, you have not only this, but you have the Heisenberg, the off-diagonal interactions, anisotropies with the lattice, the ones that I call the pesky interactions. And the problem with all these other pesky interactions is that they make the system order. So it's no longer a spin liquid. But if these interactions are small enough, the prediction is that you apply a magnetic field and you will still get a modified version of a Kitaev spin liquid, and it should still have the topological excitations. In fact, something that we didn't actually talk about is that a little bit of magnetic field is actually necessary in any case, because you need your particles, you want them to be gapped. not gapless. So in any case, you need a magnetic field, and the magnetic field might suppress any long-range orders in the system to get you to the spin liquid. So the leading candidate in this field is a compound called ruthenium chloride. Ruthenium chloride it only has 2 elements. It's been known for a long time, and it forms in a lot of different phases. So the one we care about is called alpha ruthenium chloride. That's the one that has a honeycomb lattice. This is one of the papers that attempts to describe the system's phase diagram. So on the vertical axis is temperature, horizontal, I overwrote it to say this is magnetic field. And it has various different phases. So at 0 magnetic field, it forms this zigzag antiferromagnetic order. But in applied magnetic fields, this ordering, the temperature is suppressed. And then this big red thing may or may not be the Kitaev quantum spin liquid phase, depending on who you believe. And then eventually the spins saturate and you get into a just non-topological phase. So at this point, this compound has been extensively studied. Some people believe that this, where it says half integer quantized plateau, that's referring to the thermal conductivity. It may or may not have a quantized plateau in the thermal conductivity, which would be one signature. Over on the right is the inelastic neutron spectra. So this is sending in neutrons and watching them be absorbed by the various magnetic excitations as a function of the wave vector of the neutrons as well as their energy. And this is also a bottleneck in this field. It's hideously complicated to calculate what you even expect from the neutron spectra when you have all these other pesky interactions. But from here, you can attempt to extract that you think it's probably a Kitaev quantum spin liquid or not. So the thought is it probably is with some other interactions. This is another compound. This one is maybe less likely to be a spin liquid. This is sodium cobalt telluride. This is another example of a compound that has a bunch of different ordered phases. So these different colored regions are different ordering phases, but the one at the highest magnetic field on the right may be a quantum spin liquid. And then also just beyond it and before the spin saturate is another place where people are looking for potential quantum spin liquid behavior. Now, of course, in all of these, you have a magnetic field, and the magnetic field is, okay, so I'm from the high field lab, so these are small fields of 8 to 10, maybe 12 Tesla, but still it's a significant technological issue that now you need to study this thing in the magnetic field. Okay. So, if you look more broadly at this field, there's a lot of different candidates. The blue arrows indicate how far along we are, and the ruthenium chloride one is probably farthest. The others are variously stalled or entirely failed. But luckily, there are many different candidates we can cycle through until we find the one that's in the right regime. So right now we're focusing on this ruthenium chloride here in the middle. Okay, so what are we doing? So if you want to prove that something is a spin liquid, so it doesn't have classic long-range ordering, so that's one thing you can test. You can check the inelastic neutron spectrum, but it's difficult to calculate. You can look for the quasi-particles because they conduct heat. So you can measure their thermal conductivities, but there's also other things that conduct heat, like phonons. And so we're looking for a smoking gun for evidence of these non-abelian anyons. And so right now, that's the bottleneck. That's where we are right now, where the research is focused, is on this hunt for the smoking gun. And so I would say the leading things that we're trying here in the Quantum Science Center are, this is 2 of them. I think that the most promising one I haven't shown because I'm not sure how much the researchers want it all to be shown, but These are approaches to creating quasi-particles and then causing them to interfere and looking at their signatures. So up on the top, this is a material that has 2 holes drilled in it, basically. And then you expect your non-abelian anyons or some form of quasi-particle to be circling around the edge. And then the idea is that you turn the spin liquid on and off in different regions. So on the left and the right, you have some adjacent ferromagnet that applies your magnetic field, where you flip the spins so it's on or off, so the spins are canceling or not canceling each other. And thereby you can cause the quasi-particles to create and to be moved between the various sides. And then you can detect whether they're interfering or not interfering with each other. So this is in progress. And then down on the bottom is another attempt to look at how these quasi-particles are moving along the edges of the system. So on the bottom, this is a material that's been shaped into 2 wings. And then at the center, where this gray dot is, on the micron scale, you further pattern it to be one of these 3 different shapes. And the idea is that quasi-particles moving along the edge will interfere with each other 0, 1, or 2 times. And this in turn then affects their thermal conductivity. So you can measure the heat transport across the system and then distinguish these 3 different cases. And most importantly, you're filtering out phonons, which are too large to pass through the center, because it's smaller than the phonon's mean free path. So this is in rapid overview form, the state of where this field is. So we're eagerly hoping for the outcome of these and other similar measurements to determine the existence or non-existence of these topological quasi-particles, how they interact and interfere with each other. And then this would be the nucleus of creating a qubit based on one of these technologies that can manipulate the quasi-particles. Okay, so that's most of what I had to say. This is, again, a summary of the magnetic approaches to quantum information, of which the one on the right is where we are. We're looking at collective patterns. And again, this is a summary of the topological approaches to quantum computation, especially the ones in the QSE. I talked about the 3rd one, spin liquids. You'll hear about the first 2 also later today. And this is where I will end and take questions, with the apology that I did not give you an in-depth derivation of the Kitaev spin liquid, but I did give you the citation. So.
All right, let's give a round of applause to Vivian. Thank you for joining us virtually. We're gonna open the floor up to questions, but if you have a question, make sure I can get the mic to you first. So anyone has any immediate questions, we got about 5 minutes. If not, I will start first. I guess Vivian, first question is, assuming you are able to realize these non-abelian anyon state, do you expect, what would classify, are there ideas out there as to what would be a unit for the qubit? Would it be like each triangle set of like 3 set of spins? Is it going to be like the whole honeycomb lattice? And also, how do you go about probing the spin states in the magnets?
So yeah, these are why Thrust 1 of the Quantum Science Center exists. So if one of these approaches, that would be then the nucleus of creating a quantum computer. And in these systems, you only need 1 honeycomb plaquette in theory to have a quasi-particle. But in practice, the approaches are looking at quasi-particles that are moving along the edges. And so what we would be doing is probably creating a system where you're moving quasi-particles along edges, and then you're using your edges to interact the quasi-particles. And so, 1 qubit would not be just 1 honeycomb plaquette of the lattice. 1 qubit would be a particle that's free to move around an edge. And then, in theory, you could have as many particles as you have honeycomb plaquettes. But in practice, that's a good question. We haven't thought about what's the density of quasi-particles you can fit in there. But I think the most important thing is that you just want a few quasi-particles that you can manipulate their interaction. So something like this would be a qubit, where the gate operation involves, for example, turning on and off these ferromagnetic pieces. The final architecture does not yet exist, but these are the beginnings of how people are thinking. So.
All right. Any other questions from the audience immediately? You just, oh, cool. Oh, I got one.
Hello. So my name is Tahar Webeh. I'm associate professor from University of Constantine in Algeria. And with my student, Abdullah Tunsi, who is participating with me here, who have been working on the theoretical part of topological quantum computation. We are working mainly on the design of braiding gates for topological quantum computation. And I believe the Hadamard braiding gate that you have shown in one of your slides is from one of our papers, I think. And I'm happy for that. So our next step, so we have been working on braiding gates for a while, and we have also created a full, let's say, software for the simulation of braiding gates, which is TQSIM, which is open source and available on GitHub. But we are thinking about our next step being the simulation of those topological quantum states. And my question is, are you thinking about collaboration with one of your partners like ColdQuanta or IBM for the design of some quantum simulation schemes on their devices like superconducting qubits and cold atoms? And if yes, what are the challenges? Because what we are thinking about is that it's going to be extremely challenging to simulate this kind of honeycomb lattice on IBM computers, for example, or even using cold atoms, although they are extremely well controllable. Thank you very much.
Yes, well, thank you for that summary, as well as your work in this field. So certainly we would like to simulate this, but I think you also summarized the challenges. So, I mean, the KIT-IF interaction is not native to any of the quantum computing approaches that exist now commercially. So let's see if I can get all the way back to the beginning. So the KIT-IF interaction on a microscopic level is the power of this approach to quantum computing, and it does not exist in the cold atoms, transmons, or trapped ions. So an attempt to simulate it then becomes very complicated. So at this point, I'm not aware that any of these commercial prototypes are at the stage where that's feasible. But there are several papers that have attempted to simulate other forms of topological braiding, not based on the KIT-IF model. So I think each of these cold atoms and transmons each has, Google has a paper on simulating topology on their system. And then in the cold atoms, there's also several papers. And possibly we'll hear something from Michael Lukin. I don't know if he's going to cover this topic. So some form of topological simulation exists, but I'm not sure that the KIT-IF system is feasible in the short term. But the reason why it's not feasible in the short term is it's so fundamentally different, and that's why we care about it. If we can implement a KIT-IF interaction, in these systems microscopically, then you have a form of error correction that is so powerful and so fundamentally different, which is why we can't simulate it on the other systems. Does that make sense?
All right. Any other questions? Oh, Zach. Oh, you got it.
I have a mic. Is it on? Okay. Yeah. Thank you. Thank you for your talk, Vivian. Kind of in the sort of I guess, long-term directions for the research. Is there any kind of theory work done on how these spin liquids might be localized excitations, and then what kind of, say, like rubidium trichloride circuitry might look like, just in terms of physical implementation? How might that come to fruition?
So I think most of the theoretical work is focusing on these edge modes. So the idea is you want them to be mobile, so that they can interact rather than being localized. But there is some work being done on defects. So with the defect, you could localize or control not an edge mode, but a quasi-particle within the bulk of your system. So with defects is where you could think about what you just said, thinking about microscopically localizing them. But that research is very nascent. I mean, people are just starting to think about it. So.
All right. Thank you, Vivian, and thanks for all the questions. We're gonna thank Vivian again before, and then we're gonna transition into our next speaker. Thank you, Vivian. So we're now gonna thank you, Vivian, for joining in. For the next part, we're gonna shift toward our in-person part of the programs with our next couple of talks. So our next talk is gonna be presented by Professor Yang Chen. We're gonna get that all set up. In the meantime, I'll read out his bio for you. So Professor Yang Chen here is the Karl Lark Horvitz Professor of Physical and Astronomy, and also a Professor of Electrical and Computer Engineering. His lab exploits quantum physics to manipulate electrons, atoms, spins, and photons in various materials and artificial systems, with the aim to uncover novel quantum phenomena and new states of matter, and to explore applications in quantum devices such as quantum information and quantum computation devices, nanotechnology such as nanoelectronics and nanosensors, and energy. Professor Chen is also the director of PQSA and on the governance board of the QSC.
Vivian talked about a variety of quantum materials studied in Quantum Science Center, maybe particularly focused on some of the magnetic spin leaf candidates. So I'm an experimentalist. Okay, my group, we are passionate about making and measuring different interesting quantum matters, particularly quantum materials, some of which are studied in the Quantum Science Center. And in my talk, I'm trying to give you a more some examples and maybe tutorials on some of the experiment techniques we and the community use to study some of these quantum materials. And particularly, I'm going to focus on the set of techniques that take advantage of the spin degree freedom. You've heard the word spin in the Vivian's talk, and it's actually going to be quite important for many of the quantum materials study. And particular examples, I'm going to talk about topological insulators, which is a platform for lots of other interesting topological states of matter, including topological superconductors, and a little bit these quantum magnets that actually Vivian mentioned in her talk. And a lot of these experimental techniques actually give you an example of a potentially could be used for functional devices. And I will actually, a lot of the focus of this Quantum Science Center is to transition interesting quantum materials to possible useful devices, and hopefully give some example, at least inspiration along that direction. So I'm drawing examples from my group, but also a lot of colleagues. We benefit from collaboration with a lot of the other experimentalists, theoretical colleagues, material growers, so on and so forth. Okay, so if I can get this moving. Okay, so this is my kind of a broad view of why quantum materials are interesting. Okay, it does maybe not summarize all the possible interesting quantum materials, but it's a very large class quantum materials. They're interesting because of the interesting spin properties. They all have spin inside. Okay, well. First major type paradigm of materials. Actually, I mean, we don't usually think of boring magnets as quantum, but actually to really understand how magnets arise, you actually need to understand quantum mechanics. Otherwise, you cannot explain even a simple why it actually occurs at room temperature. There's all aligned ferromagnet, for example, or other magnet order system, antiferromagnet. But these, I call this, has a spin, excuse me, position order. Meaning, if I know the spin direction in one position in this material, and I go to another position, I can predict what that direction of spin would be. That's called spin position order. So this is the first example of the magnetic material. You heard quite a bit from Vivian's talk, and this is one of the major, one of the material focus here in Quantum Science Center is these spin liquid, or let's say candidate spin liquid materials. They are sort of relate to a magnet. I mean, of course, sometimes people call this quantum magnet. These materials, under some conditions, like ruthenium chloride, and many other examples we mentioned, could be magnet ordered, they're antiferromagnetic, but we hope they're actually not ordered, all down to lowest temperature, 0 temperature. Not only so, they are fluctuating and the spin fluctuating, but they have some very unusual property we call spin position entanglement, long-range correlation. Okay, so in fact, according to theorists, at least, if this is a truly quantum spin liquid, the ground state will be this massive superposition of lots of different configuration. Seemingly, they are not correlated, but so you're fluctuating. If you say, hey, at this node, my spin is up, but I can see quite far distant away, the other person, they will be spin down. And next moment, instant, you're spin down, the other person will be spin up. It's almost like, it's actually a form of entanglement. It has this very interesting many-body entanglement. So this is actually captured the quantum spin liquid. By the way, it remains to be shown convincingly that a real solid-state material actually possesses amazing property. But there's Canadian material, ruthenium chloride being one example, people are checking out, show to be promising to realize this state. So this has spin position entanglement. Another example of the very interesting quantum material, a lot of us study, including in this center at Purdue, are broadly speaking topological materials. Topological insulator is one example, and I will spend quite a bit of time talk about topological insulator. But one of the primary property of topological insulator is on the surface. So it's actually not even insulated. The bulk is insulated, but the surface is very conducting. In fact, on the surface, this conducting electrons has very unusual properties. This is the Fermi surface look like. If you fix the momentum, that electron at that momentum will be only have one allowed spin states, typically kind of tangential along the momentum like this. So we call this has a spin momentum order, kind of a dual to this spin position order in magnet. But here, if I tell you where I'm in the momentum space, my spin direction is fixed. In the case of topological insulator, if I go to opposite momentum, I have opposite spin. There's broad range of other materials, not topological, even boring, but actually not so boring, metal like platinum, as spin orbit coupled metal or spin Hall material. They kind of partially possess some of these properties. If you flow, due to spin orbit interaction, if you flow current in a heavy metal like platinum, on the surface actually also have spin accumulation, which even not fully polarized as much as topological insulator, but you still get spin polarized electrons at the surface in a lot of other materials like heavy metal, we call spin orbit coupled materials. Nonetheless, so this have this kind of spin momentum order. If you know where you are in the momentum space or which momentum you promote, then you can predict kind of spin properties, which direction spin would be for electrons. And last paradigm, very important quantum material that is used for is superconductor. So I'm drawing a very simplified BCS S-wave superconductor, which I'm writing this BCF Cooper pair wave function in this form, which you see this is spin momentum entangled wave function. If Cooper pair has 2 electrons, spin up, spin down pair, but each electron, you don't know which spin there, but if you know at plus momentum K, if a down spin, the minus momentum will have up spin. And it's most importantly, you have to also have the other part of wave function. So this is a spin singlet, actually spin momentum entangled wave function for the Cooper pair. So these, again, these are not all the interesting quantum material, but I bet this captures a very broad range, a large substantial space of the interesting quantum material. They are interesting to a very large extent because something interesting about the spin degree of freedom. By the way, even you have a material which has no interesting spin degree to start with, maybe insulator, like diamond, boron nitride, which for condensed matter physics, it's basically a vacuum, right? You can make it interesting by creating defects in this insulator. It actually would be actually spin qubit. Okay, I'm probably not going to have time to talk too much, but if I end, this is actually also interesting member, in my opinion, to bring to this mix because it can be interesting tool to study these other quantum materials. So most of what I'm going to talk about is that if you can start with this material, start to combine them to actually using one interesting spin degree freedom to measure or manipulate another interesting spin degree freedom. Broadly, I call this spintronic quantum material or spintronic technique meets quantum material. Okay, so that's kind of the theme. Example I'm going to give, for example, how to use a magnet to measure a topological insulator, prove this kind of a spin helical property. You can also do things reverse influence the other way around, and how the combination of a topological insulator and superconductor give you interesting degree of freedom, how you might measure that, and how you may use a spin helical electron like this, or spin of the material to sense the spins in a candidate spin liquid. So this kind of stuff I want to talk. I guess this is outline I just mentioned. So probably I spend most time talking about spin sensitive transport device measurements in topological insulators to prove, not only prove you do have these kind of a very unusual spin helical electronic structure, but you potentially start to do useful things. You can flow current, generate electron spin polarization, maybe even nuclear spin polarization, which is actually very long-lived. Amazingly, actually, we think probably protect by topology. I'll explain what it means. And you don't necessarily have to use a magnet. Actually, use a superconductor built-in Josephson junctions. You can also build interesting devices with unusual properties due to these spin helical electrons I just mentioned. And I give you one or two examples, probably just one. Time limited, I'll focus on using these, again, spin orbital material, partially spin helical electrons, let's say, to sense the spins in the spin liquid material. And you may hear later in the conference, I think my postdoc, Andreas, is giving me a short talk on some of the optical mode study of 2D magnets. Give you another example. These are spin sensitive, either electronic or optical techniques to study some example of these quantum materials. There's a lot of additional interesting examples, probably won't get to, start using these NV center or spin defects. I think it's also a powerful platform to study these quantum materials. So so let me start with topological insulators. I think many of you have heard this multiple times, but let me just focus on one aspect. I already mentioned, it's actually an insulator. The name is also bisnormal. It's actually a conductor due to the surface. But let me say, the bulk is insulator, but it has a very strong spin orbital coupling. Typically, these materials are made of heavy elements on this side of the periodic table. The elements are heavy, orbital coupling strong. And in atomic physics, when you have spin orbital coupling, it can push those energy levels around, right? It can also push bands around. It can even invert band inside this material. You got this so-called inverted band gap. What would be a conduction band actually became a valence band. But outside this insulator is not inverted. Vacuum is a half mega EV trivial insulator. It could be another trivial insulator like silicon oxide, whatever. So when the two inverted band evolve to a non-inverted band in this very simple structure, you got a crossing which is guaranteed. Okay, and that crossing gives you these gapless modes. Actually, the massively Dirac fermion, kind of like graphene, but with a real spin degree frame running on the surface. So the key property of topological insulator is the two following. It has, when I say topology, so again, the name is always a bit tricky. It's actually a conductor, right? Protect the conductor on the surface inside the insulator. It would be an insulator if it weren't for this topology. So it has two interesting topology. It has a real space topology, which is what I just mentioned. In a sense, the conducting electrons only occur on the surface or the boundary of the 3D bulk. It has an interesting momentum space topology of these electrons on the surface. The Fermi surface looks like this, has this helical tangential kind of a winding number, and the spin kind of runs around the momentum like this. We call the spin helical electrons. For each momentum at the Fermi surface, you only have one spin state allowed. So you're actually missing the other half spin state. Usually electrons, right, 2D electron gas has two spins at each momentum. But here, you have only one. The other spin actually occurs at the opposite surface. Okay, so spatially, it separates this to allow spin states. So this is actually, all these are tied together. So these are very interesting materials. Bismuth selenide may be one of the most well-known, but it's typically in this family, involve elements, bismuth, selenium, tellurium, antimony. So these are class of material. They're the example topology, but these are the topology that we work with in the lab, also partially because they are layered the material, kind of like graphite, so you can easily exfoliate them into finite number of layers, building thin film-like devices. Okay. Of course, I should mention first, I mean, they're beautiful. This is actually a picture from QSIPI Zahid. The beautiful RPAS full image like this, showing indeed the band structure had this conduction band, valence band with these surface state Dirac cone with the spin helical electrons. So the electron structure, band structure is pretty well established. But to show these properties, to bring to functional devices, took a lot more effort. So you have to improved material, for example, in a material like this, bismuth cyanide, for example, typically, so in the photo emission, you see everything below the Fermi level. So you see this material, Fermi levels are very high, which allow you to show beautiful RPS band structure like this. But if you want to build the transport devices whose property is dominated by this topological surface state, Dirac cone, this is not good at all, because the conduction will be totally dominated by this highly occupied conduction band. So you need some other material, which I'll introduce, which actually lower the Fermi level to inside this band gap to allow you to build these topological insulator-based devices. Okay. Now, I will just focus on, I said, one set of measurements which are somewhat sensitive to spin, okay, for now. So you may call this spin sensitive or spin. Let me try to hide this bar. Just give me a second. Okay. So the idea has been around for quite a while in spintronics community, and this particular context, this is proposed by my colleague Supriyo Datta here in UEC, whose group pioneered a lot of interesting ideas on spintronics. You may heard Datta, Das transistor, so on and so forth. But this kind of measurement technique is called spin potentiometer measurement. So basically, today, how do I prove? Okay, let me back up. Let me back up a little bit. So I said the key property of topological insulator, for example, is that if you fix momentum, the spin is well defined. Okay, here's another cartoon. Or you have a Fermi surface like this. So so to show this, you need a spin-sensitive transfer measurement or spin-sensitive, let's say, electrode. And the simplest spin-sensitive electrode is basically a metallic ferromagnet. Okay, the ferromagnet has polarized spins. You can use that to build your devices, and you have to perform the spin-sensitive transfer measurement. So the proposed scheme is the following. You basically flow a current, okay? And when you flow current, you promote certain momentum, okay? So this in this language, let's say you flow current in one direction, promote certain momentum. You would make those electrons with that momentum more occupied. In this language, it has higher potential. And in topological insulator, right, that occupied momentum also indicates occupied spin. So this particular occupied spin state has higher chemical potential. How to measure the spin-dependent chemical potential? You use a ferromagnet as the electrode. So it's a spin-sensitive voltmeter. If the you can control the spin direction in the ferromagnet simply by external magnetic field. So you can switch your ferromagnet electrodes or voltmeter from two magnetization direction, which will selectively allow you to contact spin up or spin down volt or chemical potential. Okay? So you will see a difference or switch between the two voltage levels, the two chemical potential levels for two spins, controlled by which direction or magnetic field you have to control this ferromagnet. But that's only one half story. Most important probably that half. Then you need to reverse the current direction. If you reverse current direction, you're promoting the other momentum, opposite spin. So now it's a mu up more higher than the mu down. And then your spin-sensitive voltmeter would actually measure a reversed switch of this different spin-dependent chemical potential. So that's a basic idea. So this idea has been around spintronic community in semiconductors, but they redeveloped this model for topological insulator. So this is a basic expectation, okay? And we build these simple three-terminal devices, basically two gold. I guess experiment is next. So this is a work by former postdoc, Dr. Jifao Tian, our professor at University of Wyoming. And he flowed this, so simple three-terminal devices, two gold, inject current, a DC current, well-defined direction, and use a ferromagnet electrode voltmeter, in this case a permalloy, contact in the middle as the spin-dependent voltmeter. So you see, if you flow current to the right, when you use the in-plane magnetic field to switch the magnetization from one direction to the other, you see a jump of the voltage measure in this direction. But when you reverse this current, you see the reverse jump. Okay, so that's the key. So this shows whatever you're measuring underneath has this spin momentum locking or spin current direction locking, right? When you flow current in one direction, you're promoting one spin direction. You reverse current or momentum, you're promoting the opposite spin direction, sensed by this spin-sensitive voltmeter. And if you reduce the current all the way to the zero, there's no current flowing, and you don't measure any spilling of the spin current potential. As expected, this is a linear response. So this confirms this expected property of spin momentum locking, And from a direction, so when you flow current this way, which voltage higher, you can actually infer the helicity of this electron you're measuring had this so-called left-handed spin helicity on the Fermi surface, which is consistent with what the people in ARPAS measure. So everything is good, people are happy. This, you can say, already realized potentially interesting spintronic device as a spin injector. You flow current, you don't need to use ferromagnet to inject spin. Here, use ferromagnet just to verify spin presence. But you flow a current using non-magnetic electrodes, you can get a spin polarized electron source, right? So this is useful for spintronics. Right. By the way, I should mention, you can push this technique to not just in the regular time devices. This is a nice collaboration I like with actually colleagues from Oak Ridge National Lab, Anping Lee, who is one of the leading experts in these 4-probe STM, actually doing transport measurements. So he has these 4 electrodes, each scanning probe tip. One of them is a magnetic scanning probe tip, nickel, doing similar measurement I just described on these topological insulator. And you see, depending on the direction of the magnetization of nickel, you can again contact one of the 2 spin-dependent current potential. But what I'm really like this example is that if you shrink, so this is now the 4-terminal measurement, 4-tip measurement. If you shrink a distance of 2 voltmeter to 0, for usual conductor, if the distance between 2 voltmeter is 0, you should measure 0 voltage drop. But here, when one of them is a magnetic, you don't measure a 0 voltage drop. So you similarly violate Ohm's law. Turns out what happens is that because this nickel would selectively contact the spin up or spin down chemical potential of electrons, while the other non-magnetic voltmeter measure the average. So you even when you separate 0, you still measure the splitting or half that splitting. Okay, so this is another example of unusual, maybe the transport properties. But I should give you a caveat in real materials. So I forgot to mention these materials. We see this good properties consistent with the expected topological insulator spin helicity is actually 3-element material called the bismuth, toluene, and selenide. The reason to mix these elements is to reduce the bulk doping, so the chemical potential is in the gap close to the Dirac point, so you are not influenced by this band. In bismuth selenide, that's usually not the case. In fact, when we perform cylinder measurement on bismuth selenide, we see the opposite spin helicity, which is not consistent with what you expect from topological surface state. This has caused quite a bit of confusion early on in the history of these kind of studies. Some of the early experiments performed by bismuth selenide. Early on, we thought maybe due to topological surface state, but now we don't believe so. It has this inconsistent spin helicity. So the real material is more complicated. I just probably be very brief on this. If you're dealing with some topology that we focus on right now involving multi-elements, it's simpler in the sense, really, there's no other source of a conducting channel other than these topological surface states I mentioned. But in many other materials, even though the band structure may be topological insulator, like bismuth selenide, you have many other conduction channels in the material. In addition to this topological surface state, which is what we want, you could have a band inversion, right? Conduction band bends down near the surface, causing a 2d electron gas with a spin of the couple, so the Rashba spin of couple 2 electron gas. That also can generate spin, partially develop spin momentum locking with opposite spin helicity, actually, that we actually believe is what could cause this kind of opposite sign we observe. And then if your bulk is conducting, you have a bulk spin Hall effect. So it's actually complicated for some of these materials. So for more details, we wrote a long PRB paper in collaboration with theorists like Mike Flatte to analyze contribution of these different possible sources. But good thing is, you don't need to worry about this complication if you work with a better topological insulator which has no bulk band occupation. Then you should not work with bismuth selenide usually. You should work something with more elements like bismuth, antimony, toluene, selenide. All right, but I want to highlight one other example about this spin. So I said, we and many others observe this. If you flow current in good topological insulator, right, and you induce the spin splitting in the chemical potential. If you reduce current to 0, the spin splitting goes to 0. Okay, so nice to see, nice to confirm, no surprise. So I really credit my former postdoc Jifa. So he didn't stop. He didn't say, well, okay, I got what I expected, done, experiment done, go home, even though it's already like a day or 2 later. So he kept measuring this. After a while, in some of the devices, after a while, the device entered a totally different regime. Something qualitatively different happened. So after a long time measurement, now if you reduce the current to 0, this spin splitting between spin down electrons not vanish. It's actually independent of the current now. So something very weird has occurred after a long time measurement. Okay. So now we're still using this ferromagnetic electrode to detect. We still observe a splitting of a spin down, spin up chemical potential. But this splitting now is no longer controlled by the external current we apply, which is needed in the first case. Now you do not need to apply current. If you don't apply current, you still measure voltage output. So something else now, the device has entered the new regime. Something else is giving rise to the spin polarization. What is it? So in fact, quite surprisingly, so when I showed this data to my colleague Supriyo, he said, well, you have something out of the voltage, which doesn't need current. That's a battery. So he called it spin battery. Actually, there is a word called spin battery. So this battery output a EMF you want. At low temperature, this polarization survived for a very long time, a couple of days. So GFAP really got tired. He actually went home, sleep, but this signal is still there. Okay. If you raise to 50 Kelvin, you can still, this signal decay in about 10 hours. So very long-lived. Non-equilibrium, this is non-equilibrium phenomenon, right? Spin polarization. If you plot this lifetime, first of all, this occurs at actually, you do not need external magnetic field. It occurs at even not so low temperature with some previous example of people observe relatively long-lived injected spin polarization. This is actually among the longest lived. All these previous examples are usually very high quality, high purity insulator or semiconductors. In fact, all of the examples that with the report lifetime are due to nuclear spins being polarized by electrons. So why do I involve nuclear spins? So we hypothesize this is also what's happening. But let me, we believe we achieve this quite long, maybe among the longest lifetime compared to some other materials, benefit from even in relatively dirty material. So even though we say we have pretty good quality topological insulator, but the real material in terms of defect is nowhere can be compared with this conventional semiconductor, silicon or gallium arsenide. Yet you have a pretty long-lived this that prevent this being polarization from being relaxed. And now I'll say words. We believe the topological protection actually plays some role here, possibly. So long story short, actually let me invoke this picture from a late Purdue colleague, Professor Overhauser, who was here for many decades. He's well known for pioneering the idea. You may have an Overhauser effect, which actually laid foundation for the NMR, a lot of NMR in chemistry, biology, of course, physics, and so forth. So one of the key concept foundations is called dynamic nuclear polarization. So the idea is if you polarize electron spins, build up electron spin. So if you just naively polarize nuclear spin, it's very difficult, right? Nuclear spin has very small energy splitting. You need a ridiculously low temperature or very strong magnetic field. But he said, no, you don't need to do that. There's a smarter way. It took a while for community to appreciate, but it's actually the main way in many modern day. So you first polarize electron spin, build up electron spin polarization. And then those electron spin can pump the nuclear spin by this hyperfine coupling, so dynamically polarized nuclear spin. And once nuclear spin polarized, they can have in many situations, have a much longer lifetime. And in this particular case, we think what is happening is in a good topological insulator, we flow electrical current for a very long time, build up a splitting of mu up, mu down for electrons. And this is pumping on the nuclear spin underneath the surface and build up nuclear spin polarization through this dynamical nuclear spin polarization. It's like charging a battery, charging that nuclear spin battery. Once the nuclear spin are pumped up, you can remove this initial pumping current, and this polarized nuclear spin can now has back action on electron spins on the Fermi surface and start to pump slowly, like your battery is now being discharged, but can be over a long time, and maintain a favored electron spin through the reverse coupling process, and that favored electron spin also translates into a motion, right? You guys detect in your voltmeter, so you have this splitting of electron spin potential you measure. So that's the qualitative hypothesis. This is hypothesis, remain to be directly verified, but this is such a long-lived non-equilibrium spin polarization. We don't know any other example that give such a long-lived non-equilibrium spin polarization other nuclear spins. So why it lived for so long? There are several reasons. There are actually several arguments to say it should not live so long. First of all, our topological insulator, it has conducting electrons. Usually conducting electrons are bad for nuclear spin. If nuclear spin sees conducting electron, they can flip electron spin to relax So there are two common mechanisms, right? The first mechanism I already mentioned is usually quite efficient for nuclear spin to flip electron spin and cause spin relaxation. But I mentioned in topological insulated surface state, you have this very unusual momentum spin topology. You do not have the other spin available to flip at that momentum. To flip, you need to go to very large moment transfer way of, which is more difficult. So this first, and usually in the electron system, usually people have to go to very high magnetic field, like fraction quantum Hall regime, or to remove the other spin state to very high energy to suppress this flipping spin via conductor electron. Here, you can achieve this almost very high magnetic field regime at the zero magnetic field because the other spin is not available easily. So there's one mechanism, you suppress the nuclear to conductor electron spin relaxation. The second common mechanism for nuclear spin relaxation is through nuclear diffuse to other nuclear spin. So if I have a nuclear spin, my neighboring nuclear spin can flip through this nuclear spin diffusion. It can also relax nuclear spin. However, here, the real space topology comes into suppress the second mechanism, because we have built up this spin polarized conductor on the surface, which set up an effective so-called night field, effective magnetic field. It decays very quickly into the bulk because the bulk has no conducting electrons. So that's the key. BSIM cell is not going to do this because bulk has no electrons. But for good topological insulator, there's no electron in the bulk. So this effective night field decays very rapidly within about nanometer, which is depth of the wave function of the surface state. And this very sharp gradient of magnetic field, or effect magnetic field, is known as another mechanism which can suppress the nuclear spin diffusion-induced relaxation because suppress energy conservation. So we believe this double mechanism, one, real space topology, because the spin polarized electron is only on the surface, and the momentum space topology, because the other spin state is not available at each momentum Fermi surface, work together to suppress or reduce these two common nuclear spin relaxation mechanisms that produce a very long-lived inject spin polarization. Which, if true, okay, there's more different work to need to do to directly probe this. As I said, we are only measuring electron spin in our experiment, but it'll be nice to direct probe nuclear spin even at this very low field. Has some challenge, but we have some ideas we like to probe. But this will be an example of functional devices. This topological protection, for example, these forbidden spin flip actually does something, in this case, useful to elongate the lifetime of the inject spin polarization. Okay, so briefly go to a different example, not using magnet. So I mentioned if you have these topological protect electrons, right? If the spin flip is forbidden, you have to reverse momentum, or momentum reversal is forbidden, you have to flip spin. Can also manifest into other devices. And here's an example of manifestation in Josephson junctions. If you put the two superconducting electrodes, flow a current at low temperature, you'll see a supercurrent. Okay. By the way, already, so this is in collaboration with my colleague here, Leon Rockinson, and work with two former students, both of them are faculty members. There's actually already unusual property of the way the supercurrent flow. When you the temperature, the supercurrent has some very unusual temperature dependence. We believe this is due to this real space topology, supercurrent wrapping around the surface. But most strikingly is the so-called phase-sensitive measurement. When you build this Josephson junction, you can actually apply a magnetic field. Actually, this is a SQUID device. It's in parallel with another conventional junction. By applying magnetic field, you can control the phase difference between these two superconducting electrodes, whose order parameter has a phase and amplitude. You can modulate this phase by this magnetic field. When you change the phase, the way the supercurrent, the critical current has a very interesting dependence on this phase, which is very different from conventional. The conventional German junction, people expect a sinusoidal, usually this Josephson relation, the supercurrent is, or critical current is a dependent sinusoidal between the phase difference to super. Here is a very non-sinusoidal, okay? It's almost like sawtooth, this sharp, very sharp transition. So in fact, it is known, if you work very hard, make the junction highly ballistic, scattering free. The example of this in other systems, you can start to have these non-sinusoidal or so-called skewed current phase relationship. And here, in the relatively dirty material, okay, without working too hard, and in this kind of flaky, junctions, we obtain this highly skewed current phase relationship, which usually require a lot more effort. So what we believe, okay, let's keep a lot of details. This is also an example. The reason here this was relatively easily achieved is because the scattering is forbidden in the topological surface state. If you want to backscatter, you have to reverse spin, which is very difficult because it's a momentum space topology. I mention this because this potentially actually give a useful functional device. Turns out there's already quite a bit of theoretical work saying if you have a Josephson junction whose current phase relationship is highly unusual, if you have got this kind of phase, you see it's not sinusoidal. But if you do Fourier transform, you can expand into high harmonics. If this harmonic term exists in current phase relationship, there are various ideas, including some, I think this paper is from Joe Moore, one of the QSAPI. You can actually wire up several Josephson junctions together to utilize this kind of property to suppress the dependence, for example, the effect of charge fluctuation. So this is broadly called circuit engineering or band engineering for Josephson junction. Utilizing unusual type of a Josephson relationship, you can actually build, of course, motivation is build qubit. As you know, Josephson junction is right now considered the transistors quantum computing, at least there's a front runner at this time, right? So there are many ideas how to improve Josephson junction or the way to wire them up. So this is one class of idea for Josephson with unusual current phase relationship. You can wire them up in a clever way to suppress the fluctuation to charge, for example, or electromagnetic field to make more resilient Josephson junction or maybe similar qubit. I think this is quite interesting. So far, I have not mentioned anything about topological qubit. This is not the topological qubit in the sense people usually talk about. This does not need more exotic or difficult physics like nonlinear annealing, which you'll hear a lot in the next talk. This is based on relatively simple conventional physics, but with a different current phase, you can potentially already gain something beneficial. Okay, so of course, we are interested in topological insulator also because this is one of the platforms, so-called the Majorana platform. When you bring a superconductor, build a bilayer, in this particular case called the Foucault proposal. Again, start with this spin helical electrons I highlighted, but if you bring a superconductor on top, theorists like Foucault told us there is a tension here because the superconductor I highlighted at the beginning favor these singlet, right, spin momentum entangled singlet wave function. You need pair plus minus momentum with the one pair of spin, but then you need to do it again with opposite spin configuration and write this singlet combination. But if you want to do this, if you want to induce this kind of pairing on the spin helical, like surface topological, this is not possible because I only have this part available. The other spin is forbidden, I said, on the same momentum. So this is not available. But nature is smart, or our theorists is smart. So say you can, again, I'm writing a very simplified hand-waving argument. You can still pair, but mixing the other triplet or P-wave effector component, then you can do this. So if you put the superconductor S instrument on top of topological surface state, you'll force the system to effectively have a channel, a component in this P-wave or triplet channel. And then there's a long history of theory idea says if we got a P-wave superconductor, if you induce first of all, you have these itinerant Majorana fermion now running around. But if you localize that near some kind of defect of vortices, you have a energy, you have a level stuck at the zero energy. And that is called Majorana zero mode, which is no longer fermion, so there's a lot of confusing terminology. And the zero mode actually anyons, or actually they are supposed to be non-binary anyons, yet to be experimentally verified, but that's at least the prediction. So this is one of the, you may have heard, there are other platforms to pursue this kind of Majorana zero mode, but this is one of the platforms, at least we work on in Quantum Science Center. And there are other material examples. There are also intrinsic topological superconductor, like this famous iron-based superconductor, it's one material, you don't need a bilayer. It's already have this topological surface state, but it's also superconductor. So the self-proximitize into something very similar to this. In Quantum Science Center, we're also building device structures, which instead of using a magnetic field to induce a vortex, we use an artificial nanostructure like a hole in a superconductor, a fancy word, anti-dot, to localize a vortex to bond, hopefully to bond the Majorana zero mode to do a more controlled experiments. And this is convincingly demonstrate this Majorana zero mode and even not being. This is one of the most challenging experiments, the kind of direction. A lot of people are working on different platforms. You'll hear a lot more about this kind of physics in different platforms next talk, but I'm just briefly saying in this context, the ultimate goal, of course, initially, we have a nice material with many others working on these experiments. You can measure zero mode, resonance, transport, STM. Even we learned how to do some of the experiments. So this is data reproducing some of the earlier results in this FTS superconductor. But people have seen these zero energy resonance which is consistent with the zero mode. But the challenge is there are a lot of other things in the real material can give rise something stuck as zero energy. So this is a first step, but this is far from actually it's a good step, but there's still a lot of more work. You need to control this, but the ultimate objective is to be, if you can control, localize 4 of these Majorana zero mode. So theory already work out a lot of beautiful design. For example, a typical topological qubit is based on 4 Majorana zero modes you can control, okay? And in this particular class of non-abelian anyon for Majorana zero, it's called the async anyons. It says if you fuse or merge 2 of these zero modes, you actually get a probabilistic outcome of either nothing or half time 1 or 0 electrons or even odd number electrons. So this is a signature called non-trivial non-abelian fusion rule. If you observe this, which is actually one of the experimental objectives, even though very challenging, we're still a while to go, but we're developing device measurement protocols to eventually try this kind of measurements. If you can observe this, that would be considered one strong proof for these kind of non-abelian statistics that would be hard to imagine occur otherwise. By the way, in this protocol, what you need for, you would need to initialize 4 of the modes into some well-defined sort of charge parity state, and pairwise, perform an important measurement called the fermion parity measurement. Basically, whether you end up fused into 0 or 1. And some of those measurement ideas actually based on you have to bring coupling to some kind of charge-centered qubit, maybe superqubit. This is also pursued, by the way, in some of these kind of schemes pursued in the Quantum Science Center in Thrust 3, for example, to perform the charge-centered measurement, because you want to project them into well-defined parity. But then you pick another pair, which is kind of orthogonal, which was not same, not the remainder of this pair. Then you would give half-half even odd outcome. If this reminds me of tilting the spin to the horizontal Bloch sphere, you get half-half outcome of up or down. It's actually a good analog, because this is actually the way how these topological parity can lead to allow you to build a quantum gate. So this is one of the basic ideas. So this actually is one of the exciting, I think, objectives in many projects in the Quantum Science Center. Okay, so actually 3 minutes for me to wrap up. Very good. Okay, thank you. So just very briefly, and you'll hear probably more later in the week. I spent most of my time talking about topological insulator, which is actually conducting, right? It had an interesting spin-dependent conductance on surface, very useful. But there's a whole large class of interesting quantum magnets or 2D magnets. So we also work quite a bit on these layered magnets, particularly insulator members. I said you may hear some more about these ferromagnets. They're interesting, these layered antiferromagnet, but also these ruthenium chloride that Vivian mentioned is all example of it as low field is an antiferromagnet, but when you apply field, it becomes something exotic, possibly. And there's a lot of interesting experiments I want to do in these layered ferromagnets. So let me just say, and again, building heterostructure, I probably already gave impression that's a kind of profitable thing to do, give you a lot of interesting approaches to probe these exotic magnetism. So by the way, if you stack these magnets, you can get something almost like a metamaterial of these spatial modulated ferro antiferromagnet. I think it's very interesting. So this is an interesting platform to do emerge novel exotic magnetism. But let me just 1 or 2 minutes say in this exotic magnetic spin liquid. So you already saw this face down from Vivian. There's a lot of interest to really probe, develop different experiment probe. What exactly are these spin directions pointing? So there are lots of the experiments. I mean, I mentioned these spin are supposed to be very disordered, fluctuating, but have some kind of long-range correlation possibly. How do we even probe these spin direction? And in reality, skip this. So we, again, back to this idea, using one spin system to probe that spin system. So we have developed, tried this experiment technique. Remember, these ring chloride is an insulator material. So itself, you cannot do directly transport experiments. But we can build a bilayer, make the contact with a conducting material, in this case platinum, which I said when you flow current, you induce a spin polarization at the platinum surface and is locked to the current. So partially spin moment locked. You can use that current-induced spin polarization. Turns out, depending on that spin polarization, whether it's the relative angle of that spin with the magnetic moment in another material, in this case, it's this exotic material, ruthenium chloride, you actually have a different resistivity depending on relative angle of that orientation, which induce a transport anisotropy as well as emergent Hall signal. People call that plain Hall effect. It's not a real Hall effect, just due to this transient anisotropy. And using that, and people apply this technique to well-defined ferromagnet and antimatter insulator, but we're applying to this exotic insulator, and we observe a signal depending on there's an interaction between the current-induced spin on platinum with this undetermined moments in silicon chloride, which actually behave a little bit like antiferromagnet, but the signal becomes stuck, saturated once you hit this candidate spin liquid region, not growing anymore. And our results, still a lot more understanding is needed. Actually, we're getting good suggestion from discussion with a lot of people, both in Oak Ridge and here at Purdue, to say what we seem to be seeing is we're probing a spin anisotropy state or spin nematic state, according to some other theorists, is that in the broad region of this phase diagram that Vivian briefly showed, a lot of these still have question mark, of course, and we're seeing this signal called the spin Hall magnetic resistance. So there's oscillatory dependence of the resistance of platinum when you put a contact with the thin chloride. The oscillates function the angle between the current and magnetic field, which says no matter what kind of spin you have in thin chloride, somehow once you turn on in-plane magnetic field, it starts to be oriented transverse to the magnetic field. By the way, that is not to say it's an ordered system, because individual spin can still fluctuate crazily, but now you have a reduced degree of freedom. You can fluctuate in one of the two directions along this transverse quantization axis. So this is to say there's a spin anisotropy, transverse anisotropy setup here, which is not inconsistent with these various phases, but this together has to constrain our understanding of the candidate quantum spin liquid. So hopefully this gives you an example. Using a spin-sensitive probe, you can even probe an insulator, but with an interesting spin degree of freedom. And there are many other interesting ideas, some developing QSC, some developed elsewhere, actually build up interesting devices, some using superconductors, some using magnet, some actually using scanning probe to probe insulating quantum magnet like ruthenium chloride. I think it's a very exciting area that will, all of these are theoretical proposals. I think one of, we hope, right, we get a chance in the center, for example, to turn a lot of these into interesting experiments in the next few years. So with that, I won't have time to talk about quantum sensing, but let me just end here to say it's actually very interesting to combine these spintronic quantum material. You can develop interesting spin-sensitive measurement techniques to probe these material and also emerge interesting new quantum matter and maybe useful devices. So thank you.
All right, we'll open the floor up to some questions if anyone has any right away. If they do not, we have about 10 minutes of recess. There are refreshment out in the back. But if there are any, you can also follow up with Professor Chen during the break. If you have any immediate questions, please raise your hands. Okay. All right, let's thank the Professor Yang Chen again, and we'll get into our break. We'll resume at 10:40 for our next talk. Refreshment. All right, the speaker's on his way to get mic'd up. In the meantime, if you don't mind settling in. Also, just some logistical announcements. Thank you all for those that submitted their poster information. You might have noticed that your posters are numbered. When you are ready over during the lunch period, please go down the hall, and there are whiteboards with numbered cards on each whiteboard, so you'll find your number according to the list of poster titles. If you brought a poster and you were not listed, I'll find the one that's not numbered, and I'll come gather your information accordingly in the afternoon. There he is. All right, let me go ahead and introduce our next speaker here. So we have Professor Mike Manfra presenting next. So Professor Michael Manfra is the D. O'Brien Distinguished Professor of Physics and Astronomy, Professor of Materials Engineering and Electrical and Computer Engineering at Purdue University. He serves as the Scientific Director of Microsoft Quantum Lab at West Lafayette. He received his AB from Harvard in 92 and PhD from BU in 99. Spent 2 years as a postdoc and technical staff at Bell Labs in 2001 and Lucian onward. After 10 years at Bell Lab, he joined Purdue in 2009. He's the Keck Foundation awardee in 2013 and elected a fellow of American Physical Society in 2015, and in 2016 became the scientific director of Microsoft Quantum Lab West Lafayette. His team develops nanoscale electronic devices to explore fundamental aspects of topology and strong electronic correlations in 2020. This group reported interferometric measurements of anionic braiding, giving experimental evidence for predictions earlier. He works with Microsoft Quantum to develop scalable quantum hardware for leveraging novel properties of anions.
Thanks. Okay, thank you for the introduction and the opportunity to speak. This is too loud, just let me know. Just kind of sort of take it down a bit. I spoke last year talking about interferometric measurements of anions, and I don't want to repeat the same material that I discussed last year, so I'm giving you an update on some of our newer results. This necessarily means that it's fairly detailed. This is not a 10,000-foot view of the field. I hope that the students will feel free to ask questions, anything that's not clear. But what I really want to show here is continuing progress and how we are now able to make very complicated devices and measurements and learn more about anions. Okay. So I'm going to be talking about interferometric measurements of statistics, anionic braiding statistics. And these are interferometers of a very special kind. They're the electronic analog of Fabry-Perot interferometers that you may be familiar with from optics. Now, strictly speaking, we're not interfering photons. These are interacting electrons, and we have to take the fact that these electrons do feel the Coulomb force when considering the properties of these interferometers. But nevertheless, since we are fundamentally interested in phases and statistical angles of excitations, we know from optics the exquisite sensitivity of interferometric measurements. So it makes sense that we would try to find an analog for fractionally charged quasi-particles and particles with fractional statistics. Let me be clear, there's a lot of words and buzzwords that you hear, topology this, topology that. When I'm talking about a topological phase, I mean something very distinct, not just topological band structure, but topological phases of matter that support fractionalization of charge and statistics. These are the topological phases that are of potential interest for computation. Now, there are different types of fractionalized excitations. They can be abelian, they can be non-abelian, but this is what I mean when I say I'm talking about topological phase, okay? So actually, the history of this field is quite long, and the theory was developed a very long time ago. The idea that the quasi-particles of the fractional quantum Hall effect would have fractional charge, a quantized value that is a fraction of the bare electron charge, and fractionalized statistics goes back to the earliest days, the early 80s. Laughlin for fractional charge, and to Halperin and others for the fractional statistics. So this is in the early 80s, the theorists knew, or would suggest that if you probe these systems, these fractional quantum Hall systems and two-dimensional electron gases, you should have fractionalization. Now, the reality is how you develop probes and systems to actually make those properties manifest directly is another story, and that's the one that we've been working on for some time, and I'll try to tell you about. So while the underlying statistics was known in the early 80s, in the late 90s, there were some theoretical developments, primarily driven by Sivaji Sandhi and Steve Kivelson. Claudia Shimon is the first author, Jacques Anouilh is also a contributor, that first put forth this notion that if we build the electronic analog of interferometer, we can probe the fractional charge, we can probe the fractional statistics, we can even probe the Luttinger liquid behavior of the chiral edge mode circulating around the boundary. And so, I mean, it's hard to see in this abstract, but this is a paper from 1997. And what I've summarized over here is that, you know, in this simple picture that they developed, we should be able to access 3 important parameters of a highly interacting topological phase supporting anions. Now, in the theory paper, as theorists do, they draw schematics. I call them cartoons of what you needed to build. What they have here is a Hall bar, just a piece of gallium arsenide with a 2-dimensional electron gas in it. They build or draw quantum point contacts that bring the edge states into close proximity to induce scattering. And they have a couple of those so that we build an interferometric chamber so that there's actually a region in here. If the transport is coherent, we can actually look at the interference of the backscattered waves. And in this region, they also have potentially a gate where we can modify the flux going through the system, or equivalently the quasi-particle number. Now, this picture looks fairly straightforward, and the theory is beautiful, it's very prescient. It said exactly what we should see, but the reality of how you build devices and the mesoscopic physics that you need to understand to get these to work has been the challenge, and why, you know, in 2020 to 24, we're talking about the first direct observation of anionic braiding statistics. Okay, the system we work in is the 2-dimensional electron gas in gallium arsenide, aluminum gallium arsenide heterostructures. And the reason why we work on this, I want everyone to realize, is this data, okay? Over many years, through the work of many, many groups, the quality of these materials has progressed to such a level that we can see all of these very highly correlated states with very small energy scales developed in one material system. So here's an overview. This is just the longitudinal resistance in red, the Hall resistance in blue as a function of magnetic field. This is just a bulk transport measurement of a typical sample grown in our laboratory, measured at very low temperature. And from, you know, your basic understanding of semiconductor physics, you know that the Hall resistance should be proportional magnetic field, inversely proportional to the carrier density. And you do see the remnants of the linearity in this blue trace. Of course, that's interrupted by these very flat, very highly quantized plateaus that are the signature of the quantum Hall effect. I've labeled a particular number for these, filling factor 1, filling factor 2. That filling factor tells us the ratio of the density of electrons to flux quanta penetrating the system. So at nu equals 1, I have exactly 1 electron per flux quanta. At nu equals 2, 2 electrons per flux quanta. And in those instances, the gap that must be here in order to have the quantization and the longitudinal resistance dropping to 0 is just the cyclotron gap, the discrete nature of the Landau levels, and it's the single particle gap. Of course, there's fractional values that has the same phenomenology, but a completely different origin. It's driven completely by electron-electron correlations. All the electrons reside in a single Landau level. There's states available, but nevertheless, the system develops a gap. Now, why do we look at this particular system? Not only is the quality unmatched, our ability to manipulate, process, and make very complex devices has been developed over many years by many groups to the point where we can have control over the system and really test, make very precise and tests of exotic physics. So if you're interested in composite fermiology and you worry about such things, you can look at the n equals 0 Landau level. You know, you can study all the composite fermions that your heart desires. If you're considering non-abelian states, you look in the n equals 1 Landau level. Here's nu equals 5/2. Note that this is fully quantized. There's no ambiguity, 0 resistance. At a very low magnetic field, we have this quantized down around a Tesla now. So this notion that you have to go to very high fields is you know, a relic of, you know, maybe 30 years ago. But all of this physics occurs at relatively low magnetic fields. And it's because of the development of the samples that has allowed for this. Okay. Now, I'm using the example of the fractional quantum Hall effect in gallium arsenide, but by no means is this the only system in which, you know, I'm hopeful and confident that anyons may eventually be found. I think it's a pretty exciting period in condensed matter physics for development of different material platforms and actually seeing progress in those. You heard earlier from Vivian about quantum spin liquid. Of course, there are topological superconductors, both the intrinsic type and in engineered hybrid systems. That's what I work on with Microsoft, engineering topological superconductivity in hybrid systems. And you know, there's been really exciting developments in graphene in even the last few months. Seeing the fractional anomalous Hall effect is in rhombohedral quintuple layer graphene. This is out of the Jew group at MIT. So, you know, gallium arsenide 2DEGs are sort of the paradigm in which the tests can be done, proof of principle, in which we can actually see if these tools that we're developing work and expose the physics we want. But I'm very hopeful that in time, you will see these types of techniques that we develop applied to other materials. And in fact, what I want to mention is I'm talking about building interferometers and looking at quasi-particle interferometry. Very recently, two of the leading groups, Andrea Young at UCSB and Philip Kim at Harvard, have put papers forward saying that they also have evidence of anionic braiding, confirming the statistical angle that we've measured in gallium arsenide, but this time in graphene systems. And they've built, you know, similarly complex devices in their materials as well. So this probe of using interferometry to probe statistics, I think, is general and is very powerful. And my hope is that this will continue on. And the field will not be limited to just what we're doing, but as you see, other examples. Now, this has been this has been a quest for sort of 40 years in the field, and I'm often asked, well, why did it take so long? You know, if you can do it, anybody can do it. Why did it take so long? And the answer is that, you know, everything has to be in place, and it all has to be in place with one group of collaborators. So, you know, in order to, we had to make innovations in heterostructure design. Then we have to build very complex mesoscale devices. And then we have to measure them, you know, making small signal measurements at very low temperature. And putting all those pieces into place takes a long time. And we learn from the experiments and failures of other groups. We built on that. And that's been part of this process. And what's been unique about Purdue is that we have everything all essentially in one house. We can design and grow the highest quality materials. We can design and fabricate mesoscopic devices, and we can measure them. You know, this isn't that common. Maybe the Heibloom group at the Weizmann Institute is similar, but to put all this stuff together takes time and takes a lot of work. And that's why, you know, in the end, what you'll see is you can say, well, I could have done that too. And you could have. I'm sure you could have. But it takes a while to figure all this out. Okay, so just to summarize perhaps what I talked about last year, in a series of experiments in which we made a significant modification to the head structure design by introducing ancillary quantum wells. We're interested in looking at a primary transport and a primary quantum well. We built in through growth 2 quantum wells, approximately 25 nanometers on either side, that have high density electron gases in them. We were able to overcome some of the mesoscopic physics challenges that had hindered some of the earlier investigations. And that first led to the observation of Aronoff-Bohm interference in the fractional regime. And then in 2020, the observation of fractional statistics and the measurement of the statistical phase at 1/3 of 2 pi over 3 in agreement with predictions from Halperin and others. Okay. We continued along that path and said, well, how, it's not just the individual phase slips that tell us that the anions are present in our devices. There are a range of device operating regimes that are, if you do have anions, are sensitive to them. And you often hear people claim, we need a smoking gun. There's one smoking gun. That's a fallacy. There's no such thing as a smoking gun experiment. There's a build-up, a preponderance of evidence that over time becomes harder and harder to think of an alternative explanation. And that is what leads the community to believe in the end of an underlying physical mechanism. So we know from what theory tells us that there should be many signatures of the fact that anions are present in our devices, not just in the individual phase slips. We probe that by redesigning our header structures and devices to see if these effects were indeed true. And one here in 2022, we saw very precise phase slips, but we saw a very precise transition from an incompressible regime near the center of the plateau to a compressible regime out in the flanks. What does that mean? In one region, anions are very rare, they're hard to make, and therefore we see the discrete events. As we go out into the flanks, anions are made with the insertion of every flux quantum. They're abundant, and that modifies the interference pattern as you see here. Okay, now that work at 1/3 was also, I don't want to say confirmed, there were independent measurements using different techniques that came following our work that demonstrated or were consistent with anionic braiding. So one powerful technique is to look at cross correlations in noise. You have QPCs, and you look at the cross correlations in quantum shot noise. This is a technique that's been pioneered both the Weizmann Institute in Israel and also at Saclay in France. And both of these groups reported experiments where looking at cross correlations, basically what you might call time domain braiding, gave further substantiation to the claim that their anions are present at 1/3 and can be probed directly. But the question for us, and the one I want to address now, is that's great, and that's, we had a good time doing this, but how general is the technique? Can we push it further? And we measured 1/3 because it's the primary Laughlin state, the largest gap state. It has a single edge mode circulating around the periphery. It was the easiest one. But if we want to keep going, we want to look at more exotic states, and not only exotic abelian states, but also putative non-abelian states. And so the question for us is, have we gotten all we can out of this horse, or can we ride it a little bit longer? And there isn't, as I was saying, we want to see the Jane sequence and candidate non-abelian states. And it's not an obvious extension to say, I've done it at one primary fraction, now I can take it to other fractions. And I just want to point out why that's so. The theorists, well, we shouldn't listen to the theorists too much, because they would say it was too hard and wouldn't work. There's a paper from Dima Feldman and Burt saying, well, yeah, it worked at 1/3, it'll work at nu=1, but life is going to get tougher as you go on. Why is this so? Well, say you go to the first daughter state of nu=1/3. You look at nu=2/5. What is the challenge? Well, the gap is smaller. The gap, the underlying many particle gap, is significantly smaller. There are multiple edge modes. 1/3 is unique in that it has only one circulating chiral edge mode. If you have multiple edge modes, their interaction can be important, and you have to learn how to interfere them independently and know which mode you're interfering. There's a smaller effective charge. The charge now at 1/2 is E/5. Everything scales in the size of the charge. There's this factor of delta nu between the inner and the outer modes of 1/15 between the edge states. That's a very small gap. So this ability to independently interfere outer and inner edge modes would prove crucial to the success of the experiment. The data will also look quite different because the physics is quite different. there'll be very slow Aharonov-Bohm evolution. That's because the periodicity is so much larger, and very large, relatively speaking, discrete jumps, because the statistical phase at 2/5 is actually -4 pi over 5. That's the theoretical expectation. So in the end of the day, we want to measure charge and the abelian statistical angle. And remember, the theoretical paper told me that these interferometers could access both charge and statistics. Okay, so in work that came out late last year, we extended the technique by building new header structures and new devices to this regime of nu equals 2/5. And we're able to measure in the experiment the charge of approximately 0.20 of the bare electron charge. That's what's anticipated by theory. And the anionic phase factor, which should be -4 pi over 5. We measured, you can see the measurement plus the error there, very close to that value. So this tells us that the technique, although life gets harder, is general enough, and we can apply it to more complex states, and hopefully it can become a tool of general utility for many materials and systems. But this exsensitivity to fractionalized charge and fractionalized statistics is really what drives the effort to make interferometers. Okay, just to get a little bit more concrete, if you consider the two-dimensional electron gas as the blue region, our device schematically looks like the following. There are galvanic connections called source and drain contacts. Of course, there's voltage probes all around. The blue regions is the two-dimensional electron gas. The yellow lines and T's are surface gates that we use to deplete the two-dimensional electron gas and define the area of the interferometer. These lines that come in close proximity are called quantum point contacts. That's the electronic analog of a beam splitter. The current will come in and be partially backscattered. Most of it will circulate around the interferometer. But we control these, the behavior by applying gate voltages. We can use these side gates called plungers, these T's, to make the area bigger or smaller. Think of it as an accordion. We squeeze it, make it smaller, reduce the gate, negative gate potential, make it bigger. So the surface gates define the electron interference path. Quantum point contacts act as beam splitters. In the quantum Hall regime, current is carried by chiral edge modes, circulate around the periphery. They come into the first QPC. We siphon off or backscatter a small amount of the current. Most of it circulates around the interferometer. We again control the backscattering at the second QPC. This interior region is where the current circulates and picks up a phase relative to the part that was backscattered at the first QPC. So the current that comes out at the drain is what we measure. We measure the conductance of the device. The current that comes out, of course, is proportional to the transmission coefficient squared of the first QPC, the transmission coefficient of the second QPC squared. That's the boring, scattering term. But then there's this cross or interference term that goes as cosine theta. Now that theta is the interference phase. It's not the anionic braiding phase. It's the actual phase that develops inside the interferometer. And so if I'm dealing with just boring old electrons in the integer regime, that's nothing but the Aharonov-Bohm phase. It's proportional to the area of the interferometer times the magnetic field. That's the flux penetrating through. And of course, it's periodic in the fundamental flux quantum H over E. So I can measure interference by measuring the electrical conductance across the device. I can operate the device by changing the area by these T gates, or magnetic field. I can tune the magnetic field. And over the years, the theorists have worked and told us what we should expect. So if I plot the conductance in a two-dimensional color plot in the B delta V plane, what I should see are lines of constant phase or constant conductance with negative slope in the B delta V plane. These barbershop pole patterns, has been called pajama plots, is the naive expectation. Now, if I'm in the fractional regime and I have localized quasiparticles, life gets more interesting. The AB phase is scaled by the effective charge. The periodicity will change in directly proportional to the multiple of the effective charge over the bare electron charge. And the interference phase will be directly proportional to the number of localized quasiparticles inside the interferometer times the anionic phase factor. So if I were to change the number of localized quasiparticles, I should see discrete changes in the evolution of this pattern. Slips, noise, somebody you might say at first noise, but phase slips that herald the removal or addition of an individual quasiparticle. Okay. Now, I am not going to have time to go over all the details. I've covered it in many talks before, but what's really the key here is, I've made this analogy to optics, but of course, photons don't interact. And so we have a non-interacting system. And so this notion of an inert interferometer has to be modified, of course, if I'm dealing with charge carriers subject to the Coulomb force. And there's been much theory that's developed over the years by many, Halperin, Steve Simon, Dima Feldman. How do we treat, what is a formal way of treating this so we can understand what happens in our interferometer? And what it comes down to is we have to know the couplings. We have to know the edge stiffness, basically how much energy does it cost to add or remove charge from the compressible gapless edge mode circulating around. That's parameterized by this number called Ki. We also need to know the important parameter is the bulk edge coupling. If I have a localized charge, an anion sitting in the middle of my interferometer, how much does that affect the edge through the Coulomb interaction? And what I want to do is try to minimize that interaction as far as I can, in order to have the interferometer behave in this sort of ideal AB limit. But as it turns out, you can write down an energy function just for the electrostatic energy that is involved in the formation of an interferometer like this. And what we've just been able to do and add to this field is figure out that you can measure those coupling parameters in situ. They're not fit parameters in a theory. This KIL and this KI can be measured in situ for your real device, because, well, we can use all the tricks of dot physics that's been built up over many years. We know how to figure out lever arms. We know how to figure out what the charging energies are. And we use those tools to relate them to these coupling parameters, and therefore understand our interferometer better. So in the presence of these real coupling constants, the phase factor does get modified. It looks particularly nasty in this form, but it's really not. The modification of the AB part is just related to the coupling between the charge on the interior and on the edge, how much that actually changes the area of the interferometer. And all of this can be related to quantities that we can measure in situ. Okay, so for the 2/5 experiment, which was completed, we published at the end of last year, we had to modify our structure design to get the right density in the middle, high density 2 DEGs out in the 2 sides. In order to have an appreciable gap at nu equals 2/5 while maintaining still relatively weak coupling between the bulk and the edge. There's finite coupling between the bulk and the edge, but it's something that's, if you will, perturbative, and we can measure. We have to make fairly complex devices, but nonetheless, even after making mesoscopic devices and doing lithography on both sides of the chip and thinning it down, the relative quality is still quite high. And so there's well-formed fractional quantum Hall states, even though we've kind of, in order to build a mesoscopic device, had to beat it up a bit. Okay, what does the device actually look like? Well, there's this interferometer that I showed you in cartoon fashion sitting in the center. It's a mesoscopic device, less than a micron on a side, sitting in the middle of a mesa that contains all 3 layers. We also have to do front and backside lithography in order to gate off the galvanic connections between the various ohmic leads. We want to see transport through this primary quantum well, but since we have these other quantum wells fully populated for screening purposes, they would short circuit the whole device unless we do something. So we borrowed a technique to cut out this parallel conduction from a colleague of mine from the old days at Bell Laboratories, is before I was there, but Jim Eisenstein was studying bilayer systems and wanted to look at the correlations, excitonic states and drag between different layers. And he developed a technique where you have this sort of subway system of gates around where you can apply a gate voltage, disconnect the contact from one of the wells by doing it on the top side. You do it on the bottom side, you can disconnect the bottom screening well. I still have galvanic connection, but only through the primary quantum well. Those two DEGs are only depopulated out in the periphery. In the interior, they're still fully populated and able to screen and have their beneficial effects for device performance. Okay, so here what we did is we have a new use, but we wholesale just took over something that had been developed in a previous generation of physics experiments. Okay, now how does this differ from 1/3? We've done 1/3 and the evidence is, I think, fairly convincing for anionic braiding at 1/3. Well, I want to show you a comparison. Here on this device, we have many probes, voltage probes, so we can measure RXY, which is the bulk Hall resistance. That's the black curve. And you see here's nu equals 1/3, here's nu equals 2/5, here's nu equals 3/7, and the nice scare case that you'd expect when measuring any Hall bar. The red curve is the quantity called RD. It's the drop across the mesoscopic device that we measure simultaneously with the bulk transport. Okay, so I've depleted the gates. There's a well-defined interferometer, but now I want to know does a 2/5 state live inside that interferometer once I've defined it? And there is, but you can see the range over which it exists where there's quantization in RD is rather narrow. Okay, it's a more fragile state. The gap is smaller, there's two edge modes, there's an inner edge mode that can backscatter. So the regime of operation compared to 1/3 is restricted. We can look at the individual QPCs and look at the backscattering. We can in fact control the backscattering. So out here at relatively high gate voltage, we see quantized conductance corresponding to 2/5. We start pinching down the QPCs. We lose the quantization, start backscattering. We see an intermediate plateau when we fully backscatter the inner mode, but are transmitting the outer mode. And then we begin to backscatter the outer mode. What this data tells us is we know exactly what we're doing with the chiral edge modes, how much we're backscattering, how much we're interfering, and which one it is. And the important point is that we can resolve the two of them. They will have different properties because they're different modes. Okay, we took this device and operated it in a trivial regime. It's very important to do things, sanity checks in your experiment to make sure everything makes sense. We first operated at integer filling, and we see AB oscillations as expected. These modulations are due to a finite but small bulk edge coupling, which we can actually extract from measurements. We can extract the gate lever arms. We know how much we're changing the area per change in voltage, and we can measure the periodicity in this central incompressible region. So we know that one flux quanta, what corresponds to the insertion of one flux quanta, the effective area of this device is about 0.4 microns squared. Okay, so that's the electronic area of the device. And all of this can be mapped out in excruciating detail by doing these calibration measurements. It's not like we make one measurement and say, we hope, oh, look, it must be, you know, anions or something. We know exactly how the devices work, what their response function should be, and only later are able, to, based on that, to conclude in the interesting regime that we have anions. So these periodicities are mapped out and known in a more conventional area and then used later on. Slow advance. Now we go up to nu equals 2/5 and look at the interference of the outer mode. What that means, if you look at the cartoon over here, I've set up the backscattering of the QPCs such that the inner mode is fully reflected, and it's circulating in the interior and reflected in the outer region, source and drain region, and the one I'm actually scattering is the outer mode, the outer mode, the one that's closest to the edge. If I set it backwards, I may sometimes get inner and outer messed up, but this is the outer mode. And what it looks like is what we see at nu equals 1/3. Okay, the lines of negative, the lines of constant phase with negative slope in the incompressible region, and then a transition to flat lines. This is all what we saw at 1/3. Luckily, this is what we should expect because the outer mode theoretically is predicted to behave as the single mode at nu equals 1/3. This is what the theorists would expect you to see. And the fact that we've isolated the inner mode, so it's circulating only in the interior, and see behavior like this tells us that we are indeed scattering the outer mode. We're at 85% transmission. But there's things that we also can learn that tell us that while the mode behaves as if it's 1/3, the state is not. The gap is smaller. There's a narrower region of incompressibility, and the edge of the inner puddle remains gapless. So the overall charge in the center is quantized in units of E/3. We measure that. That's not the E/5. The E/5 charge is associated with the inner mode, and that's the one we have to look at next. Okay, we can track the interference pattern all the way from 2/5 to 1/3. We lose coherence, and the normal AB part when the state becomes compressible, just like you'd expect. There's no reason to have phase coherence when the system, the edge states are connected across the interferometer. This is all consistent with what you might expect. Okay, then we do the move to backscattering the inner mode, the one that's closest, the slower moving one in the interior. And the pattern looks quite different than it has before. What the first thing we notice is that the range of incompressibility, that's where this checkerboard occurs, is quite narrow. This is associated with the very small charge and the very small gap. If we move the magnetic field too far, we lose basically the interference pattern. It becomes incoherent. But in this central region, in the incompressible region, we can make some observations. First, there's a small incompressible region. The vertical line cuts versus gate voltage are not sinusoidal. So when you first look at this, it's very hard to interpret. You would think that a vertical line should be sinusoidal, but that's not the case. If we take a vertical cut, which is the blue line, you just see this sort of behavior. But if we move along one of these slanted lines that goes red, blue, red, blue, red, blue, we do recover the sinusoidal dependence that we expect from the interference pattern. The issue that we're seeing is that this AB oscillation has a very long period because of the small charge. So it's evolving very slowly. Nevertheless, when we add a quasi-particle, boom, there's a big discrete phase slip, and that's why you see, say, this going from blue to red like that. Okay, so we can do this analysis and actually look in detail of what the flux periodicity and the voltage periodicity is along these particular lines. Okay, so the gate voltage periodicity is on the order of 14 millivolts, applies a flux periodicity of 4 phi naught. Now, this is neglecting the bulk edge interaction. We should see something on the order of 5. The discrete jumps have a slope of 0.75 millivolts per millitesla, consistent with the transition in localized quasi-particle number. By looking at these lever arms that I told you about before, we actually know what that slope should be. Okay, so if we calculate what this gate voltage periodicity should be, it should be modified from the pure unadulterated value by a function of kappa, which is the ratio of the bulk edge coupling to the edge stiffness, which we can measure in the experiments, and this quantity called alpha bulk, which is the lever arm. How much charge do I effectively change inside the interferometer for a change in the gate voltage? And as I said, we do those experiments first. We know those values. So there's no free parameters in here. If we then calculate what the effective charge must be, where we say E star is the only free parameter, we measure the gate voltage periodicity, it comes out to 0.17 plus or minus 0.02, with the expectation being 1/5 charge. This we found to be pretty good given the sensitivity of this particular state. The point being here is, if there's anything I want you to come away with, is this isn't a fit. There's no free parameters here. The only free parameter is the charge, but all the other things are measured in situ. Okay? We can do the analysis of the discrete phase jumps, and I'm going to run out of time with this, but there are formulas for what that should be once you include the bulk edge coupling. Now, the bulk edge coupling in this device is rather small. It's only about, the ratio is 0.17, okay? So that's not a lot of bulk edge coupling. But the fact that the charge is so small and this delta nu is 1/15, if you look in the formula for how much that affects the measured phase angle, it's quite pronounced. So even though the physical coupling is small, its effect is quite large. So if we extract the anionic phase from the actual measured phase slips, which we can do, and consider the bulk edge coupling, which we measure directly, we get a statistical phase of minus 0.43 times 2 pi, which is what we expect for the 1/5 state. The reason this is 2/5 state, sorry. The reason this is interesting, everything is not the same. It's not as if the filling factor, the charge, and the statistical phase are all the same. There are different numbers. We're at a state that's derived from a principal Laughlin state, so the charge, the statistical angle, and the filling factor are not all the same number. It, in some sense, demonstrates that the utility of the technique to more complex settings. Okay. Now, what's the time left? 2 or 10? 2. All right. What else is going on? What else can we do? There are other circuit approaches to probe non-abelian anions. There's been many theoretical proposals for measuring conductance, say at the nu = 5/2 state, which is non-abelian, putatively non-abelian, but it could have many different underlying topological orders. Discriminating between these different states is not that easy. There's been proposals for doing conductance measurements where you basically interface different filling factors, 3, 2, and 5/2, and look at the interface modes, the conductance of the interface modes. This is work out of the Weissman group. And there are predictions of what the conductance quantization should be if you had a Moore Reed, or if you had a Parker-Hole-Pfaffian, or the anti-Pfaffian state for the experts. These different underlying topological orders give different conductance quantization. I'll just skip through the thing, but we're actually building these devices now. They're multi-layer, many layers, but we can build them and start measuring the conductance in these funny geometries where we have filling factor 3, 2, and 5/2 all butted right up against each other in a very small area. If we measure the conductance, the value is preserved, even though these devices start getting messy with many dielectric layers, we still preserve the 5/2 conductance plateau. And once we start looking at the interface conductance, we also see the expected value at the interfaces. So this is not proof yet of the underlying topological order. It's just saying you can build mesoscopic devices that have direct access to, the most central features of these topological states: fractionalization of charge and statistics. Okay, so what's next? We're obviously going to try to do it at 5/2. We want to better understand tunneling processes at QPC. These are supposed to be Luttinger liquids. We would like to see that behavior manifest. There's all sorts of things that can be done, even in the integer regime, where exotic pairing mechanisms have been proposed. There's entropy that can be measured. We can look at for topological degeneracy through entropy measurements. So there's a lot going on, and what I want to leave the students with is this is just the archetype of strongly interacting topological phase. The fact that we can actually make complex measurements and complex devices with it gives us an advantage right now. But the hope is that this kind of these approaches could be applied to the other material systems that have other unique phases that we don't have access to in gallium arsenide. In the the anomalous quantum Hall affected zero field, for example, that's seen in graphene and the TMDs. That's something that would be nice to see what the underlying order is, and these types of techniques are what will give you that access. Bulk transport, there's only so much you can say. Okay, conclusions. I hope I convince you Fabric Pro interferometry is a way to quantitatively nail down statistics and fractionalization in real devices. Okay, it works at 1/3, it works at 2/5. We hope that it will work in other arenas as well. So thank you.
All right, we have time for some questions. Any questions immediately from the audience? All right, yes,
Right here.
Professor Sega.
Look around.
I got you.
I want to ask a related question on Majorana fermions. It's related, it's not exactly what you do, but since the promise was there for a long time, even here at Purdue was done the first observation, or first claim for, not observation, but for evidence.
Be careful.
And later on, okay,
Be careful.
Kovenhoven and Moti Eibblum also published some papers on that. This was already in 2011, 2012.
I'm fully aware of that, yes.
You're fully aware of
Thank you.
What's the situation? And when you told us about Microsoft,
Yes?
what's the status? I mean, they
Did you read the
pulled out their
papers?
money.
It's all in the papers. We just did the parity measurement. There was a reference made to measuring parity in some of these devices. That's the paper that
I
I
didn't
left.
read. I'm not from that field, but I follow the literature a little bit. So is there a claim on the first observation of Majorana fermions coming up somewhere?
Majorana zero modes, these sort of blanket statements that I warned against of saying a smoking gun, there is a paper that's published, we published it last year, showing devices that pass the topological gap protocol, a predetermined set test that you need to apply to a particular sample, and this is what that paper was out. It's out for a year now, where in this geometry, we are actually able to demonstrate, you set up a criteria that you must pass before you measure the device. You apply that criteria. If you pass it, then you say it has passed the topological gap protocol. So yes, it's a
Very careful not to mention the word Majorana in your talk, even once. So that's why, it's difficult to...
I'll answer any question you want. What exactly are you asking?
No, I'm not from the area. I want to know, since I follow...
Yes,
I did
so
follow
I'm
the
telling
literature.
you that there's been progress within the Microsoft effort. There are publications out now, one on the archive where we actually did the parity measurement that was discussed. That's a very difficult measurement, but it's done by dispersive capacitive gate sensing at microwave frequencies. And so, I feel sometimes that there's a little bit too much hype in these fields of saying, this is it, this topology, blah, 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 and waving hands. I'll let the experiments speak for themselves. You're free to ask me any questions about the experiments, and I stand behind them.
So there's hope to observe them.
Absolutely.
Hopefully.
I don't, this is not in, this is in the superconductor high spin orbit coupled semiconductors, not topological insulators. There isn't evidence there. But the real problem is the still relevant. And the size of the topological gaps that are achievable, even in principle, is not large. So this idea that you're topologically protected, well, you're only protected insofar as a gap. You have a gap. And there's no magic topology. If the gap is relatively small and is disrupted by disorder, your topological phase will be limited.
I know, I started ecological performance, so I know a little bit about this. So this is why I tell you where is the criticism. It's not you. I criticize the people that are talking about offering this as a contender for quantum computing. So I think it's nice physics to see, to do what Charlie Marcus did and many others, but to look at this as a realistic quantum computer, to do quantum computing with Majorana fermions, I think we are decades away. I think
maybe, but that's a question of energy scales. It's not an absolute statement, so it's not reasonable for you to say, oh, it can't happen. I mean, it's utility scale quantum computing in any of these systems is a long way off.
Actually, it's not it's another story.
No hype, no hype.
Okay, that's good. At least that, I think.
We acknowledge that there are significant challenges to proving utility scale quantum computing in all platforms.
I think the photonic platform is not that far. I mean, that's my opinion.
Well, I'll be waiting for your paper to come out.
No, it's not my paper. It's some people that I know well, that's all.
Okay, great. I know a guy. I know lots of guys too. I get very tired of all the hype and then proclamations made about we did this, we did that, and then you do the analysis. In fact, most of this stuff can be done classically with not much difficulty. Yes. So of course there isn't. There
is no useful quantum computer coming up now.
Yes.
Doing something that is useful, like
I know.
And this, my friend Dan Anderson may claim otherwise, but we'll hear it.
Okay.
All right. Let's thank Professor Manfred again. We're going to transition. In the meantime, well, while we get set up here, I'm just going to introduce our next speaker. Our next speaker is Professor Vlad Shalaev. Professor Shalaev is the scientific director for nanophotonics. So we're kind of pivoting toward the photonic-based systems now before our lunch break. So he's the scientific director for nanophotonics at Berkeley Nanotechnology Center and the distinguished professor of electrical and computer engineering at Purdue University. Specializes in nanophotonics, plasmonics, optical metaservices, metamaterials, and quantum photonics. Professor Shalaev has received several awards for his research, including APS Frank Isaacson Prize for Optical Effects in Solids, the Max Born Award for Optical Society of America for his pioneering contributions to the field of optical metamaterials, the Willis Lamb Award for Laser Science and Quantum Optics, IEEE Stryver Scientific Achievement Awards, and so on, as well as the UNESCO Medal for Development of Nanoscience and Nanotechnologies. Well, that is, cool. I have time to finish reading. Professor Shalaev is recognized as a highly cited researcher in physics and web science group for 6 consecutive years from 2017 to 2013, and he's also a fellow of IEEE, APS, SPIE, MRS, and Optica.
Sorry if I'm making it long for you. All right. Well, it's certainly good to be here. Oops. And thanks for the opportunity to present my results, our results. So where should stay? So that, Jesus. Okay. There are a couple things. Could you just do something? Where is the second one? No, I don't see the other one. So is it okay now? Okay, looks like it's fine, yeah. Okay, 2 things I'd like to discuss with you today. I'll still. There's a speaker right above you. Oh, that's why, I see. All right, first it's about our recent observation, extremely high, in fact, record high nonlinear responses, optical nonlinear responses, and also new phenomena which could be observed with single cycle light. And then I share with you some results on quantum photonic circuitry based on really very promising material platform based on silicon nitride, where we found a way to create these single photon emitters, which is a built-in block for quantum photonic circuitry and quantum simulators. So let's start with this idea of using electron avalanche for extremely high nonlinear response. That's based actually on a very simple fact that SPAD, single photon avalanche detector, diode, sorry, is actually a uniquely sensitive device. It measures single photons. And of course, it involves extremely nonlinear process, which is exponential increase in number of electrons. So therefore, it's kind of straightforward that we could use this idea and repurpose it to make out of this optical modulator, which is the key thing for many photonic applications, including quantum photonic applications. So that's exactly the point. It comes down to these modulators. Arguably, one could say that at least in the modern era, the most important device ever created by humans is a transistor. That's really the nowadays electronics. But we would like to have modulation faster, and people talk about all optical modulators. So basically, what you would like to have in this case to control source with some additional control beam and change its property. And typically, it is based on the fact that refractive index depends on intensity through nonlinear response. So of course there is linear one, and there is additional Kerr term, which is proportional to intensity. The problem that this N2, which is nonlinear effect proportional to chi3, is extremely small. If you look at the table of nonlinear responses and then two from the textbook by Bob Boyd, you could see that N2 is around 10 to the minus 10, which means to significantly modulate optical properties of material, you would need quite substantial intensities. And that's a problem, particularly if you have in mind quantum photonic applications when you're dealing with few or eventually single photons. And when you think of quantum, there are already some demonstrations, but they always kind of heroic efforts to do modulation with single photons. Here you could see some pioneering work in this area. And what is common for all these efforts, it's they use typically cryogenic temperatures and extremely high quality factor cavities. So which implies that the device would be slow. The higher quality factor, the slower the response. But it also operates in extremely narrow spectral range for which this cavity is designed. And yet another problem that if eventually would like to put it on a chip and make real quantum photonic circuitry, all these approaches, they're not really friendly, let's put it this way. So in the idea which proposed by my postdoc, Dr. Demid Sychov, is actually I think very simple and elegant. So it's to use this electron avalanche phenomenon. So we know how it works. You have this PN junction at reverse biased at voltage exceeding the breakdown. So that when the initial electron is induced by absorption of a single photon, it creates self-sustained avalanche of electrons. So that's the way it looks. You have this photon, you created first electron, and then you have this avalanche. In typical multiplication number, basically how many electrons you create with one single photon is quite significant. It's around 1 million. So you create 1 million electrons with one single photon. And in terms of the time characteristic, they're also quite spectacular, even for existing SPADs. So it's typically nanosecond time. I'm talking about dead time, how much time it's needed that restart your device so that it would be able to absorb next single photon. But it could be optimized and bring to the picosecond scale. So there are already some ideas, and we have yet another idea. So it clearly could be brought to picosecond time. So what we have in this case, very strong change properties caused by one single photon, which means that we could work as an optical modulator. So in other words, if I now send a probe beam, which doesn't create electrons simply because frequency is below the gap, so then you could probe this quite significant change in the optical properties of this material caused by a single photon, which acts as a control beam. So that's again the story, that single photon, which is above the gap, creates this first initial electron, then this multiplied in the this PN area. So and then you get this quite dramatic change in properties. And if you do simple calculation by using textbook formula, how actually single photon changes the refractive index, and it's truly amazing. Single photon changes refractive index at the level 10 to the minus 3. So this is like a dream that came true in terms of optical modulation. It's really, and it's fast, and it's extremely broadband. Conventional silicon-based SPAD operates between 400 nanometers and 1 micron. So the whole range is available. If you would like to go to infrared part of the spectrum, there are antimonite-based avalanche detectors. So you could also cover that spectral range. And indeed, it's CMOS compatible. Silicon is the most silicon compatible material. So it could be integrated with a chip. So here is the simple minded experiment. That's all very recent. We just started actually doing this. And so what we have here that you probe the change caused by this single photon, which we call control pump, and it is at 810 nanometers, and we probe it with light beam at telecom, which is below the gap and should not cause avalanche effect. So we use these 100 femtosecond pulses with 80 megahertz repetition rate. And the thing to point out here, that the average power of this control beam is truly minuscule. So basically it's less than 1 photon per pulse, quite less actually. And so the story is again that you have this single photons, which creates avalanche, exponential increase in number of electrons. As a result, you have a large change in refractive index. Therefore, you have very strong modulation. So it could operate in very broad spectral range, 400 nanometers to 1 micron, and it could be potentially a terahertz rate, picosecond time. So with that, we did very simple experiment, just took from a shelf SPAD, existing SPAD, not even being the best in terms of its characteristics, quite regular one. So we use this kilohertz chopper to check that indeed we see this modulation. So this is our control beam, this is an infrared probe, and the modulation provided by this chopper is 1 kilohertz. And exactly at this frequency, we see modulation in the detected signal here at an infrared detector. So, and again, the control beam is at the level less than 0.1 photon per pulse. So not even every pulse has a photon. So if you do the measurements, of course, this modulation which you check on the detector depends on the power of near-infrared beam. So when you increase the power, of course, the signal increases. But again, the number of photons per pulse is very low. So it increases, and to find out N2, you need to change, to plot the change in refractive index as a function of this control beam. And here you could see the result. And when you extract N2 here, this nonlinear coefficient, it's at the level of 70 centimeters squared per watt, so which is orders of magnitude higher than any reported nonlinear refractive index so far. And again, it's fast, so it could operate at terahertz spectral range. So to sum up this first part, we have quite significant modulation at the level of, let's say, 0.5%, which is caused by single photon intensities. So the refractive index, nonlinear refractive index, which we extracted from these measurements, are remarkably high. And again, it's not that surprising because it causes electron avalanche. So it could be brought to terahertz rate by optimizing the system, and if somebody is interested, I could discuss it further. So, but that time could be brought to picosecond time scale. And indeed, it's CMOS compatible, and it enables on-chip integration. So that's like having the optical modulator on a chip, on photonic chip. That's the hope. All right, let's move on. So there's so-called materials which have epsilon, the electric permittivity, near zero, ENZ material. And if the absorption is small, then when epsilon is close to zero, refractive index becomes close to zero. And refractive index is the very basic characteristic of how light couples to materials. So in this case, you really could open what I believe new chapter in nonlinear optics by using these epsilon near zero materials and enable something which arguably the most exciting thing in the field of photonics, so-called photonic time crystals. And we will have a separate lecture on this subject to be given by true warrior and my good friend Maurice Yair. All right, but what is special about this Hien-Z regime? So basically think of this. Epsilon is zero when polarization induced by the field completely compensated the field. So you have stationary in space situation when epsilon is zero, but it oscillates with optical frequency. And all this regime is accompanied by lots of singularities. This is kind of singular optics. Why? Because if you look at the phase velocity, which is just speed of light divided by the refractive index, when epsilon goes to zero, the phase velocity diverges, meaning that you have no retardation. Phase propagates with no change, no retardation. If you look at the group velocity, then the group velocity actually goes to zero. It means you have a slow light. Slow light means that the light has more time to couple to your matter, and therefore the coupling becomes more efficient. Yet another singularity, because the normal component of the displacement current D has to be conserved across the interface between materials with different dielectric permittivities. If in one of the materials epsilon goes to zero, the field has to diverge, become really large. So that's all indicate that these materials are indeed quite unusual and very interesting phenomena, could be expected. And we published quite a number of papers on dramatically enhanced nonlinear responses in materials, but that's not the subject of what I'd like to talk about. But the important thing that there are materials actually that do have this performance. And this is called transparent conducting oxides, which my colleague Sasha Baltasova actually developing and optimizes. So if you look at this material, such as aluminum doped zinc oxide or gallium doped zinc oxide or well-known indium tin oxide, around telecom, the real part of the electric permittivity crosses zero. That's actually where you have like phase transition. When epsilon is negative, it's metal. When epsilon is positive, it's dielectric. And losses are quite small, much less than, let's say, in gold and silver, typically used for plasmonic materials. The important thing actually that the behavior in this case is Drude-like. It's basically like free electron type of material, which is described by this formula, and it depends on the plasma frequency. And the plasma frequency in this case could be controlled optically, meaning in a very fast fashion. For example, if I do interband transition, bringing electrons from valence to conduction band, then of course the charge carrier density increases and the plasma frequency moves to the blue. However, if I do intra-band excitations, because of non-probability of the band, actually you have increase of mass. And when mass is increased, the plasma frequency moves to the red. So you could really control the plasma frequency. And the thing to appreciate here, since n is square root of epsilon, if you would like to find the change of the refractive index induced by light, you take derivative n over the epsilon and multiply by the delta epsilon. But derivative of square root of epsilon gives you square root of epsilon the denominator, which means when epsilon close to zero, the change in refractive index is enhanced. It's extremely sensitive. Any change in charge carrier density results in quite significant change in refractive index. So, and we first demonstrated that these materials based on transparent conducting oxides have truly remarkable properties by simply looking at change in reflection and transmittance caused by short pulse. And we see changes not at the scale of, let's say, the hundreds of percent, which is typical and already good for conventional materials. We have a change here, like at the level of 100%, and it's extremely fast at the scale of 100 femtosecond. So more recent result, like if you look at conventional zinc oxide, so the change caused by light is truly remarkable here. Look, what I simply change here, the fluence, the intensity of pump, which induces this change in dielectric permittivity. And the point of crossing through zero, where you have all these unusual properties, varies between 1.6 to 8 micron. If I stay this particular wavelength, the magnitude of epsilon changes between 0 to 4. Again, I want to emphasize we are so much away from any perturbative regime. It's really a dramatic change. And why it's so exciting? For many things, but photonic time crystals, I believe one of the perhaps most spectacular development in optics, which hopefully would happen soon. Let me provide some introduction first. So this idea of time crystals, like analog of spatial crystals, was proposed by Frank Wilczek in 2013, and he basically described it as a new matter of state for a very good reason. Interesting that Peter Holloway, who actually was graduate of Technion and spent his career in Mexico, theoretically predicted photonic time crystals as early as in 2009. And all this crystal-like structure, the beauty of this is actually the existence of a band gap. Conventional photonic crystals, suggested by Eli Blanovich, when you have periodical modulation in optical properties with the period matching the wavelengths, has a band gap in the frequency domain. And because of that, you have unique control over spontaneous emission, all these beautiful properties. What if now I have periodical modulation of my optical properties in time domain with the period matching the cycle? Of course, it's very challenging to do, but you could expect right away that you also would get a band gap, but in this case, in the momentum space. This is because of space-time duality in Maxwell's equation. Now the band gap would be in the momentum space. One could say, hey, and so what's the difference? It's actually a fundamental difference, because in the conventional crystals, you have this band gap in frequency because of this multiple reflection and refraction in different interfaces. And when you look at the reflection and refraction at interface in space, the frequency is conserved, but the momentum is not. But frequency is conserved. When you do the same when you abruptly change properties in the time domain, actually the momentum is conserved, but frequency is not. And that makes a big difference, because if you're dealing with a band gap, you cannot have propagating modes. You should have exponential modes. And in the case of frequency, conventional photonic crystals, it means exponential decay, because energy could not change, because frequency is conserved. But in the momentum, in the case of momentum band gap, you could have exponentially increasing solution, because in this case, energy does not have to be consumed. It's drawn from this periodical modulation, Flaquet modulation. And based on this, the Segev group actually predicted truly remarkable phenomena, such as amplified spontaneous emission and absolutely new type of regime, which lasing, which is relying not on the conventional resonance structure and population inversion, but rather it depends on the properties of the band gap. So clearly it's very interesting, but can you realize it? You have to modulate it periodically with the period matching the cycle. Could you significantly change refractive index as required within such period of time, short period of time, and bring it back? Because matter usually responds, let's say, through electron phonon relaxation, so it's like 100 femtosecond. You have to do it at a scale of few femtosecond to match the cycle. And here the experiments done at Technion, and we collaborated on this, provided our materials. Specifically, they use this transparent conducting oxide that developed by Sasha. So in this case, the probe was at 1225, which corresponds to this E and Z point, where you have all these remarkable properties. And for this wavelength, you actually have if you go to the pulse duration 6 femtosecond, it would match the cycle, the duration for the pump at 800 nanometers. So it's like single cycle. And the beauty of this experiment that indeed a very strong change in refractive index has been observed. And what you expect in this case, if refractive index increases, because momentum is conserved, you have to have redshift. And when it decreases, you have to have blue shift. And indeed, that type of change was observed. And the time scale on which it was happening, it's close to the cycle. It's far shorter than, let's say, electron phonon relaxation. So yes, light just increases refractive then and brings it back. So looks like we're now ready to do experiment, like creating really photonic time crystal. Next step would be just to do it periodically. But at least it's a good development, and we hope to get exciting results on this soon. So let me sum up first part. So we introduced these very strong nonlinear responses, which could be used for optical modulation. And then we also use this ENZ material to show quite significant change at the scale of one single cycle, which seem to show that photonic time crystals should be possible to demonstrate. So let's move to the second part, and that's based on the single photon emitters. In general, as was part of this short discussion, I also believe that, yes, photonics-based quantum simulation might be not perfect, but it might be easier to realize. It's so-called measurement-based quantum photonic simulation. So, because in this case, you don't really need gating. The single photon coincidence measurements plays the role of gating. And importantly, error rate is by far less than in other materials, because photons are very robust. So the problem is to find a good material platform. And everybody knows that two best material platforms for photonics, conventional classical photonics, is silicon and silicon nitride. It turns out that silicon nitride is even better. Therefore, companies like PsiQuantum or Xanadu is actually switching from silicon to silicon nitride. Why it's better? Because losses. Losses are really remarkably small in these structures. They go down to 0.1 dB per meter. It's really, really good. And there is a high refractive index, meaning that there is good, strong contrast, and you could enable strong confinement. They are transparent in very broad spectral range and have a relatively high Chi3. That also could be useful. The problem is silicon nitride. It's known to have very strong fluorescence background. So there is no way to see these single photons, even they would be there. So you need somehow to suppress that background. And that was accomplished in our group by these two remarkable young men, Alex Sinichev and Sam Pina. So what they did, they just used nitrogen-enriched silicon nitride. And remarkably, the background actually decreased by orders of magnitude. It goes away. And specifically, they use so-called high-density plasma, CVD, and get this nitrogen-enriched silicon nitride. So that's first thing, to get rid of the background. How to get these single photon emitters? The next trick they played is actually to use this rapid thermal annealing. Silicon nitride was sitting on top of a substrate which is silica. So what we believe is happening in this case, although this work is still in progress, when you do this rapid annealing, because thermal expansion coefficient for silicon nitride and silica are different, you create strain at the interface between silicon nitride and silica. And that strain causes these defects. And anyway, after doing this procedure, you start to see this many very bright single photon emitters. So, and that's all at room temperature. And the properties are actually quite remarkable. If you look at the purity of these single photon emitters, this G2, which is characterizes autocorrelation function, at room temperature goes really low, which is quite impressive. So all this emission kind of around these four lines. So when you move from one defect to another, you get this emission at the same wavelengths. And the counts is quite impressive. It's 10 billion counts per second at room temperature, actually. The brightest emitters reported at room temperature, to the best of my knowledge. So to understand the nature of these emitters, we did this low temperature measurement, looked at the zero photon line, and then in collaboration with this group from Technical University of Denmark, we did this DFT simulation, first principle, and it looks like all these features are well reflected in simulation if you assume, but that because of the strain which you create, one of the nitrogen atoms is replaced by oxygen. And remember, it's all happening at the interface between silicon nitride and silicon. And one of the silicon atoms replaced by nitrogen. So you have this type of complex. And that seems to have exactly the structure what we see. So the next step, you would like to integrate it with the waveguide. That's what we did. Here you could see silicon nitride-based waveguide, 2 gratings, one to couple light in, another one is to couple light out. And that's what we did, and obtain this good G2, meaning that you preserve these properties of single photon when you couple it to a motor waveguide. Well, the thinking now is how to create them deterministically, because you ideally would like to have like thousands of them and put it on a chip. And this wonderful idea that Sam suggested is actually to make these pillars of silicon nitride of a particular diameter. And of course, strain depends on the diameter. So by controlling the size of the diameter, you control the strain. You place them on silica substrate. You do this rapid annealing. And then you look at the properties and you see these very bright emitters. Like each pillar produces an emitter. When you arbitrarily choose these 55 pillars, 100% of them showing anti-bunching, and 67% show actually G2 below 0.5, indicating they're single photon emitters. So LUX clearly looks very promising, and because now we could do it deterministically. And if you look now at this trade-off, which you typically have when it comes down to creating big circuitries with single photon emitters. So this, you plot here large-scale integration ability against the yield. Of course, you could have very high yield if, for example, you pick and place pre-selected emitters. But scalability would be really a big issue because you cannot do it one by one. It would take forever. So in terms of large-scale integration, you could do this drop casting random emitters. That would be large-scale, but you shouldn't expect in this case high yield. So in our case, we're already here. So it's kind of going beyond what people observed so far. And we are pretty sure that we will increase the yield quite significantly because we just started to do this work on optimization of yield. So therefore, that's how we envision it's to happen eventually. Like you have this waveguide, you place this pillar, and the coupling of the pillar to the waveguide could be optimized through this inverse design approach. So that's actually inverse design structure done by Omer. And in this case, coupling could be quite strong. So yet another thing which I think important to realize and make it working is to use plasmonic speedup. Why? Because for quantum photonic simulators and for quantum photonics-based quantum computing, you need indistinguishable photons. With these distinguishable photons, there are protocols, you could create cluster states, and you could do all these type of calculations. But typical time of emission of single photon, given by the Einstein coefficient in nanosecond scale. Typical decoherence time is picosecond. So it means that you would get single photons, but they would be randomized. If somehow you would emit photons faster before decoherence happens, then they would be immune to decoherence. And here is the idea which we came up with a while ago with my former postdoc, Semyon Bogdanov. So to speed up the rate with which photons emitted by using Purcell enhancement. So Purcell factor is known as the way to increase coupling of light to matter. Typical size of the wavelength is 1 micron. Typical size of your qubit is 1 emitter. So there is huge mismatch in size. Therefore, coupling is not official. And as Purcell, who, by the way, was a graduate of Purdue electrical engineering, so suggested this simple idea to place your qubit or your atom inside of a cavity, so that when light bounces between mirrors, it would effectively couple stronger to your atom. And the enhancement is proportional to the quality factor, obviously, and inversely proportional to the volume where electromagnetic mode is localized. There are 2 ways to accomplish one. One is just use the electric cavities with very high Q. And it would work, your light matter coupling would increase, but in this case, the speed would be very slow. Because the higher the quality factor, the slower the response again. And it's not what we actually want. But we could accomplish the same by using plasmonic structure. In this case, Q is modest, 100, meaning that the rate would be terahertz, very fast. That's what we want. Broad bandwidth, that's what we really want. But volume could be much smaller than diffraction limited, like in this case. So it could be 1/100th of the wavelength, let's say 5 nanometers. So you have to raise it to the power 3. And you would immediately see just because of confinement enabled by plasmonics, you would get enhancement at the level of 1 million and times the quality factor. But in this case, you have the speed. The system operates at terahertz rate and could beat the rate of coherence. So that slide further illustrates this idea. So normally to deal with this problem decoherence, of course, we go to extremely low pressures, trap atoms, ions, and of course, indeed, it's beautiful, it works. But as a complementary approach, we could simply speed up the process with which we're after. So like in this case, emission of single photons. If photon is emitted before decoherence happens, then it's immune to decoherence. So that's a first experiment we did to just illustrate this idea. In this case, it was just conventional nitrogen vacancy nanodiamond. We use it as quantum emitter, place it between this single crystal cube, silver cube, and epitaxial silver. So the smaller the gap, the stronger enhancement. But the size of the cube shouldn't be too small because you want to outcouple photons very fast. And what we obtain is actually the reduction in lifetime by 3,500 times, quite significant. Remember that the difference in lifetime or rate of emission photons and decoherence is roughly 3-4 orders of magnitude. So we're already close to that. So and as calculations show that if you optimize this system, the efficiency could be 96%, and the rate with which that these photons are emitted could go as high as 300 terahertz. All right, here is kind of the vision, what we would like to accomplish in the end. This is silicon nitride-based single photon emitters, which we now can place deterministically on a chip. Then a bunch of this switchable Mach-Zehnder interferometer, all these things which required for so-called measurement-based quantum simulations. And most probably we will still need to use this antenna, plasmonic antenna, to speed up the rate with which photons emitted and to ensure that they are indistinguishable. All right, this summary for this second part. So we now have this quite efficient single photon emitters, which is opposed to what PsiQuantum or Xanadu do, and they use this parametric spontaneous down conversion, which is a probabilistic process, not deterministic, but probabilistic. Dramatically increases the infrastructure. In this case, we could have deterministic single photon sources. And plasmonics could be important because it could make process faster and beat the decoherence rate. So here is the group who actually did the work, and let me just end up with this slide reminding to what we covered today. Thank you for your attention. Where is my chair? Oh.
Any questions from the audience? Can you? Someone started to ask a question, I think. Is there any questions from the audience? There was one question. Oh. Wait, who had a question? Oh, Mike.
Simple, naive question. When you were showing the distribution of energies for the silicon nitride single emitters, that there were 4 primary peaks, but there was a distribution around each wavelength, and so I was just quite wondering how should I interpret that? That it's not an atomic transition; it has width to it.
Well, the truth is we don't know yet, Mike. So we just show that most probably this is caused by strain, but the precise nature of these single photon emitters and why they are grouped around these 4 lines, we don't know yet. But in terms of like making them narrowly spectral, we could do spectral filtering, which we have not applied yet. If you would like to have one particular wavelength, that's what other groups do. So you do the spectral filtering, and it's much easier to do the rest of the work.
Thanks.
Yeah, I'm a student from University of Michigan. I have been using SPATs for normal TRPL measurements. So during those measurements, I came across these trapped electrons that recombine at a later stage, leading to a later on emission. I mean like avalanche effect, and you get a signal. So will that affect the optical modulators that you proposed in the beginning?
Yes, in terms of speed. Not in terms of magnitude, but in terms of speed. So what you're talking about, the dead time. Basically, how much time you need to restart your system so that it will be able to absorb next single photon. And typically, if you do nothing, if you take it spat from a shelf, it will be nanosecond, which is already fast, gigahertz. But there are several ways how to make it faster. One of them, the area of multiplication is quite big, it's microns. So what we could do for our purposes, all optical modulation, we could use much smaller spot, which is diffraction limited. And in this case, the time would be limited by the time you needed to go through this focused probe beam, which could be very small. And the drift velocity is 10 to the 7 centimeters per second. If you take really tiny, let's say, diffraction limited spot, which is, let's say, 200, 300 nanometers, you would end up with 3 picosecond time. That's how much time it takes to go through this spot. And that would define, in this case, the response time. And 3 picosecond, it's already 0.3 terahertz. So yes, what you're talking about, like electrons sitting there, don't coming back so that you could not restart the system, that's called the dead time. And typically it's a nanosecond, but if you look, for example, even at Wiki, there are already some demonstration make it much faster, like 100 gigahertz. And for that case, it's designed to detect single photons. For our purpose, we need to do modulation, and therefore we could dramatically reduce the area of interest, which would be defined by the laser spot, which could be much smaller, very small. And so the time which takes to go through this, that would be defined in that time, and it would be much shorter.
What I meant is, say, once you excite all the electrons, some electrons get trapped inside the band and then get released on a later.
There is some special ways, which is called active approaches. You basically apply voltage and you make them to come back. That's existing techniques. They do use already thin spats to avoid exactly what you're talking about. Instead of this passive control, they use active control.
Oh.
Thanks, Vlad. So you spoke about the changes in the real part of the refractive index. What happens to the imaginary part? Because for single photon application, that might be also very important.
That's truly deep question. Because things which I put aside, like I said that it might be very good for quantum, but in quantum, the key thing is coherence. So would this preserve coherence? It's a big question. And that's exactly related to what you just said. So we look at the nonlinear pattern change in refractive index, real one, but how about the imaginary one? That's what would be responsible for basically decoherence process, still to be measured. We don't know answer to this question, but that's a very important question.
Hi, Vlad. On your single photon emitters, so how much, I might have missed, but how much power can you actually get out of each of them? I mean, what's the spectral range that you can go?
Okay, so it operates in the visible, and one could say, hey, it's not telecom. But I would argue, I actually think that this is a good way to do everything in the visible on a chip, all the functionality switching, and convert it to 1.5 and send to the external world through the fiber. But in terms of the brightness, in terms of how much, it's actually, as I pointed out, it's 10 million photons per second at room temperature, 10 million. So, and if I apply plasmonic antennas, we hope to increase it by 3-4 orders of magnitude. So then the rate would be so high that it would outpace decoherence. Not only you would get increase in number of these single photons because it emits much faster, but also you would potentially, hopefully, beat the decoherence and they would be immune to decoherence. That's the game in the town.
In the line width, can you remind me also, like
how pumping light is just conventional. I mean, conventional light source like diode source could do it. It's lane width. Lane width, it's broad. And that's related to what Mike pointed out. It's actually quite broad. So, and if you would like, probably to create there are existing product also, as I pointed out, if you have indistinguishable photons, how to create this cluster states and so on. For that, we most probably would need to do the spectral filtering. Then it would depend on the filter. So we have it in a relatively broad spectral range. So, but eventually, depending on what we want, we would filter it out. But actually, having this possibility going from one wavelength to another, it also might be attractive and actually could be advantageous.
All right, let's conclude there. Let's thank Professor Shalaev again. We have about 45 minutes for lunch. They're ready in the back for you. If you're students or postdoc presenting a poster this afternoon, please use the time to go down to the hallway to put it up.
Yes. It's already on. I'll turn it up there in just a second.
So, test. So, all right. Welcome back, everyone, to the afternoon session of the Quantum Summer School. We will be starting this session by a talk from Professor Dana Anderson on a lesson on electronic sensing and signal processing. It's my great pleasure to introduce Professor Dana Anderson, who is a professor in the Department of Physics and Electrical and Computer Engineering at the University of Colorado. He is a co-founder and former CEO of Colt Quanta, later renamed to be Inflection, and he serves as the Chief Strategy Officer of the company. As a JIL LA Fellow, Professor Anderson's research interests span a spectrum of topics, including atom-based precision sensors, atomtronics, RF sensing with Rydberg atoms, quantum signal processing, and machine learning in optical and atomic systems. So please welcome Professor Dana Anderson.
Thank you. Let me say it's a pleasure to come here. I think this is my third summer school, something like that, approximately. And I'm really enjoy having an opportunity to speak to students, especially students oriented in one way or another towards quantum. This picture, by the way, is meant to articulate Schrodinger's cat all grown up. We're trying to get power out of Schrodinger equation. That's what a lot of what we are doing attempts to achieve. So, so this is going to be, at the very beginning, a little bit of an advertisement for what you will hear on the next talk. It's about Octant. Octant is a quantum matter machine currently put on the cloud by Inflection, and we're very proud to be acknowledged by Time Magazine's Best Invention of 2022. And Octant exists in part thanks to QSC, where we have an interaction to make Octant useful to the public. If you were to come into Boulder, Colorado, into the company site and ask to see this machine, it looks approximately like this. And another word for it is it's a souped up Bose-Einstein condensation machine. Another term for it, it is a souped up version of what is currently today flying on the International Space Station and has been since 2018. So this is real and real deployed quantum. And the goal is to make this quantum technology based on cold atoms available to anybody. So you'll hear from Noah Fitch in the talk after mine about logging onto this system and utilizing it. But I'm going to motivate the sensing and atomtronics portion of my talk based on this machine. So on this machine, you, and I mean you, can generate atoms that are about 100 nanokelvin and take their snapshot. So this is a picture, time of flight picture, it's called, of atoms at about that temperature. You can also take what we call in-trap images. So here's a cloud of atom, presumably about that same temperature, taken directly as an in-trap image as opposed to the time of flight image over here. So very cold atoms, basically in a pure quantum state, and we can paint potentials onto these atoms and control where they sit. So for example, here's an in-trap image of a cold cloud of atoms, and we use laser beams to change the potential in which they sit in real time. And so what you see here is the atoms are sort of squished up in the upper part of this picture by a laser beam that is shaped like a knife, so it goes across this region, and it's pushed up in time so that, and then stopped so that all the atoms are now confined to a smaller region. We can slice atoms, a cloud of atoms. So here's a picture of ultra cold atoms with a barrier separating them into two. And we can do it in the other direction as well. So again, atoms that are separated in two clouds with optical barriers, and the height and position of those barriers you can change in time. We first released this machine to the public at the Quantum to Business Conference, Q2B, in December. And very shortly after we made it public, here is an experiment carried out by Dr. Kerry Widener, who's currently at the University of Bristol, showing interference between two clouds of atoms. Now, this was first done in the 90s by Wolfgang Ketterle's group at MIT, and was quite an arduous thing to do at the time, but now you can do it. Kerry had it running about an hour or two after we publicly released machine. So here's a cloud of atoms. These are time of flight diagrams. So when you're looking here versus looking here, this is at a later time. You just can't tell. The atoms are falling. Here they're captured in the center of the picture. Here they're further down, but still captured in the center of the frame. And what you see is a set of interference of fringes appearing as the atoms are falling. And to me, this is still remarkable. You have two clouds of atoms. Think of them as ping pong balls. They overlap, and you get bright and dark regions in the atoms. So these are among the experiments you can do with this machine. Again, I was proud to make this available to the public. And again, thanks to our work at with the QSC for making this happen. And then one can work with open quantum atomic systems. What does open mean? Well, most of what we talk about in quantum mechanics, we have a potential, we have atoms or whatever our particles are, and all the forces are conservative. And the fact that the forces are conservative means energy is conserved. In an open quantum system, in this case, it's done by effectively connecting the atoms to the vacuum. And we do this by shining on a part of the potential a laser beam that is tuned to atomic resonance. So if atoms move from left to right and run into this, we call it the terminator beam, they go away. And this effectively couples the atoms, as I say, into the vacuum. That makes an open quantum system. And that makes things very interesting from an information processing point of view, very much like the difference between optics and quantum optics. And in quantum optics is often concerned with hooking systems to the vacuum. So this system enables experiments, sorry about that, in tunneling, in noise, in non-equilibrium quantum systems, in driven quantum systems, and so on. Also, by the way, is available a Gross-Pedievsky equation simulator. So you can first simulate on a classical computer what Octant can do experimentally to see what you should expect. You can run the simulator and then you flip a switch and it puts the same program onto the hardware. And it's done through Python or a web app. So altogether, we can carve potentials for atoms. We can introduce barriers. We can have terminators. And I want to tell you about my favorite system because we're going to slide now from the sort of octet-centric to the portion about signal processing and the kinds of things I like to think about these days. So this is a picture of the z-axis in the pictures that I showed in TRAP. That would be up and down. This is the z-axis and this is potential energy. So we are carving a potential that looks like this. It's roughly parabolic, and then it has two barriers. In between the two barriers is again essentially parabolic. And atoms can tunnel from, if they're collected in what we call a source region, across what we call a gate region into a drain region. So this is where the terminator is. This is vacuum. This gate is harmonically shaped. And as I said, the atoms can in principle tunnel from one barrier, across the next barrier, and get out to the vacuum. So this is a very interesting system because, why? Because this is what I'm interested in doing. I'm interested in seeing how to get what I'm so very familiar with, what you are so very familiar with in optics, instead in an atom framework. So up till now, if you're a student and you've read about all the experiments, say in atom interferometry, so we're now talking about sensing. And one of the most significant historical quantum sensors in our business is an atom interferometer, say for measuring acceleration, rotation, making inertial measurements, and possibly making other kinds of measurements. But until today, there are no resonant frequency interferometers, resonant interferometers in matter waves like there are in optics. So in optics, we use so often, we put two mirrors that face each other, for example, and we build up optical power, or we build up sensitivity by having those two mirrors of high reflectivity. That's a resonator, and we tune some incoming laser at the resonant frequency, and it has enormous value for so many reasons, and in matter waves, we don't have that. And that's because in matter waves, we don't have a coherent matter wave source. And by coherent, I often use a capital C, meaning Glauber coherence. And if you don't know what Glauber coherence is, it just means the same kind of coherence I get in a laser, but now with, instead of light waves, I mean with matter waves. If I did have such a source of coherent matter waves, then, and I can combine it with a resonator, I can do some very powerful things. So for example, I'm so far making an imaginary matter wave coherent oscillator. And it emits a matter wave, and I have these blue things that are optical. You'd say, well, those look like mirrors. Actually, mirrors are very easy to do in our business. So these can be just bluely tuned laser beams, just like I showed you sweeping across the atoms. And they form barriers. And by adjusting their height, I effectively adjust their reflectivity. And so I can make a resonator using these barriers that I described before with octant. And also by choosing the height correctly, I can make, for example, a beam splitter. And these things are conceptually straightforward. So I can set the reflectivities just by choosing barrier heights and so on. And so far, this device is a bit imaginary. This is an atom detector and there's feedback, but this looks exactly like a scheme I use to lock lasers to cavities for clocks, for gravity wave detectors, or what have you. All right, so the first step in any signal processing essentially is generating the signal in the first place. So far conceptually, I have this thing I call a matter wave oscillator that generates the signal, and then I can use it in a resonator. And to give an example of what I might use it for, here's gravity conveniently pointing down. And suppose I have two of these systems, two matter wave generators, two cavities, resonators, detectors, etc. One is aligned gravity and one is perpendicular to it. Then, because atoms going up to this resonator have to work against gravity before they come back down, the effective length of this cavity is actually longer than this one. And that means that its frequency that it'll resonate at is different. And that's very easy to work that out. The frequency shift of this resonator to that one is given by some scale factor, kappa alpha, times the acceleration due to gravity. It's very easy, very straightforward to say what the scale factor is. And if you ask about a measurement of G in the uncertainty, the key here that really counts is that there's this factor F. All this is, the rest of this is a little bit boring. It's kind of as you would see in any measurement of G done with an atom interferometer, for example. But there's this factor F. And in optics, we call that the finesse. And here it's about the same thing. So it's effectively the number of times that an atom wave would bounce back and forth between these resonator mirrors. And that means that I can enhance the measurement of G by this finesse just by choosing the reflectivity of these barrier-based beam splitters. All right, so this is a very powerful concept. In all of atom interferometry, all the sensors, they're all essentially single pass, with one or two exceptions. But none of them are based on resonance or finesse. So if I can do this, it's really interesting because I can enhance the sensitivity of matter wave interferometers dramatically. So we're in teaching mode at the moment, all right? Rather than, I'm not telling you about latest work or something like that. This is what I would really like you to go away with, is the original lesson in coherence, and then apply that to matter waves. And through that, we're going to create something new that you don't know about from something that you do know about. So what did we learn from James Clerk Maxwell? I hope you learned something. I mean, you either read Jackson or Griffiths or something. And what we learned from James Clerk is that if we have a current shown here, and if that current is time dependent, and particularly if it's oscillating in time, it'll generate away from that current electric and magnetic fields. We know that the radiated field from an oscillating current, for example, propagates at speed c, and it propagates in vacuum with an impedance. And the physics side of the house may not be that accustomed to talking about impedance as being so fundamental. I hope the electrical engineering side of the house, it's meat and potatoes. So these are the two dynamical quantities that count. And in particular, if I have an antenna with the current moving up and down, it'll radiate a field, again, that propagates at the speed of light and experiences the impedance of free space, 377 ohms. And the interesting thing is that an oscillating current will give rise to a radiated field that is both classically and quantum mechanically coherent. All right, so a classical oscillating current generates a pure state of the quantum mechanical field, namely the coherent state, a la Glauber. Okay, that's something you already know. That's nothing new. So I have a quiz. I wasn't expecting a quiz. All right. Consider instead of electrical current, a time-dependent current of neutral atoms, such as rubidium, meant to be shown here as in red. Is there a set of fields associated with that current, which I might call F and G rather than what I call it E and B? Well, here's a hint. Electrons repel each other. And in the case of rubidium atoms, cold rubidium atoms, they also repel each other. All right, there's an interaction. Electrons repel each other through Coulomb interactions. They exchange photons. Ultra-cold rubidium atoms repel each other through van der Waals interactions. Exchange of what? We know that ultimately the source of the interaction is electromagnetic, right? So as we talk about exchange of what, I want to take care of that to say that we're not actually going to invent anything new here. Rather, we're just going to take what we know and apply old stuff and come up with things that we didn't know, but nothing new in terms of physics. And to do that, we employ classical gauge field theory. So by classical in this case, I mean no relativity and no quantum mechanics at first, all right? So when I started going down this path of applying gauge field theory, I discovered it's very, very hard to find classical gauge field theory in any textbook. Almost all modern treatments use relativity early on the derivation. Now, here's the thing. Well, I'll explain why field theory is relevant in a moment. But here is one of the revelations that took place in about the 80s. You've probably heard of the standard model of physics, standard particle model, quarks and gluons and things like that. Well, more or less that same field theory which gives rise to that, it showed that you can also derive Maxwell's equations. And that's a bit of surprise because you and I were taught Maxwell's equations came together because first, on one hand, we knew about electrostatics, electromagnetics, changing flux then, et cetera, et cetera. But in fact, you can derive Maxwell's equations directly from field theory. And so, as I said, most modern treatment of field theory bring in relativity very early on. So if you want to learn about what I'm talking about, there's a very nice set of notes from Nicholas Wheeler of Reed College, same college David Griffiths came through. How many used Griffiths texts? Anybody? Oh, come on, be proud. All right, thank you. A small handful. Same college, older guy than Dave Griffiths. And I don't even know that he's around anymore, but his notes are still available. And he does bare bones of the classical theory of gauge fields. And these are a lovely series of notes revealing a family of Maxwell's equations that results by applying gauge theory to electromagnetics. All right, I'm not going to go through it, but I'm going to tell you what the steps are. And the steps are, is this any new problem in physics is write down either the Hamiltonian, or if you want to take a step back from there, Lagrangian, L equals T minus V, to remind you. And this looks a little bit familiar or not. You instead, in our case, write down Lagrangian density. And we think of a stream of particles. They could be charged particles, but they also might be rubidium atoms. And this R describes particle density. This S is Hamilton's principal function. And I said, since this isn't really a deep lecture, I'm going to suggest you might want to go back and if you're interested to learn what that is. But it's typically seen in this approach to solving the dynamics of a system described by Lagrangian. And then you identify global gauge invariance. That's just a statement of, I don't care where I measure the energy zero from. If I drop a ball from here and call this zero energy and allow it to fall, I know when it gets to the ground, it is mgh worth of energy by the end of time it gets to the ground, where h is the height. Or I could call this plus, 10 joules if I want up here, and measure everything relative to that, and then this will be minus some number mgh, right? So that's what global gauge invariance is. Then we introduce gauge fields that you call the vector potential and the scalar potential, and we say, how do these particles interact? Do they interact like through the Coulomb force? Do they interact through something else? But we add interaction terms, and then we know the field itself must involve energy. And then use Hamilton-Jacobi equations to find all the fields and conditions and so on. For me, gauge field theory was, I'm an experimentalist, so gauge field theory was, had a big potential barrier for me to get over. The way I think about it is you could do gauge field theory of superballs as well as atoms or what have you. And this is the way I think about it, forgive me, real theorists. Imagine I have a bunch of rubber superballs or bouncy balls or whatever you call them, rubber balls. They're lined up here, and the left-hand side of this wall is vibrating at some frequency nu. And because of the interaction between the balls, because they're rubbery, some of them manage to roll off down the slope, and they go along and they go back up. All the while, in some sense, they remember that earlier they were vibrating with frequency nu, so that some of these balls arrive slightly late, some of them slightly early, if you like, all because the fact that back here in history, they knew about the frequency nu. And if they're van der Waals forces or rubber balls that have to be touching in order to vibrate, they're certainly not interacting here because they're far apart. Nevertheless, they know, so to speak, that they were vibrated earlier. And so you can think of gauge field theory in some ways as merely bookkeeping, but bookkeeping that has physical significance, as we will see. So you could do the gauge field theory of any system of identical particles that go interactions. All right, and if you want to read about it, this was work done by my colleague Kasia at Los Alamos Lab, again, thanks to the QSC. We put this paper together, a gauge field theory of coherent matter waves, and it applies exactly what I said. And here's the way also to picture it, is that there's classical gauge field theory. Here it is, the Lagrangian density. And if you apply relativity, you come up with Maxwell's equations. On the other hand, if you don't apply relativity, but you apply a little bit of quantum mechanics to get some right answers, you get something that are identical to Maxwell's equations. And in the case of Maxwell's equations, we have electrons. In the case of atoms, we have van der Waals forces. The gauge field, well, we call these electromagnetic waves, and here we're going to call them matter waves for lack of a better term. And we know that what characterizes the dynamics of electromagnetics is basically only two things. I'm ignoring polarization, etc. But in terms of the dynamical variables, it's the velocity, which is the speed of light, and the impedance. And the difference is, on the right-hand side, it is not the sort of a constant velocity, it's a particle group velocity that replaces the speed of light. And it turns out what replaces the impedance of free space is h bar. And in the right system of units, if, h bar is impedance particle, coincidentally. So we call that the quantum impedance, which is why I needed to bring in h bar. Quantum mechanics is finally, that's how you discover what the impedance of free space is for matter waves. So we can go, for example, in electronics, we go from the current density into just a current. It's a little easier to think about sometimes. And then we think about flux and power carried by a current. We talk about the current as being an amplitude. The power is quadratic in the amplitude. And again, instead of bringing in relativity in the speed of light c, we incorporate quantum mechanics, where we get the group velocity takes the place of the speed of light. These are just what these variables actually look like, and the quantum impedance. Depending on your unit system, it's either h bar over the mass squared of the particle squared, or if you're just measuring impedance per particle, that's just h bar. And then you can define, once you define a current, you can also define voltage. So think of this as current and voltage. You're all familiar with that in electronics. You can also do it in rubidium atoms, for example. And there are a number of non-trivial changes that occur. One is, and maybe most stunning in some ways, is the speed limit is not a maximum, it's rather a minimum. As it turns out, it's also dispersive. The speed limit depends on the frequency that is being carried by the field. And I think I'll skip about why it's a minimum. But in particular, there are no source-free fields. You know, we can have electrons wiggling. It'll generate an electromagnetic field, photons if you like. And if I go far enough away, I don't even know really that there's an electron wiggling somewhere. A photon has a life of its own because it's radiated. Here, there are no equivalently radiated free fields. However, you can define an index of refraction, but whereas in optics, index of refraction is typically near or above unity, here the refractive index is less than unity, and typically a lot less for most problems. And then there are a number of other differences, unintuitive differences in the matter wave field theory. And one of them is that the impedance, again, for especially electrical engineers, is negative. And that's kind of weird because it means the power carried in the field is negative. And this is, again, mostly for the electrical engineers and physicists to enjoy, but electrical engineers to especially appreciate, is if I have an electronic circuit with a source, and there's a source resistance and that drives a load, you know, for example, you have a flashlight, you turn on, it gets, these days with the high intensity LEDs, the flashlight gets hot because the battery has an internal resistance. And likewise, if you're driving a load, the load resistance will also heat up. But here, oddly enough, if you have a battery, and what's a battery? A battery in our business is a BEC. It supplies positive chemical potential, much as your AA battery applies positive electric potential. And if you have a current that's flowing out, and this current is an oscillating current, it'll actually cause the battery to cool. And likewise, if you're driving a load, it'll also cause the load to cool. This isn't actually net cooling, it's only cooling due to the field. There are particles also going and losing energy here, and you have the particles have positive energy. So always there's a net positive energy, but just in terms of the field itself, it causes things to get cold. All right, so we're calling these things Maxwell matter waves because they're coherent matter waves, not like de Broglie waves, but temporal coherent matter waves that are derived from a dual to Maxwell's equations that we know and love from electromagnetics. All right? Everything that you know in electronics, like Ohm's law, they all have counterparts in this business. There's a characteristic impedance for a transmission line. There's a characteristic impedance of vacuum, and it's frequency dependent, but nevertheless, for any given frequency, I can think of a lot in the same way as that I do with electromagnetics, except again, that is negative. So we can work out classic problems that we're used to working out from quantum mechanics. or optics for that matter, we can do reflection off of a barrier. So here's a barrier. If here I have potential energy 0 and then I have a jump, I can ask if I have an incoming matter wave, or if I have an incoming de Broglie wave for that matter, how much is transmitted, how much is reflected. If I do that, I get an answer that's a symbolic answer that's familiar in electromagnetics, it's familiar in quantum mechanics, in de Broglie waves and so on, where the reflectivity is given by the differences of impedance across the barrier divided by the sum, for example. And in the case of where my index of refraction in the matter wave case is small, much less than 1, for example, then it turns out that the reflection of a de Broglie wave, the thing that I'm used to calling a matter wave, and the reflection of a matter wave that we've just learned about, Maxwell matter wave, is identical. So I don't get a different answer between these Maxwell matter waves and the de Broglie waves that I'm used to, as long as the index is fairly different than unity. If I make a Mach-Zehnder interferometer, so I take an input beam and I divide it in 2, and I have a delay in one arm, and I have a detector 1 and a detector 2. If these two arms are identical, let's say detector 1 receives pure darkness and detector 2 is bright. Then I can change the delay and ask, what delta L do I need to change detector 1 from being dark to detector 1 to being bright, and vice versa. In the case of Maxwell matter waves, the wave vector, which tells me about the distance between interference fringes, is proportional to the index of refraction times sort of basic index of refraction, where the de Broglie waves, k vector, is divided by this effective index of refraction. And so interference fringes have much different spacing between these two kinds of waves, with the Maxwell matter waves having a long spacing and the de Broglie wave having a small spacing, for example. So I get different answers. These are truly different, therefore measurable, and therefore we can verify or not the theory. I can work out the states of a particle in a square weld potential, or an infinite weld potential, for example. And you might be familiar that the quantum mechanical states are discrete and grow as n squared. So it starts out with n equals 1, n equals 2, n equals 3 is the separation goes as 2 squared and 3 squared and so on, times a fundamental number that describes basically the size of this box and the mass of the particle that you're containing. On the other hand, you solve this same problem for Maxwell matter waves, you find that there's a continuum of modes that can be in the fundamental state, and a continuum that's in this second state, and a continuum for the third state, and so on. But there's a minimum energy for the fundamental mode, but it's a continuum rather than quantized. Likewise, harmonic oscillator, we know that when we solve Schrodinger's equation, that the states are again discrete, their energies are equally separated, but in fact, again, in Maxwell matter waves, you can have any energy in the fundamental mode above a certain minimum, for example. All right, so there's different physics. All right, so the point is, this is a new tool set for one to understand actually rather complicated systems. Complicated mean they're quantum mechanical, they are open system, they are finite temperature. So in this system that I showed you earlier, there's a finite temperature BEC, which acts as the battery in the source well. Somewhere it's going to show up, I think. There it is. All right. So this is a finite temperature BEC. I told you that there's a gate well, which is harmonic, which means that it has harmonic oscillator states. And in principle, you get tunneling. This is a complicated system to, what we call it. We call it a quantum mechanical open system in thermodynamic non-equilibrium. It's a tough system to deal with. However, one can begin to treat it in a way that is much simpler when I take this Maxwell matter wave approach to see that actually this system has very transistor-like behavior, which is why we call this the source gate and the drain, and that this system will oscillate in much the same way that an electronic oscillator does. Even though it's purely, one can think of it as a system that has only atoms and otherwise a conservative atomic potential up here until you get to the open system. All right, so all I've done so far is really gotten up to not the depths of details on this, but instead the takeaway for you, what I want you to have learned is that, oh, in fact, Maxwell's equations, which I learned early on as an undergraduate, can be derived by using gauge field theory, and I can apply the same principles, gauge field theory, in the case of matter waves to come up with a class of matter wave duals to Maxwell's equations, and that is the route in which to get temporally coherent matter wave fields, which are going to be very useful for signal processing. And the beginning of signal processing is generating the signal, which is what I'm showing, but haven't described. Actually, I've described that in earlier lectures, I think even here. With that, let me end and take questions.
Okay, we have one question.
Hi, thank you very much for a very interesting talk. Van der Waals forces are emergent forces. They are collective response of molecular type of charge distributions. What guarantees the application for this kind of interactions of the minimal action principle that you use to derive from Lagrangians the equations that govern the system?
So I'm not sure I got the core of your question, but let me try this. We have a theory which is assuming very simple interactions that are described as S-wave collisions, all right? And that's an underlying assumption here is that's it. Once you've said that, then the rest of this theory comes. It doesn't really care. Physicists, theorists I've heard like to call this an effective field theory, but it doesn't really care the nature of the underlying forces, only that as far as this theory is concerned, it's a very simple force.
You still apply the principle of minimum action, right, to derive the equations from Lagrangian?
Yes.
How is it justified that you can apply the principle of quantum minimum action in this case, when you have emergent forces instead of fundamental forces?
I'm not. That's an interesting. I'm not sure I actually understand the question, and I don't think the Lagrangian cares whether they are fundamental or not. All I need to say is that such interaction exists, and simply doesn't care that, oh, you know, electromagnetics is fundamental, this is van der Waals forces, and which is ultimately electromagnetic. The theory doesn't ask that question about the source or how fundamental this force is.
That nature behaves such that the action is always minimum, and from there you derive all the equations, Maxwell's equations. In this case,
I think the Lagrangian itself, your solution, asks for the least action. The solution to the Lagrangian, specifically, that's where Hamilton's principal function comes in. Asks you to say, how do I apply the principle of least action? And these field theories, you know, the analogs of electric and magnetic fields arise naturally from that. They embody the fact that these particles are interacting. And I've heard this before, so I'd love to talk with you more to try to understand why folks get worry so much about whether the force is fundamental or not. Most of what we do in Schrodinger's equation, for example, doesn't really ask, where does the potential come from?
Yes, but it's more a fundamental force, and you know, for those empirically, right? You don't have a reason why the action should be minimum, but empirically you know that for fundamental forces, the action is following the least action principle. Equations follow that. And here you apply directly by constructing a Lagrangian and apply the least action to get the equation set that you got.
Well, you're right, but in fact, the principle of least action plays a lot of roles in which fundamental forces are not at play, including the flow of air over airplane wings. So which doesn't involve fundamental forces at all. So I'm not sure if I really understand the statement why we get so hung up on whether they're fundamental forces or merely descriptive of the interactions. But I would love to have you, try to go deeper with me and explain why.
Thank you so much. Yeah.
I should.
Thank you very much. We have more questions.
Yeah, I just wanted to ask an application question. Can you do mode modulation of the matter waves the same way you would funneling light through a nonlinear medium, for example?
Yeah, before we get into nonlinear medium, it's pretty trivial. For example, if I want to modulate by changing just a barrier height that you saw, that will modulate the beam. I can either modulate the amplitude or the phase of the matter wave beam. If you want nonlinear interaction, it takes a longer discussion, but the answer is yes, because the atoms interact. So if you have high densities, such as you have in a BEC, you can think about how you do it, how you get nonlinear behavior between, some matter wave field and some BEC, let's say.
Would this involve driving the barrier height of the light, for instance, using some sort of complex time-dependent function or something like this?
Yes, I'm thinking though very simply if an optical modulator drives the intensity. I don't have to get very complicated about that. You asked for a nonlinear interaction. So I think there's some very early work of having more conventional de Broglie waves interact in four-wave mixing experiments done by Bill Phillips ages ago. All of those are nonlinear matter wave interactions.
Okay, thank you.
You're welcome.
Do we have more questions from the audience? I have a quick question about the nonlinear interaction. So for the electromagnetic waves, we need nonlinear interactions because they don't fundamentally interact with each other. Is that the same case here?
No,
or
the atoms absolutely interact. You have two crossing waves and they'll certainly interact. So that's one of the nice things about this. You don't have to work as hard as you guys do to get ultimately you have photons that have to interact within a medium. Atoms will interact without.
So you don't need to mediate that.
That's right.
They just interact,
right.
Which is great. Yeah. If we don't have any more questions, let's all thank Professor Anderson one more time for the great talk. Setting up. Let me introduce our next speaker, Dr. Noah Fitch from Inflection, previously known as Cold Quanta. Dr. Noah Fitch is the Quantum Matter Portfolio Technical Lead at Inflection. He's a former Royal Society University Research Fellow at Imperial College London and an expert in low energy precision measurements for testing fundamental physics, atom and molecular laser cooling, and molecular beam deceleration techniques. His PhD work at California University at Boulder focused on decelerating and trapping molecules for studying cold collisions and chemistry near absolute zero temperature. His postdoc and fellowship work involved developing techniques for generating ultra-cold molecules and using those molecules to execute precise tasks of physics beyond the standard model, specifically CP-violating physics as evidenced by a non-zero electric dipole moment of the electron. At Inflection, his work includes leading the Octant program, which provides remotely controllable quantum matter as a product/service, as well as acting as principal investigator for numerous government research and development projects targeting inertial and gravitational sensing and other applications of ultra-cold quantum matter. So you also received a very nice introduction from Professor Anderson for your talk as well.
I did. Dana did most of my introductory work for me, so that will make my job easier.
Okay.
And I guess it matches the spirit of education where the best way to learn is to do it yourself, and the second best way is to hear the same thing more than once in a row. A couple points before we get going. Thank you for the very nice introduction, and thank you for the invitation. This is my first time in Purdue. I'll try to keep the crosstalk of microphones to a minimum. The eagle-eyed among you might notice the difference between your agenda and my title is the placement of a comma. And if I do my job today well, then you'll understand the distinction, but also that comma or no comma, it's a perfectly valid title. So yeah, I'll be telling you today about Octant, making quantum matter for anyone and everyone. And this will very much not be a lecture. This is going to be 10 or 15 minutes of introduction, stage setting, and then we're going to do some practical in-person jobs on the experimental hardware in Boulder, Louisville. So unlike most talks I give, I want to see everyone's laptop out if they have it. And I believe, since we're at Purdue, hopefully most of the students have a NanoHub account. Raise your hand if you do. That's an okay fraction. If you don't, I think it's pretty easy. Jump there and make an account. And then about 20 minutes in, we'll hit a place where you'll also want an Octant account. So I'll give everyone a few seconds to rustle through their bags, and I'll stop talking for a moment. And then if you can get a web browser open and get accounts made on those two sites, then we'll hit the ground running in 1 minute. I'll give you 30 seconds to get going. Much like a normal education experience, this reminds me of when you were in elementary school and your teacher ran out of ideas. They would give you a homework problem and then let you work on it in class. So this is your in-class homework assignment. And if you don't want to do it now, you can do it later, but I will check the website validation and user registrations. So I'm going to keep you honest. So those are the three things that we need for this session. So please get those going. Okay. Now, what is Octant? Dana did a very good job setting the stage for me and kind of deep diving into one of the different application areas. But ultimately, at its core, Octant is a cloud-controlled quantum matter generator or machine that puts what we call quantum matter or ultra-cold atoms in the hands of all of you with software tools that we strive to make relatively easy to use, including a web app, Python module specific for this purpose, and generic REST API that control experiments executed on that hardware that we host and maintain and tune up regularly at Inflection. Yes? Oh yeah, sorry. Oh, nanohub.org, excuse me. Nanohub.org. It's not a .com. Already found a glitch on the first slide. It's like when you look back at your thesis, you find a typo on whatever page you flip to. So nanohub.org. And we could do Python version installs and pip installs of the product, but I think this will be easier as an entry point. So nanohub.org, excuse me. Any other questions? And also raise questions as they come up and also comments so that this is more of a discussion. I really don't want this to be a traditional lecture. This is a summer school after all. Okay, so Dana also showed the machine looks something like this, although I'll show you the actual guts of the machine servicing the cloud service. And you plug into that with Python or the web app. And Dana gave an interesting example of one of the areas of application, but there's kind of almost 30 years of fundamental research to build on at this point with BECs and quantum matter. And what I mean by quantum matter mostly is just that we're giving you a quantum fluid or a quantum gas where the statistics are, depend that the particle is a boson, right? We have to throw thermal statistics out the window and it starts to matter what kind of particle we're dealing with. And in this case, we'll be dealing with rubidium atoms, which are bosons. So there's lots of different applications of what Octant can do, and we have different partners in different fields to work on this system and to provide them with service. One is just workforce training. Companies want their employees to be engaged with quantum and know what's coming and be able to play with the system, in many cases without having to employ the few PhD student equivalent people and the few $1 million of hardware to get up and running. And then physics education, particularly for non-R1 schools who don't have access to this kind of equipment, they're interested in giving their students exposure to higher end research. We have actual academic research partners studying things like atomtronics, phase engineering, controlling quantum currents. Dana talked about a very evolved version of that. But also I've been talking to partners about studying collisions, interactions, vortices, time crystals, kind of building on the 30 years of work that's been done in this kind of field. And where we're very much leaning as a company is towards quantum sensing and building quantum technologies and getting them out in the world. This kind of system is particularly good at building up towards inertial sensing, rotations, and accelerations. Gravitational sensors are a hot topic with us right now, and also magnetic field sensors. So you heard talks about non-abelian anyons, a couple already today, and how do you even detect that they exist? You could imagine that cold atoms placed over a surface might be a decent magnetic detector of things going on in the surface, or even using the matter type objects that Dana or de Broglie would tell you about as potential sources of edge states and things like that. In terms of analog quantum signal processing, you can think about analyzing quantum signals in kind of a digital quantum computer kind of way with gates, or also with kind of a more analog system. That includes things like quantum networking and memory, and then particularly a good connection to the QSC. Here's Kasia again. I never can pronounce her first name, so it's always just Kasia. But she's interested in looking at continuous variable quantum algorithms and something called measurement-based quantum computing, which is kind of a different error correction robust paradigm. So if you want to learn more about that, talk to Kasia at Los Alamos or Tyler as well. And that's part of Thrust 2, the algorithms thrust of the Quantum Science Center. So then I just have some images here of some work that's gone over the last 30 years with BECs and with quantum matter. And there was a particularly interesting overlap with this kind of dual well edge state type stuff that looks exactly like the dumbbell pictures we saw earlier, although I'm unsure how strong the connection would be. Okay, so what you get to play with Octant is the first thing you get control of is the creation of the quantum matter, the creation of the Bose-Einstein condensate. And this is the user gets control of the last cooling step. There's a lot of cooling steps ahead of this, but they get control of the last one, which is called forced RF evaporation. This is where you have your atoms trapped into a bowl, and it's the common analogy is like blowing on your soup. You blow away the hot ones, everything else gets a little bit colder. Except for in the atoms case, you blow away about 99.999% of them, and you're left with a very, very cold core. But the way you do this is you do this with an RF knife. So you have your atoms in a bowl, and then you bring an RF photon or radiation resonant with atoms that reach a certain height in that bowl, and then you slowly cut down into that potential surface and throw away the atoms that become resonant with that. Those are the hottest ones. They've rolled up the furthest on the potential, and then you're left with an increasingly more dense and more cold sample. And eventually it turns from a thermal cloud. This is the famous picture of forming a BEC. A thermal cloud, which looks, if you took cross sections of this, you'd kind of get Gaussian wing profile. And then you get this Thomas Fermi distribution, which pops up out of the center. This would be what you'd call a thermal cloud. This is a mixed cloud where it has a Thomas Fermi distribution and a thermal distribution together. And then this one, there's some thermal distribution left over, but it's pretty well squashed. And it's mostly this inverted parabola cross-section type Thomas Fermi. And that's the condensed quantum matter. Most of the cases we'll look at today involve both thermal components and also condensed components. But you get control of this process through Octant. That's the first thing. And the second thing is manipulating that matter. So just making a BEC is interesting, and 30 years ago, 35 years ago would have gotten you a Nobel Prize, but now we actually want to use them to do something useful. So most of those hooks into that are to manipulate the matter that you've generated with relatively arbitrary and dynamic potential energy control. And these are the images that Dana showed you earlier about the optical projection. Shining a laser down on those atoms that's off resonance, and how long you leave the laser there and how intense the laser is, you can form the optical landscape, optical potential energy landscape that you want to apply. And you have time control over that as well. you know, when you're taking pictures of these atoms at the end of all the things that you're doing, one, it's a destructive image, but two, you're, you know, really imaging a macroscopic wave function, which is, you know, in our case, some 100 microns long in one axis and some 10 microns long in the other. And that's something that we all take for granted now, but if you actually sit back and think about what you're doing, you know, you should appreciate the physics of the world that you're engaged with. So there are generally, you know, thousands or tens of thousands of atoms coalesced into this single quantum state. And you're taking a picture of them either in trap, so our trap geometry is such that there's one weak axis where the atoms are long, and two tight axes, so it kind of looks like a cigar, or if you prefer breakfast food, which we tend to do, sausage. And so if you look down on the cloud, it looks something like this. Gravity is away from you in this case. And if you drop it down, we call that in-trap imaging, where it's still trapped by the magnetic fields. And then if we release them from their magnetic trap and let them fall under gravity, those are some of the images that Dana showed you. We call that a time-of-flight image. We can control over when we take that picture. Now, Dana said you can do interference experiments with Octant, and I'm going to change his words to be you will in about 10 minutes. So we're going to recreate in real time the experiment that he showed you that happened on the first day of Octant's public release. So hope you all get that data to yourselves. And then, you know, once you have this playground, you can explore all kinds of quantum properties, coherence, tunneling, interference, the things that underpin all of kind of quantum sensing and technologies, all without having to build a piece of hardware yourself. Again, Dana mentioned this as well, but I've got some pretty pictures to go with it. Octant is, in many ways, the terrestrial cousin. I think he said a souped-up version of what's sitting on the ISS, which is called the Cold Atom Lab. This is a dual species system that has potassium and rubidium, and it doesn't have the projected light control. It's focused more on interferometry, but in many ways, they share a lot of ancestry and a lot of hardware designs. So this is kind of the picture. There's some coils to generate magnetic fields. There's some laser cooling of atoms that happen here, and then the atoms get transported up and trapped just under the surface of this chip, where you do the experiments that you want, and in the case of Octant, where you get control of what's happening. And there's just some relatively steady stream of Nature papers slowly filtering out of that work. And in fact, the same team that's in the Boulder area running Octant is also the same team that interacts with JPL to provide hardware to go up on the ISS, and we're currently working on delivering improved generation of this hardware. Before the ISS comes down in, I think, 2030, it's meant to have a fiery death of some kind. So, yeah. Okay, so how does Octant work? It's good to know at least the 5,000-foot view. Elevation of the machine is 5,000 feet above sea level, so hence the 5,000-foot view. And I just want to show you the general flow of how it operates. This faceless entity is you, and you interact with your computer either through Python or a web browser to create and define inputs that will control the experiment that gets executed. Those get submitted through a REST API, which runs in Google Cloud, along with a partner database, which also acts as our job queue. And once it arrives there, it becomes a job and gets a job ID. So it's very similar to submitting a program to a cluster computer, where you get a job ID back, and it gives you the status of that job, when it's going to run, the outputs attached to it, everything like that. We then have the local machine in Louisville. Has what we call a job runner. It queries this database, picks up new jobs, generates what we call an experimental recipe. This tells the apparatus what to do, submits it to the local control system. The experiment then carries out the job as specified by the user, which can contain many different aspects. We do all the pre-cooling steps. For the AMO people in the room, we do a 2D plus MOT. Originally here, where the rubidium atoms come from, injected up here into a 3D Manu optical trap, where we cool and collect the atoms. We then cool them a bit further with a few more tricks, trap them magnetically, and then we shuttle them up to just under the surface of the vacuum chamber. This is called a Rubecki, and the atoms ultimately sit about 100 microns off the vacuum wall under this chip. We then do the experiment manipulation that the user wants us to do. There's a little window in the chip which lets projected light come in from above. We'll see that in a second. At the end, we take a picture of the atoms with absorption. So we pass light, resonant light through the atom cloud and image their shadow. We pass that back to the job runner. In certain cases, certain analysis is done, figuring out the temperature of the cloud, condensed fraction, things like that. And it gets passed back up to the REST service. And that output data joins your input data in your job, and then you're free to pull those results whenever you want and analyze them. Any questions on that process? There's a lot of steps, so let's hope it all goes right. The hardware that supports this service, again, looks much like this, and here's kind of showing you some of the laser systems involved or where the light is deployed. And then this is kind of what the chip looks like. It's a little difficult to tell in yellow. But essentially, it's a chip that forms the wall of the vacuum chamber. And we pass currents through these wires, and those currents create magnetic fields. And they're engineered in such a way that that creates a magnetic trap, so that the atoms are sitting in kind of a magnetic bowl, which has this cigar geometry to it. The hardware isn't quite as clean as the picture that Dana showed. Here's the control system without the front panel on it, so it looks a little bit more messy. Some of the laser systems in this case have been moved to a small optical table. This is a 4 foot by 6 inch, 4 foot by 6 foot optical table, so relatively small. But we have a laser system for the projection, a laser system for cooling. There's a physics platform, the Rubecki. This object sits kind of in the middle of this object. And then it's difficult to tell maybe, but there's a little black box here. And that's the projection system which controls the optical potentials applied to the atoms. So again, Dana showed you some of the more extreme cases where we can kind of use that projection system to do various things. The way it works is crossed acousto-optical deflectors. So these are objects that deflect the light based on RF frequency and amplitude in a crossed axis. So we can paint light in 2 dimensions. Most of what all of what you'll see today is just one-dimensional control, where the light is always being rastered in this axis, and then you control its position in this axis in time and time and position. So this is kind of showing you what's happening, but really the details are here. The atoms sit, some 100 microns off the surface of this chip, this outer wall, and a microscope objective not very far away focuses light down onto those atoms. The size of that beam at the atoms is somewhere around 2 microns, 1/e squared waist. And so that lets us build these fine features on top of the atoms and move that light around. No questions yet? Okay. Yes? This isn't particularly high. The NA on this one's about 0.4. One issue with this cigar shape in the cloud is if you choose too large of an NA, then your Rayleigh range becomes shorter than your cloud depth. And so your potential in this position, imagine now this is depth instead of width, be different. In fact, it would look a lot like this, where you have you'd be seeing the Rayleigh range and that structure inside your cloud. And for this one-dimensional type potentials that we're doing, that's not very much desired. We could certainly go with a higher NA and get a finer spot, but I think it comes with additional complications. We do have at least a nominal program where instead of a sausage, we want to make a pancake. And then you could be free to have much finer resolution with a higher NA lens. Because you'd flatten the cloud and make it a circle from above and thin from the side. Yeah. Thanks for the question. Okay, so hopefully everyone's had a chance to make an account here. And with that, I'll just talk a little bit about the web app before we jump in. The web app offers kind of very basic functionality. You get to see the jobs you've submitted, track their status. You can submit new jobs with limited knobs. We'll see that in a second. Currently, every user gets 100 free jobs a month, up to 20 a day. There are paid options available, which lets your jobs execute more quickly and ups your limit of how many you can submit per day. And as well as that job kind of management, there's also access to resources and technical notes on the website. But the web app always lags behind what you can do from the Python module, and we'll see that as we go. Okay. Now I'm going to try to jump out of my presentation. And I will note, as we go to submit jobs on the hardware, there's nothing quite like taking data in front of a large group of people on your machine, and particularly when you're, I don't know, 1,000 miles away, and it's sitting there babysitting itself. So this is slightly stressful, but it's okay. So here's the web app. There's a little bit of a lag, but that's okay. Hopefully everyone can log in. If anyone has any issues, then let me know. And you're free during this session to submit jobs. They will run if they get to the top of the queue. It takes about 15 seconds per shot on the experiment. So if all of you do it at once, you'll all be competing with each other and things will be a little bit slow. My jobs will win because I'm in admid, so mine go to the top of the queue. So don't worry about disrupting the class. Feel free to submit as you would. So here I've logged in. I see some jobs that I've run in the past. Their status, these have all finished running. What job type? This job type basically depends on what kind of features you're using, whether or not there's barriers involved, or just making a BEC, those kinds of things. Each job gets an ID, which is the handle that you use to interact with the REST service. And so maybe I'll just quickly walk you through making a job of different types so that you can see kind of how it works. So if you go up here, you hit new job. There's two options here for the web app, BEC generator, which we'll do first. So here you have control of the forced RF evaporation frequencies. So as that frequency gets closer to 0, we're cutting deeper and deeper into the cloud, and we'll end up with a colder and colder sample. And how you do this in time determines kind of how efficient that process is, how fast that process happens. So you can move these things around in time and frequency to make the cloud different temperatures and have different populations. And then you also control the RF power sent to the antenna that emits that radiation to the atoms. This one's slightly more complicated because it's an antenna that's actually kind of optimized for a certain frequency band. So as you get towards lower frequencies, here, the actual delivered power drops. So this is all described in some of the technical documentation. But for right now, I'll just stick with the default things. All I need to do is give my job a name. And then the other settings here are time of flight. So this is 12 milliseconds at the moment. This is how long we're going to let the atoms fall off the chip before we take their picture. And then you can also give something I wanted to remember notes. Something like that, and we'll submit the job. Takes us back to our job page. We see that job go in. It's currently in a pending state. Hopefully in a moment we see it as running. There's probably a user job running currently, so we might have to wait a few seconds. But now it's changed to running. And while that runs, we'll do another new job, except for this time we'll do barrier manipulator. The web app has kind of by default 2 barriers built in. You're on the top panel here, you set the barrier position in time, and then you can also change the barrier height. So here we see, for instance, we are going to ramp the barriers on over a period of 4 milliseconds and then hold their positions, but you are free to move them around dynamically as you wish. Once we get to Python, these will be completely arbitrary, well, not completely arbitrary, but highly arbitrary lists that you can have much more control over the barriers. This one will do something slightly strange because we're going to be sweeping barriers around. But in this time, we're going to do an in-trap image instead of a time of flight. You can do either one. Usually with barriers, it's easier to see the effect in trap. And we'll submit that one. We'll go back to the other page. Here we'll see my BEC generator job is already done. And here was the image taken as those atoms had fallen to the 12 milliseconds off the chip. What did I do? I made about 20,000 atoms with those settings at a temperature of about 98 nanokelvin. I always twitch when I see this because it's always low, in the sense that I worked with molecules for most of my career. And I remember the day where it was a success to get 1 Kelvin molecules. And then I remember the day, I'm probably aging myself, that it was a success to get 100 millikelvin molecules. And then I remember the day where we figured out laser cooling and we were able to get 1 millikelvin molecules. And then I remember the day that we figured out subdoppler cooling and we were able to make 10 microkelvin molecules. And those decades of work are wiped out by a single submission, getting the atoms down to 100 nanokelvin. So it's not a competition, but it still gets to me sometimes. In that population that we made, about 11,000 of the atoms were identified as thermal distribution, and 7,000 or so were condensed. That might not be totally obvious to you from these types of images, but from a cross section it can be, and this we'll see a little bit later too. Here's a cross section through that cloud. And you can see, maybe you can make out the fact that there's some Gaussian wings, Gaussian-like wings here, which are the thermal fraction. And then this strong peak in the middle is much like those pictures that we saw earlier. And then you get a picture of the MOT as well. That's just collecting light from the MOT fluorescence to help you track drifts or make sure that everything was working. And then you also get a fit for the time of flight, which is how these numbers are calculated. Any questions on that level? Yes. Sorry? I didn't quite catch the beginning of the question. Sorry. Instead of the images, is the actual measurement data of the measurement? Yes. So that's a great question. If I go here, I can view data. These are all the inputs encoded in some job data, some Python class structure. And then you have access to the raw data here. It'll be much easier to access via Python, but it is available here. And in fact, for select users, we're giving them access. So these are all processed images. So these are OD images. So we've taken an image of the atoms, an image without the atoms, subtracted them to calculate the optical depth. And that's what gets passed back to the user. Every shot, we do capture all the inputs and outputs and all the details about what happened in that experiment. At the moment, that data is only accessible by what we call partner users, which help fund the storage for that data and access it and things like that. So there's quite a bit of data here, and if you run out of that data being useful, then you can talk to us about having access to more. My barrier job, but I don't know what it will do, also ran. And there we go. So this one, none of that analysis is done, so we don't get anything about condensed fraction. For one, that's because we've taken a picture in trap where there's still magnetic fields on and the imaging environment is quite complicated. But also, we've applied barriers to it. So the simple model of thermal fraction, condensed fraction kind of falls down, and it's a much more complicated problem. So we don't do that, but you could certainly do analysis on your own. Okay, so those are the simple ways to use the web app. That was the easy bit. But the machine's actually sitting there executing jobs successfully, which is always amazing. And any questions before we transition out? Okay, I'm gonna leave that web page open, if you don't mind, and we'll come back. So far so good. Are we back? We're back. Okay. So as you saw, the controls there were functional, but kind of rudimentary, kind of basic. And we've been working hard on, and most of our users engage with the platform through the Python API. This is an object-oriented program for the most part. It's available on PyPy, so all you have to do is just pip install Octant if you're a Python user. We always suggest doing that inside of a virtual environment, but we won't have to do that today. So don't go pollute your global namespace or whatever it is. We have a dedicated evolving documentation site, which I'll talk about for a couple slides, called octant/docs, denoflexion.com. This involves walkthroughs, which teach you basically how to use the tool, how to use the abstractions that we've built, and demos, which are kind of leaned more towards how to do cool stuff. So there's a picture of PyPy and a picture of the documentation site. but not much more to say there. Again, the walkthroughs, they take the form of Jupyter notebooks, which most users are at least familiar with. And they walk the user through how to create jobs, how to save them locally, how to process data, what the input data looks like, what the output data looks like, things like that. That basically hold your hand and walk you through how to use the system. I think we skipped one. No, maybe not. Okay. We have some abstraction layer built on top of the job data that you saw. Everything flows through what we call the quantum matter factory. That's how you create and analyze outputs and inputs and all the things that you need to do. There's something called the Octant client, which is mostly transparent, but while you're operating in the background, which you might see. The central object that you create and analyze to interact with the service is a quantum matter object. And it's a container for all the inputs and outputs that you'll be engaged with. Things like an RF evap object, which is how you control how the BEC is made and evaporated towards barrier objects, which are exactly what you say on the tin. And then landscapes and snapshots are kind of more, slightly heavier version, but more functional version of barriers if barriers are too limiting for your application. The demo slide, which I expected before, is now here. Dana showed you this multi-slit interference, which I hope to recreate with you. But there's other things, like we have one on measuring the speed of sound in a condensate, which turns out to be on the order of a couple millimeters per second, which is quite different than the speed of sound in air. We have some coming on solitons and other things. And we have one also focused on phase and collective modes, based mostly on simulations, which I'll talk about in a second. But it's kind of fun to see people play with this platform and in just about 10 or 20 lines of Python replicate Nobel Prize winning experiments from the last 30 years. As well as the ability to submit and retrieve jobs from the cloud service, we also have what we call the Octant simulator. This is a single flag that you put in your quantum matter object when you submit it. Instead of sending it through the loop that I just showed you that executes on the machine, instead it spins up a simulator locally and simulates what that would do with all the same input and output knobs as a regular job. So that it's a kind of a seamless transition between submitting simulations and submitting jobs to the hardware, which numerous people have found quite useful. You also get access, when you simulate something, to more data than you would had you submitted on the hardware. So one limitation of the hardware is that the images you take of the atoms are destructive. So if you want to take, say, a time sequence of data images, you have to run multiple jobs, because every time you take a picture, it wipes out your atoms. That's, of course, not true in the simulator. So you can get all the time data that you want, and you can make fun little animations of here's the cloud finding the ground state in the presence of a barrier. And then you also get information about phase of the condensate in various positions. And that's kind of the psychedelic things that you see here, as well as column densities, matter flow, those types of stuff. Okay, so again, you can pip install the package in your Python installation, or alternatively, me and a couple people from the NanoHub team worked through the week last week to try to get this thing working on NanoHub, on the tool that you guys use here at Purdue. I think this is quite a promising platform. I will say that it's not particularly well documented yet, so there was a lot of head banging to get a tool uploaded, but if any of you have experienced that and didn't have a hard time with it, let me know. With that said, this Octant tutorial tool is still a little bit in a fragile state, so just be aware. But it is up, and now I'd like to jump to see if that will work in real time, and hope you join me in submitting jobs that way. So while I transition, I'll pause for any more questions that pop into your head. Any comments about NanoHub and how I made it harder than it needed to be? Yes. So we do have the Terminator beam that Dana mentioned. That actually got released today. So that will allow a lot more kind of Atomtronics type applications. One of the demos that we've played with, but really want a user to kind of finish off, is like an Atomtronic or an atom laser, where we do some evaporation during the experimental phase, let atoms fall out, and create a kind of a coherent matter wave that way. So Dana, did you have something to add? No? Okay, I thought I saw your hand go up. So I think the experiments that we can do are limited only by our imagination, your imagination, and then we love to work with partners to add new capabilities, new demonstrations, and those types of things. So let's give NanoHub a try. Actually, before we jump to NanoHub, okay, we can jump to NanoHub. That's fine. So go to your NanoHub account, nanohub.org/tools/octet. Hopefully you guys can get to that. And then launch the tool, and we'll wait patiently for a moment while a Docker image spins up on some machine hosted somewhere in the world. Actually, is NanoHub hosted locally? Does anyone know? Or is it? Nobody does. You guys use these for your courses? Is it pretty common? Okay. All right, and we should get, eventually, a Jupyter notebook pop up, which is going to be our working example for the rest of the time, or almost the rest of the time. Okay. So one challenge with NanoHub is Octant uses OAuth 2 for user authentication, which requires a web browser. And NanoHub does not support this. So we had to come up with a slightly hacky way to authenticate you as a user. So this is going to be the most fragile part of the whole process, but I hope you'll follow me. I might tell you to look away at one moment. If we actually first we can execute that first cell to make sure everything's working. We're on Python 3.10. You should see something about your local directory on NanoHub. Don't worry about the port. Execute the setup imports and everything there, which imports Octant as well as some other tooling. And then here's the part where we have to be a little bit hacky to bypass the user authentication. So we need to get an access token. And the only way to get an access token is through the web browser. And we haven't yet streamlined this because we only figured this out a couple days ago. In fact, it was Sunday night when we got NanoHub working. So if you go back to octant.inflection.com, everybody there? I want you to right click and inspect. This is going to show you the guts of what's going on in Chrome. Okay? Raise your hand if you need more time. So right click, inspect, and then we're going to go to network. There's a network tab here. Hopefully it's similar in other browsers. And then what we're going to see is our network traffic on this page. Now I'm going to have my other half of my window, I'm going to click on something. In this case, I clicked on a particular job. And then you see the network traffic associated with retrieving the data for that web page here. So then click on a particular event. Job limits is a good one. Okay. Everybody with me? Yeah, I'll go through it again. Okay. We're going to right click, inspect. Then we're going to go to the network tab. Yeah? No network tab? Uh-oh. We'll let the collective hive mind take a gander at it. Okay, that's a nodded chin, good. Network tab. And then we have no network traffic yet because we haven't loaded anything. But if I go back, if I do anything on the main page, I should get a series of events on that network tab. Yes? I told you this was fragile. Okay, this is not the normal operating procedure. I'm going to click on job limits. Okay, and here's all the data involved in that exchange. Now, don't focus on this, especially those of you remote that can screen grab. Inside this header, so inside this event headers, there's something called a bearer token, authorization bearer. And it's this huge long string. We're going to copy that. Do that for yourselves. Okay. And then everybody, let me know if you need more time, but everybody copied their bearer token. I realize this is a little bit fun. Now we're going to copy that token here. It's pretty long. So sometimes it's hard with the lag. Turns out when you're in a Zoom meeting, it takes longer. Usually this is instantaneous. So yeah, it's a long string. It's fine. It's for security, and I showed you mine, so it's okay. Oh no. Yeah. I'm gonna do it a different way. Yes. If there's a question, please shoot. NanoHub, nanohub.org/tools/Octut, OQTUT. You there? Okay. I'm going to paste my ridiculously long access token there and execute that cell. And then I'm going to use that token to activate this get client call. And I'll get a message about my daily job limits, and that indicates success. So everybody try that. It's also yelling at me because we released a new version this morning, which isn't on NanoHub yet, but I don't think anything will break. Okay, how many of you did I lose? Anyone successfully see this little black box? Raise your hand if you see this. But your numbers will be different, but yeah? NanoHub makes this authentication step difficult. After that, it's seamless. So, yeah. It was this or make you install a particular version of Python and pip install on your computer. I thought this would be easier. Okay. All right. For those still with me, then we're going to go start having fun. Okay. So what we're going to do is first up above, we created a quantum matter factory, which we said is defined as.
Maybe we can suggest that some people are struggling to make the key happen, that you might find a neighbor, or maybe the ones that are successful raise their hand, and then somebody can sit by the neighbor and see what's going on. How many people are actually up where Noah is? Be proud.
All right, if you're struggling, squeeze by your neighbor. We're going to talk to each other. This is a school. That's a good suggestion. Okay, and if you just want to sit back and absorb, that's okay too, but I think it would be less valuable. So what we're going to do, okay, hopefully we're in. I'll let you guys settle. Okay, and I'll continue. Here's what we're going to do. So yeah, if you're struggling, just sit back and absorb. But hopefully you're engaged. We're going to create a quantum matter object with this create quantum matter method. And what we're going to do is specify a target temperature. This is the simplest thing we could possibly do. Again, this is in nanokelvins, so keep that in mind. And we're going to give that job a name. And that's the simplest set of inputs that we need to provide to submit a job to the cloud. Yes? Is that group, you guys okay?
We're working it out.
You're working it out. Do you want me to pause for 10 seconds?
Yeah, you don't mind.
I don't mind. This is interaction. This is learn by doing. Yes. They're rubidium, rubidium-87, in a particular state that's trapped magnetically, but beyond that, it doesn't matter too much. They get wiped out, and then that's one of the reasons why it takes 15 seconds a shot, is that we do preparation steps again, get them up onto the chip, apply the experiment that the user specifies, and then take the destructive picture and do the next one, so on and so forth. It's sitting in a corner lab in our Louisville office. Yeah. And so it's hands-off during cloud service, which is every other week at the moment. Yeah. How much rubidium do you go through in a day? It's kind of hard to measure. It comes out of a dispenser, and there's something probably like, I don't know, 10 to the 20 atoms or something in that. It's a little module that you pass current through, and rubidium comes off of it. It's a salt. In terms of ones that actually capture and laser cool, we start at SHOT with about a few hundred million of them. And then by the time we do all the preparation steps, get them on the chip, do the evaporation, we're left with 10, 20,000, 10 to 100,000. So we throw away a lot. They probably end up in the vacuum pump or on the vacuum walls in most cases. But compared to like how many atoms are in a macroscopic object, these are all pretty low numbers. So I've never had that question. That's an interesting one. Okay, ready to continue. So we're going to create this quantum matter object just by executing this cell. And then that quantum matter object lets us do various things. We haven't applied any barriers or any optical potentials at all. So if I do this show potential function, which I can tell it what time is to show the potential at, it's just a quadratic Bowl potential. So this is the long axis of the cloud. So this is a relatively low trapping frequency. But if we apply barriers later, we'll see that we can control this landscape that the atoms sit in this one dimension. Okay, does that make sense? So simple potential, we're just going to evaporate to VEC, nothing fancy. And then here's how I submit a job this way. I call matter.submit, and then I've used this little track equals true option to tell me what the job is doing in real time. It does block any other execution until the job is complete, so you have to kind of keep that in mind. But hopefully we should see it get submitted here. If I go back to my job page, I see that job, I can close this. I can see that job that I submitted from the Python API has also joined this list and is in fact running at the moment. There's still some murmurs. Everyone okay? Do you want some help? Thumbs up, great. Okay, job is run, job is complete. Now we're gonna grab the result from the REST API. Okay, result is loaded. And here's all the fields. Here's just a list of all the fields that we have access to and once a job has come back. So we get back the MOP fluorescence image that you saw on the web page, including pixel data, rows, columns, all that good business. In this case, we took a time of flight image, so all that data is there. The fit image is also included, some slices, things like that. And then some calculated values at the end, total MOP atom number, so on and so forth. So you can feel free to explore those as you want. The meat and potatoes, or the center of everything, is the time of flight image that was taken. And so here's the same image that we would have seen on the web page. And then here's some slices that are taken of that data. So here you can really see kind of the thermal wings, thermal Gaussian wings, which is from the thermal fraction of the cloud, and then this inverted parabola type Thomas Fermi, which is the condensed fraction of the cloud. Yes? And then some pre-calculated values. This one actually had a temperature of about 176 nanokelvin, so a little bit warmer than our cloud job. Had 40-something thousand atoms with some small fraction of them condensed. And by changing the target temperature, this actually shows me, since I asked for 100 and got 176, that a number needs to be tuned. But that's something that we do in real time usually. Okay. I wanted to show you how the simulator worked just while we're here. So we're going to do exactly the same thing, defining this matter object. And instead of submitting it to the cloud service, we're going to use this sim equals true flag. And that's the only difference. On the NanoHub hardware, it doesn't run particularly fast, so I'm going to submit it and then cancel. So you feel free to play around on your own. Through a small quirk, the simulation doesn't actually run until you ask for the result. But in fact, if I make this short, it might run in real time. And you can see it go through a number of steps, calculating the ground state, which is before any fancy potentials have been applied, basically recreating the state after evaporation. Only condensed part of the cloud is simulated if we're being strict, but then it will go through other steps as we go through. Okay, so I'm going to cancel that one if I can. There we go. And then I'm just going to cut that out for now. So let me clarify one point. Submitting hardware jobs, they only run when we have the machine online processing jobs in real time. You can submit at any time. They join the queue, and then once we turn the machine on and start processing jobs, that queue gets consumed, and your jobs will run. Sometimes that's a few days after you submit it with our current. The simulator is accessible at any time. Nothing goes through the cloud service. Everything runs locally on your machine, or in this case on NanoHub. And so you're free to explore what a basic simulation of the Gross-Pityevsky equation thinks will happen with your manipulation, so that will inform you what you want to do in an experiment. And then you can use that knowledge to make the best use of your experimental runs, which are a little bit more precious because they only run some of the time. Okay. All right. Yeah, we're doing okay on time. So hopefully we're still it's up to speed. That was the simplest thing I could possibly do above, where I just specify a target temperature. There are other options as well. So here's that same input. The lifetime is how long should the condensate be held after the initial evaporation. So we can hold it there for a while. You'll find that the condensed fraction changes over time as collisions and other things happen in the cloud. So you can do different lifetimes. Also, that lifetime is when the optical potentials will be applied. We'll see that in a second. You have control of the time of flight. So you can take a picture right when the atoms are up next to the chip in the first couple milliseconds of being dropped, or you can do it much later when they've fallen further from the chip. And this will depend on what kind of dynamics you're looking for, your choice there. Again, each job can have a name, optional, and each job can have a note, optional. And so you can specify that. There's also a lot of validation that happens in the Python module. So feel free to play with parameters as much as you'd like. If it's outside of an allowable range, it will yell at you and give you an error. So for instance, if I try to do a negative lifetime, it should tell me no, and it does. Or if I specify too long of a lifetime, it will yell at me again. So imagine, for the experimentalists in the room, imagine you were going to give an unknown person access to knobs on your experiment, and then you have to try to protect it from them because they don't always know what's best. No offense. Okay. So again, all we've done so far is specify a target temperature and submit those jobs. Here, just like in the web app, or in fact more flexible than the web app, we can create an RF evap object, which is this function call here, where we are allowed to give times, powers, frequencies, and how to connect those in time with an interpolation option to control how the evaporation happens. So we'll do that here. This is evaporating over about 1.6 seconds. So these times are in milliseconds. Powers are in milliwatts. Frequencies are in megahertz. Suitable units for what we're trying to do are kind of chosen throughout. And the walkthroughs will tell you about the units on everything and show you what each field is doing. So we'd call this maybe direct RF control. And then I could submit that job and get a different result for the number of atoms, the final temperature, the condensed fraction, all those types of things. Okay, let's get to the fun bits. In-trap imaging is also here. You'll notice the definition and calls to this function are all the same, except for that I've asked for image equals in-trap. And then we can submit that. And it's running immediately. There's a bug here because I never called get result. So you want to add that in this line if you're following along. That job just finished. So we can grab the result. We can see the output data included. And there's our picture of our atoms while they're in the trap. We haven't applied any barriers or anything, so it's not particularly interesting other than its aspect ratio is what we expect. Okay, a few minutes left. Should we do some potentials and try to do a nice demo? Let's give it a whirl. So in Python, we have barrier objects. This is how we can split the cloud, apply potentials, nudge the cloud to one side, do all kinds of different things. And we do that by qmf.createBarrier, so relatively intuitive. We specify times. So the first time is when the barrier should be created. And the second time, or the last time, there's only two in this case, but the last time is when the barrier should be destroyed. And then for each time, we have a position, a height, and a width. This is where the barrier should be, how tall it should be energetically, in kilohertz in this case, and then how wide it should be. So this is, the projection system is able to give your barrier width. So you could grow a narrow barrier and then have it relax either in height or width in time. So you could move your atoms out to the side and then let them slosh back, or all kinds of different control. You have three choices for the shape of your barrier. And each shape has, the width means something slightly different. Gaussian, Lorentzian, and square. Basically, traditional shapes that you could describe with a single parameter on the width are available. And so you can see here we create a Gaussian barrier. I call this barrier class method a show potential. And it shows you what the machine thinks that the applied optical potential will be. This barrier is pretty boring. It sits at 10 microns and stays there. It starts at 30 kilohertz in height and stays there. And it has a width of 3 the whole time. So this barrier will just pop into existence and then pop out of existence. There's no smooth turn on, turn off, or anything like that. So the potential energy of the barrier will look something like this. The eagle-eyed among you will notice a little wobble on the top from the limits of the projection system, and dive through the walkthroughs if you want to go into that. As I said, this barrier is pretty boring. I asked it to plot its dynamics. So this plots the width, height, and position as a function of time. And so here you can see the barrier being created, not doing anything particularly interesting, and then being destroyed. Okay? To include that barrier in a quantum matter object, we use the same create quantum matter we did before, and we give that barrier as a barriers list. You can do, I think, up to 10 at the moment, but there's no real fundamental limit. So we provide that barrier that we defined in this list, barriers equals barrier, and then we submit that, and we're going to take an in-trap image. That job is running. This used to take a minute, which made this much harder to do. But 15 seconds is okay. So what do I expect to happen? I expect to split the cloud, right? This rather violently, I would say. This tall of a barrier will split the cloud, should split the cloud quite dramatically. So there we see. We made a barrier over here on the right at a position of 10 microns, which is where we expected it. There's probably a lot of dynamics happening on either side of this picture, but you can't see them in a single still. And the reason that there's probably a lot of dynamics here, there might even be vortices if you look closely enough, is that we turn that on quite abruptly. Not a very adiabatic application. Yes? Sorry? Why is it 15 seconds? It's just the time it takes to get the atom sample prepared and all the calculations to be done. So there's a little bit of lag in the cloud service. That accounts for a few of the seconds. Most of the delay is actually in the control system. So it ingests, if you want to get into details, a large chunk of data as a JSON object that represents all the steps it needs to do. There's probably 150 different steps that happen between when we hit go and when the atoms are ready to, for the user part. And all of those have many parameters that are in them. So maybe there's, I don't know, 15 steps, depending on how you define step, and there's probably 150 parameters along the way. The user has access to some of those, but most of them not. And so just loading that in, or creating that document, loading it in, getting all the hardware ready, and then doing the laser cooling of the atoms takes a few seconds. It takes 2 or 3 seconds to load the MOT in the first place, another half a second to get them up to the chip. There's some time taken to calculate the waveforms. So this optical projection system is based on what potential that you want to apply. Inverse Fourier transform, what frequency components are involved, make sine waves with those frequency components, load them into an AWG, send them out to the AODs at the right time. There's a lot that goes on, so that's why it's about 15 seconds. Good question. So we are able to split the cloud there. Barriers can also be scripted. So here I started with the barrier, much like we did before. I've moved its position. And then barriers have this evolve function. So you can start with this and then evolve them in time. Duration is how long should you take to get to the new set of things, move to a new position, move to a new height, move to a new width, so on and so forth. And when you show the dynamics, you can kind of see that those things have been applied. This barrier will nudge itself up in width. It will start with a held position, scan for a while in one direction, scan for a while in the other direction. And its height is plotted over here with green. Start tall and then ramp down again. So here's kind of a picture of that potential at different times. So at early times, we made a big barrier in the middle. It swept right and shrunk, and its width got wider, and then it shrunk to the left as well. And then, of course, the barriers don't exist on their own in a vacuum. There is this background magnetic potential that the atoms sit in. So the total potential is the sum of those two, which is often important for applications. But that's the basic way of creating and manipulating barriers. And you're free to explore as much as you'd like with that space. Okay. I want to get to landscapes very briefly. I'm going to go quickly over these, but they're kind of a more flexible version of barriers, but I don't want to get bogged down. I want to get you to the point where you're doing that first day octant public service demonstration that we saw earlier, which is multi-slit diffraction. Okay. So I'll give you the quick overview. Landscapes are the ability to specify the potential at different positions and how to connect those in space. And they're dynamic. So what we do is we define something called a snapshot. This is a single instant in time, what the potential energy landscape looks like. And then we do multiple snapshots so that later the potential can look different. And then the software stitches those together and interpolates between them. So one snapshot can turn into another one depending on their time values. So that's the general idea. Here's a snapshot. I've provided a time that potential should be realized, a list of positions where I want to specify what the potential is, and a list of potential energies there. Okay, and so here is that snapshot, which is, as you can tell, a little bit more flexible than a regular barrier because we get to specify more data. Okay, and then, for instance, for the same input data, I can choose how to connect them in space with this interpolation option. This was linear, but the same input data can use different interpolation options so that you can set up something that looks a little bit more like a staircase for a square option, something that looks more linear for that option. And here the dashed line is the ideal potential, and the solid line is what the machine thinks it will actually realize. And so there's some finite resolution of the projection system, as we discussed before, gives the square edge a little bit of roundness. And then there's finite frequency components in the AWG, which we talked about a little bit later. And that creates a few little features that you aren't necessarily ideal, but as close as the system thinks it can get to it. And then the last one was a cubic interpolation. You have to be a little careful with cubic interpolation because it will go to negative potentials, which blue light can't do. And so you'll notice that the ideal potential dips below 0 here, but the actual potential projected is flat-topped at 0. Okay, and here we take one snapshot. We've defined another snapshot that we've defined, and we use it to create those two to create a landscape. And what that landscape will do is at time equals 2 milliseconds, this potential energy will be realized. At time equals 5 milliseconds, this potential energy will be realized, and it will connect them smoothly. And so here we can take some snapshots of what that potential energy landscape will look like at different times as one potential turns smoothly into another. Okay, so hopefully that's somewhat intuitive. It takes a little bit of getting used to. And now we create the quantum matter object as before, but instead of adding barriers, we add a landscape argument. Okay, and you can do simultaneous barriers and landscapes. The world is your oyster. But here we see at 0 time or at early times, we had this initial snapshot, and then it will evolve into this other one later. The snapshots that I defined are all gone by 16 milliseconds. So this red curve is the potential with no landscapes applied at that later time. But you can play with these inputs as you want. So we're going to do multi-slit diffraction using a landscape. And I'm going to zoom over the code here because I don't want to get bogged down. Again, what we're going to do, we're going to evaporate our cloud to 50 nanokelvin, I think, 50 nanokelvin-ish. We're going to raise up 12 prongs to split that matter into multiple wells. And then we're going to do that gently. And then we're going to release the potential and release the atoms, and we're going to image them as they fall under gravity. Okay, so what we're doing with the wave-like nature of the atoms, we're going to do a multi-slit diffraction experiment. Okay, this defines the potential, the final potential, and these are the snapshots that get us from one to the other. At the beginning, all the potential is flat. That's all these zeros that you see here. And at the end, it will raise to that value that we defined above. So we're making this periodic optical potential, which will smoothly turn from a flat line minus the magnetic potential. And then those prongs will raise up in time, splitting our cloud into multiple coherent, phase-coherent pieces if we've done our job well. And then what we're going to do is we're going to drop that cloud for different amounts of time and take a picture. In this case, 5, 10, 15, and 20 milliseconds. At early times, we're kind of in the near field of the diffraction, and all of the features will be very, very fine, and we won't actually be able to resolve that. But as the cloud falls down, we'll get to the far field, and we'll be able to see the interference. So this is going to take 4 jobs, and here I'm just submitting them individually. It will do them sequentially. So we have somewhere around a minute to wait for the results to come in which I'm going to grab a drink of water, and yeah, you guys can do the same if you'd like. This notebook is what's on NanoHub. So if you check out the tool on NanoHub, you'll have this notebook. We have about 7 detailed walkthroughs, which are similar to this, and I think 4 or 5 demo notebooks at this time. So those are all on the documentation website. I'll work on making the access token flow easier on NanoHub, and then we'll keep that project updated, hopefully moving forward for you guys to play. Yeah, so on the NanoHub site, I think there's a download button, if I'm not mistaken. You can download the Jupyter notebook directly. Passing Jupyter notebooks around is a little bit of a security concern, but they must have figured it out. Looks like our 4th job is running. So we'll give it a few more seconds. Oh, we got one more. Maybe there were 5 there. I don't know how to count from 0. Just a moment. That's running. A few more seconds. And these are old results, so fingers crossed we get something that looks reasonable. I think the experimentalists in the room know how fun this is to take data in real time, and there we go. We've got a little bit of dust on that last image, it looks like. We're getting far down on the camera, so we're getting towards the edge at that 20 millisecond time of flight. But you can see that at early time, so this was 5 millisecond drop, we can image our cloud. And then it will expand, of course, as a function of its temperature. And as it does so, the clouds will overlap more and more and show us this far field diffraction. At 10 milliseconds, you might just start to be seeing some diffraction or some interference. It's becoming a little bit more clear at 15, and then by 20, I think you could start to see that we do have decent. The resolutions on my screen is much better. That we're starting to seeing matter interference. So we've demonstrated interference of coherent matter in just a few lines. So it's a fun tool to play with. One of my favorite things to do is to watch we have a resident BEC theorist, and of course he's played with these ideas forever in his head and never actually had the chance to run them on an experiment. And he's slowly earning his experiment badge. So I suggest that many of you hopefully do the same. And then we can look at cross sections, and you can start to pull out, and we're not doing any averaging here or column summing or anything, so it's a little bit messy in terms of signal to noise, but you can start to see the structure of this interference. So that's just the tip of the iceberg, and I hope you guys find it easy to use, other than the access token. If you actually install the package, it will be much cleaner, and then you can get to doing fun and cool physics with this platform. So I've got about one more minute. I think we're okay on time. And let's see if Zoom will let me do this. Kind of what's coming next. So we have all these materials we're seeking out and engaging with many different customers across industry and academia. We're slowly releasing new features and new material. So the Terminator capability and Atomtronic functionality that Dana showed earlier was released today. So there's a walkthrough for that. We're working on improved control of optical potentials, better time resolution for controlling the time of flight and other parameters. More demos are coming, more walkthroughs. Particularly there's one on solitons that I think will be next. We've been doing some machine learning and trying to figure out how best to do this evaporation process, kind of this multi-parameter space. And we're working on features inspired by and developed with external users. So if you have an idea and a need, reach out to us. We're looking at extending to 2D painted potentials instead of just this 1D limited stuff. Better resolution for the projection system, and additional machines which support additional capability, particularly sensing. And I'll leave that, since we're just about out of time, with a couple messages for you guys. If you found this fun to use or think it would be fun to use, I encourage you to give things a go. We have a Slack channel, we have emails. Reach out to us. We'd love to work with you to develop new materials. It's not quite a publication, but it's fun to get your name out there and show something that you built for the world. And make the coldest place in the universe, and then do something even cooler with it is something that we want to see you doing. This is a summer school after all. We're meant to extract information from you. You're not just meant to listen to us. I'm really excited to see what you guys do with this and everyone around the world. So go play, have fun. Thanks. I know we did some questions during the session, but are there any extras?
Thank you. Thank you very much for the great talk and the great demo. Do we have any questions from the audience? Okay. Sorry.
So when you showed like the distribution of the atoms, some of them were in a thermal distribution and some of them were in the condensate distribution. Is the thermal distribution affecting the simulation so much, and how can you get rid of that if it's undesirable?
Is it affecting the simulation? That was the question.
Yes.
Yes, so I think simulating the condensed part is fairly straightforward. You're solving basically an altered Schrodinger equation. Taking into account the thermal fraction is a bit more resource intensive. You have to worry about mean field effects and the trajectories of the classical atoms versus their interactions with the condensed atoms. It's something we're looking to potentially expand into and include that part of as part of the simulation. But right now we don't have that feature. So I think it depends. If you condense very, very heavily, you have 80% of your atoms condensed or something, then the thermal fraction will probably only play a very, very minor role. Often, if you're trying to demonstrate something like tunneling, If you have a thermal fraction, it might be able to spill over the barrier, in which case you have to be very, very careful that you're actually seeing tunneling and not just some thermal atom remnant. And so those cases, you have to be very, very careful. So try not to make claims that are just based on thinking you have a purely condensed cloud, would be my one suggestion. Yeah.
All right. Thank you.
Sorry, just real quick. Can you, how is this temperature actually calculated for the BEC and the thermal combination?
Yeah, so generally, you get a temperature from time of flight, taking data at different time of flights. And you basically get a ballistic expansion as a function of the temperature. So in this case, we know the size and extent of the cloud when it's in the trap. And so from that, we use there's some usual tricks that you play with. The cloud expands much more quickly than you would think from its native temperature because of interactions, right? The chemical potential is non-zero and the cloud kind of explodes. In fact, you'll notice that the cloud is long in this axis, but in all of our time of flight pictures, it's long in this axis. And this space inversion is a characteristic of having condensed atoms, is because it's narrow in this axis and they repel each other. And so when they're released, it expands more quickly in that axis than the other one. So we just take a single time of flight image and we backtrack to 0 time and estimate a temperature from that. If you want to be more serious, then you would take multiple time of flights and ballistic expansion of the thermal component. And then work that back into an effective in-trap temperature. So this is thing people have worked on for quite a while. So yeah, that's a good question.
So does that work for, I can see how that works for the thermal part, but the condensate part doesn't expand classically, right?
No, it only expands because of this mean field interaction part. So in fact, we are unable to measure the temperature if we get cold enough.
Yeah.
We say 0 temperature, I have no thermal component that I can detect. We raise our hands in defeat.
Okay.
Yes. Good
Yes.
question.
Okay.
Good question.
Thank you.
Thank you. Do we have any more questions? Okay, so let's thank our speaker again for the talk. And now we have a 12 minutes break, then we will continue with the postdoc talks. Thank you.
Very different than the 30-second rapid fire test. Voice is shattered. Very interesting. How often do you get So we only went public in December. So we know enough. All the papers are in the works. So nobody's published it. Yeah, okay. But that should be interesting. We're really looking forward to seeing how the especially underrepresented institutions like our own school that built a machine, build a bespoke thing, dark matter or whatever. But a lot of people don't have access to this. So we're seeing them engage much more strongly necessarily. But we can do real experiments with no equipment, no budget. How many users do you get? We've got about 1,000 users registered at the moment. We're online every other week at the moment with the hardware, so that we can keep the thing alive. That will probably increase, but usually we have between somewhere 500,000 jobs queued up immediately, and then process those usually in the first day or two. The power requirement high as well. It's not too bad. It's mostly labor hours. Like it's like minutes. The moment is one. Just one. There's a single production machine, which is another reason we have to hop on and offline, is that we want to do upgrades. We have to bring it down, do the upgrade, make sure everything works, back up. And then you were still able to keep every other week. We have been. Okay. We did take an extra week a couple weeks ago to do a more serious control system, which was using it for like 15 seconds per shot. So it was worth it, but it was. Are you a PhD student or something?
75 minutes and 7 of them. So they have
Crunch time.
about 8 to 9.
8
Need to change.
I see. Okay, 8 to 9, and then.
Successful first.
So I think I will just.
Or we should
this
My
mic
last
here
name is
and
actually-
get the other one.
My fault.
No, it's okay. Purdue
sorry.
likes
I'm sorry.
my second last name. I saw your email also, so
Okay.
I approve.
Okay. But you can go first still.
Yeah, that's okay.
Algeria.
Yeah, so we have
Summer school, or do you go to Purdue? Of the atoms themselves, I think the simulator is probably the best place to explore that. Because it gives you phase information, and you can see how violent you're being loud when you create a barrier and things like that. But in the experiment, I think if you were just blindly searching for something, it would be murder.
This is the media. We'll use this microphone. Yeah.
Okay, you can have that mic as well.
Yeah.
Okay,
So
and then
yours
there's
is the
all right,
one
perfect.
for over there. Then and then what we can do this crazy stuff. That's all right. Make sure this works. So when you
This
when you
requires
do
some
that
sort of
with
two-dimensional geometry
with
where
the
you
controls,
go around
to
the
reactivate this, you got to click
enclosed
on
area.
a lot of people. It's not obvious. Because start clicking on it. Why isn't this working? It's weird. It deactivates the connection between that and the screen. Sorry if you're.
It's there.
I didn't know that.
We're struggling up here to discuss what it's capable of.
Yeah. Or like how it might in transitions.
Yeah, we can get
help, that'd be great.
Yeah, so.
You needed to run across the whole room many times.
Well, I was lucky, my other guy was doing that, the guy who was running sound was doing that before.
Okay.
I gotta run the camp.
Yeah, that's also good.
No, I just wanted to. Yes, yes. We got most of it. It was touch and go. Yeah. It was like Sunday night, and the guys, no, guys were like still responding to tickets. I'm like, wow, we're really gonna see this across the line.
Yeah, so I mean, during
I do.
So, yeah, so you're going to make your part. So he's the person who kind of runs the, he's very supportive of, the idea of so it's probably.
Like the response to it was great, but the documentation was zero.
Yeah.
It's like, what should my invoke script look like? I have no idea.
I kind of, it's bad, but that was really, again, it was really because I had an undergrad doing some similar stuff, trying to get some other tools, and he was having a lot of trouble. And so the fact that a bunch of professionals,
I'm still kind of.
It still counts, but
It was mostly good, like a document card, and then, oh, it doesn't work, I have to create a ticket, I get an email that doesn't answer the question, and then I have to like figure out how to get, it was just really like, dragnet. And we also have some specifics, about like, we actually care about the security of our user tokens, and that means, using tools that aren't supported on Nano, so we figure out a way around that. Basically, what we're gonna do is build a button into the website that just grabs the token. Which I think will be at least functional.
Okay.
We basically, all our authentication requires new browser. And NanoHub doesn't support that.
Right.
So that's the way it is for us, and that's kind of what we decided on. So there's a bit of push and pull, but the support really came through, Daniel in particular.
Yeah.
He was like, not worried about tickets, he was just like, he figured out the way to get, once you had a token in your hand, then you could register that. And I didn't even know how to do that, so he figured that out. Then there were a bunch of firewall permission problems. It was like, you can't create an HTTP request from, like, why not? How can I engage the cloud service if I can't make HTTP? So, yeah, it's dynamic, but I think we got it working enough where it was still easier than making an install Python, Python version, and then
Okay. But you guys working on Sunday evening, and I guess it was a stressful weekend.
Yeah. I mean, I was like going through all the steps. Like, I think it was Sunday night when I was finally like, okay, it works. Thank God. Like my talk can go forward. I don't have to back up.
No, I really appreciate all the effort from you guys and everything. As it kind of continues to develop, we've got like the group kind of put together so we can, once the tool's like public, I guess it's published. So if you can, we can try and find it somehow, or you can.
Is Quantum Hub going to be a separate domain?
It's just like a group within NanoHub. So eventually we'll probably do like a separate domain that'll just link back to NanoHub for like launching.
Okay, so things will be mostly shortcuts.
Right, yeah, it'll be more like within Quantum Hub will be like a flashy, more modern web page rather than being NanoHub. But right now it's just going to be under. But we got, it linking to your guys' company website and that kind of thing, but we can add a link to the tool on NanoHub.
Yeah, and we'll probably keep on community equivalents relatively soon. As we're doing with like direct research partners on that, but we have one some of them all for. And it'll probably always lag a little bit behind like our automated deployment cycle, which is but I think we'd love to see the platform just stay, give an access route to people that don't ever want to call. Sure, we run into those people. They're like, I don't install it. Well, how do you expect to use it?
Yeah. So I mean, you can help with that, and then like, one of the other things I don't know if you guys do like inference or anything like that, but like one of the things that we can also do is kind of rapture GUI that allows it to be like, they don't even have to code and like do that.
I played around with a couple of the tools, but I didn't know anything about Rapture.
Yeah, that's Rapture, so like the act, yeah, I wouldn't have done that for the first class. No, definitely not, but that's where we have some other students in my group trying to go through that, you know, fight that.
Okay, so you've got the undergraduate army, you just
That's
throwing
right,
them at.
not had 9 this semester, yeah, so it was just kind of lobbing them at different things.
Oh, well, hopefully something sticks.
Well, yeah,
Well, thanks for the support, because I think your help really got us moving, that it's like, hey, these guys can help.
Got us connected with Danny, the person who can actually.
Daniel was
Before we start,
so this should work. Does this work?
okay.
You can use this. And so the mic, we won't transfer the mic because it's like too many talks.
Yeah,
So if
yeah,
you
yeah.
don't mind using a handheld one,
Sure,
that would be great. Okay. I hope everyone had some time to enjoy coffee and grab some cookies. So we will continue with the post-hoc lightning talks. And
Thank you.
yep. So our first speaker is Andres Alca from Purdue University.
Okay. Thank you. Thank you for the. Can you hear me fine all the way on the back? Okay. Thanks. What I'm going to present is a little bit of the work that led into my postdoc. I graduated from Purdue actually, so it's going to be the kind of the last part of my PhD and continuing to a little bit of I plan to work on, and it's going to be a little different from the talks because it's a little more in the material say processing in order to get some effects. In this case, I'll be talking about the 2D materials, which I'm pretty sure a lot of people know about and probably have worked with. And let's say it's how we find this novel way of introducing strain through what I will call, I'll use a technical name, this buckling delimation, but it's actually kind of wrinkling. And it turned out into some quite interesting effects in like 2D magnets, which we could use for as quantum matter. So obviously, and probably everybody has know about this, but I have to mention it. In the lab, we work with these van der Waals materials or 2D materials that usually we start with a very nice single crystal, and we can get flakes using simple mechanical excavation, which will inherit the nice crystallinity from the bulk crystal. And usually what we do is like, just exfoliate them and we can thin them out to very atomically thin layers. And what's interesting in them is like, people found like you can get like a single layer of carbon atom, a honeycomb lattice, and get graphene, or you can see this the semiconductor, the transitional metal dichalcogenides that have very nice optical properties. Or there's a myriad of different materials, including like, for example, 2D magnets recently, which was kind of the focus of my PhD, which actually led into what I'm going to talk. So I'll be talking actually in a reverse way, how we found some effect and we studied, found that the actual driving thing is this buckling delamination. So one of the things that they have to mention is that strain is a very nice tuning knob that we can use to modify the properties of these materials. And there have been like you can use them to kind of like break the symmetry and introduce some kind of piezoelectric effect in TMDs, or maybe even lead it to phase transitions. And a lot of the work has been to studying, like, for example, hardening or softening the vibrational modes, the phonons into the materials. And there's many ways you can do this in these van der Waals systems, and it's like just poking them using AFM tips, which has led into like realizing that, for example, MOS2 or graphene can withstand quite high strains, up to 10%, or maybe just bend them using flexible materials, or stretching them with piezo's. But this tends to be kind of like not so simple to implement, and it turns out that we found kind of a way to introduce a strain, although a bit chaotic, that is more compatible for, let's say, an optical system that has a cold finger, which was the system I was working with. There's many other ways as well to introduce strain. For example, just put in on a pattern substrate with nanopillars, and then we can see, for example, if you put MOS2 on nanopillars, you can kind of iPhone excitons, and some of them might show some nice optical properties like this single photon emission. So our kind of approach is rather non-conventional, and it might not look as pretty, but what we find is like when we kind of we were studying this heterostructure engineering by depositing thin films on these 2D materials, and we found that if we apply the stressor film, we sputter it or we grow something on top, these things start to delaminate. So this is what we call the buckling delamination. And what's interesting is that this can be applied to many different 2D materials. This applies to, for example, hexagonal boron nitride, graphite, few layer graphite, or TMDs, or more importantly, more interestingly, antiferromagnets or 2D magnets, which was kind of the focus of my research. So not only that, we found out that what we really care about is how much stress is on the film that leads to this delamination, which is actually a failure in coating technology. But there's some opportunity because this, and I'll show later, this introduces strain into the 2D material, kind of chaotic strain that we could use to study in a single sample, like a non-uniform strain profile. So the usual way we kind of study this strain is by relating it to the vibrational properties, and that's by doing just Raman. And we found, for example, samples that show like a very nice wrinkle in the middle, and when we can do just this Raman mappings, and we can observe that close to the wrinkles, we have like a Raman peak shift, which is a hallmark signature of a tensile strain. So while we show this in HBM, which is a stable sample, and we can also show that this occurs for like many thicknesses, although we kind of lose it at higher thicknesses, even though they also show this very nice hexagonal wrinkling, and that has to do with like our Raman probe being the combination of the bulk and just the surface, which is what we expect to be the thing that is getting wrinkled. And our signal just gets dominated by the bulk. But what we care usually is the very thin ones, in which we observe like quite a large Raman peak shift, indicating like a large strain transfer into the system. And obviously, just vibrational properties, well, it's interesting by itself, but there's some application that actually was the first thing we observed, and this led into me trying to generalize it to all different 2D materials and maybe using different stressors, and that was like applying them to 2D magnets. And what we observed, surprising at the beginning, was that when we use this type of stressor film leading into this delamination, we can increase the Curie temperature. And the way we measure this is all optical way of measuring magnetism. I was using magneto-optics curve effect, which is a very local probe and gives some very nice micrometer resolution in precision. So we can do like experiments like before, and then applying this stressor or this sputter in this nickel oxide in this case. And we see a clear difference in first in the Curie temperature. Our Moog loops, which is the signature of a ferromagnetism, disappear at higher temperatures. And also there is like a difference in the shape of the loops, then becoming more square, indicating like a higher coercive field. Not only that, this, of course, we tried in a sister compound. In this case, we were studying this chromium germanium telluride. The sister compound, chromium silicon telluride, also shows similar effect. The usual EC is around 32, but now this became around 65, almost doubling the Curie temperature. And of course, we believe that this is mainly from a strain. And this was what kickstarted our research. And we were trying to figure out what was the source of this enhancement. And by doing many experiments, which one of them was by just looking at the position dependent, we found that the result was correlated to the appearance of these wrinkles. And what's more, if we aggregate data from many of these position dependent samples, we find that the TC correlates with the Raman shift, which is an indication that the tensile strain in this case increases our Curie temperature. And with that, it's like, well, I'll show you kind of the end result first, which was like using this non-conventional way to apply strains to pretty much the big family of 2D material. And while it's a bit chaotic, applies a non-uniform strain, it could be a nice opportunity to go ahead and try samples that are easier to prepare in comparison to other ways to apply strain.
I think we have time for maybe 1 or 2 questions. We have. So I have a quick question. What do you think is the cause of the enhancement in the ferroelectricity with the wrinkle? Do you have any?
For the ferromagnet, it's
Ferromagnet.
yeah, it's mainly the formation of the crystal structure. So CGT is there's DFT calculations that we've done in which we apply this biaxial strain, and we see an increase in a change in the coupling in the ferromagnetic couplings, and that is what leads into the enhancement of the TC.
All right, thank you very much. Let's start. Thank the speaker again. And we continue with our next speaker, Amandeep Bhatia.
Thank you for being here. Thank you. Thank you for being here. My name is Amandeep Singh Bhatia, computer science major, working in a chemical engineering department as a postdoc under Professor David's lab. Today I will presenting our recent work, quantum federated learning for a healthcare domain, the shift from development to development, deployment, and from adults to data. So we entered the era of data-driven medicine, which is great. We have now a lot more potential and can explore new directions, but still we rely on large and diverse data sets. Currently, a lot of research is readily driven by data lakes. So we cannot create a data set and share it publicly, especially in the healthcare domain, because it consists of highly sensitive information about patients and regulated regulations. Due to the subjective to regulations, so it cannot be easily shared. So we want to avoid all the bias in terms of demographics and imbalances that impact the performance of the model. So what's the solution? Federated learning is one of the solution. Like it is emerged as a promising solution for the healthcare domain, like which allows different hospitals to train their machine learning model in a decentralized manner or collaboratively without sharing any private data. So the idea is like there are a number of hospitals are there, and so each hospital will train the machine learning model on their own repository, and they will share the updated weights, model weights with the aggregated model. Then in this way, the communication will keep on going between the hospitals and the aggregated model. So each client is having the complete control over the data. They can revoke it anytime during the machine learning progress. So this is the idea, like we are not sharing any data. The clients will only share the model updates with the global server. So now I will talk about some of that, like how we are constructing the tensor network in the quantum machine learning. Like we know about the row vector, column vector, and image in the form of the matrix. We are dealing with the tensors, like multi-dimensional data. So a few of the examples are like if you have images, we organize them into 3-dimensional tensors, like x coordinates, y coordinates, and their RGB value. If you have a heterogeneous data, like in a medical domain, like you have 4 components or 4 features, instead of organizing them into a matrix form, you are organizing into a 4-order tensors. These are the few of the examples, like tensors emerge all over place in a machine learning. So we are dealing with how we can convert the tensor networks into a quantum machine learning quantum circuits. So one of the example is in a classical machine learning theory, like a very simple example. There are 3 steps to convert to implement any tensor network in a machine learning theory. Like first is mapping the data into a tensor product features. Suppose you have an input vector x. It consists of several small tensors of 2 or 3 dimension. You just take the tensor product of those features. That is now you are in a high dimensional, exponentially high dimensional space. And you can, any linear classifier can do the classification here. So next step is evaluate the MPS model, like matrix product state model. For the evaluation, we just perform the contraction of those tensors to evaluate the model. Then third step is Then third step is to optimize. Then we just take one leg of the tensor and take the gradient of those tensors, and then we can perform optimization with any gradient descent or any classical optimizer algorithm. So these are the 3 steps to implement any tensor network in a machine learning theory. So next is how we mapping those tensor networks into a quantum circuit. So there are basic 3 tensor networks existing in a classical theory: matrix product state, tree tensor network, and a multiscale entanglement network. So these 2 are highly entangled with each other. Like they usually also call it as a hierarchical tensor network. So this is a one-dimensional tensor network. So during the mapping, we just put the 2-qubit unitaries by following the same fashion among the qubits, and using these 2-qubit gates among the qubits, and we are performing the expectation value at the end. So this is just a mapping of tensor networks to a quantum circuit. So how we are encoding the medical images into the tensor network? We divided the image into several parts. Like we use the patch-based encoding. Instead of giving the whole image into a quantum circuit, we're using the patches and giving into a tensor network. So these are the 2-qubit unitaries we are using as a part of this quantum circuit. Next is how we are implementing this quantum tensor networks in a federated way. Like you have a number of hospitals. Each hospital is having their own repository or patient image-based data, and they will perform the training on their own repository, and then the same federated learning will work. So here we are having a quantum machine learning model. So how the local model is performing on the client side, like client is having the data, hospital is having the patient image data. So we are constructing, like you have like suppose, for example, you have a 32 by 32 image, and we are just traversing the whole image by 2 by 2 matrix and put it into a quantum tensor network. And then we just perform the classification or expectation value on the basis of expectation value, that whether the image belongs to a normal chest X-ray or any pneumonia or lung opacity image. So this is a client-side training, like each hospital will perform this type of quantum machine learning model on their own repository, and then they will share the updates with the global server. For the experiments, we consider the high-dimensional medical images, like RSNA chest X-ray medical images. So then we just distributed these medical images among the number of hospitals, like we consider the 4 hospitals, and we distributed in a non-identical distribution. Like one of the hospital is having a very lesser number of samples as compared to the hospital 1. Then we check the performance of all the 3 tensor networks, and we've seen that the model which are highly entangled or hierarchical tensor networks, they are converging very quickly as compared to the one-dimensional tensor network. In the similar fashion, we consider the 4 different of medical images, like chest X-ray, MRI scans, and CT scans, and distributed among the 4 hospitals in a non-identical fashion, like very worst distribution, like some hospitals may not have enough number of samples also. So in that case, classical machine learning struggles. We want to see that how our quantum machine learning model is more robust for these type of distributions. So the conclusion is more the entanglement, more hierarchical tensor networks, they are showing a smoother convergence and less testing loss as compared to the one-dimensional tensor networks. So, and we check the AUC curve also, which shows that demonstrates the effectiveness of the quantum machine learning model. Like we are getting around more than 95% AUC for those high dimensional medical images in a non-federated fashion. And we are seeing that in a federated learning also, even if the distribution is non-identical, we can get the same accuracy. So next we check the performance of individual client models, like how the clients are performing on their repository. Like this is one of the example of the data set. You can see the client 3, hospital 3 is having a very lesser number of samples. It starts struggling, but still converging. And you will see that this is a red curve of the global model, which is a centralized aggregated model, and it's showing smoother convergence and very fast convergence. So in the same fashion, we consider another data set, and we see the same observe that global model is giving a better convergence and smooth convergence as compared to the local client models. Next, we check the performance with the local differential privacy. Like if the clients are having clients are sending the gradients to the global server. If they put some randomness in the gradients, then how the quantum model will perform. And we've seen that we are comparing here with the classical model also. Like you can see the classical MPS model is showing the fluctuation among the these type of distribution, but the quantum model are showing smoother convergence as compared to the classical model. And in terms of privacy level, we are increasing the noise in the gradients, and we've seen that when we are increasing the noise, the more entanglement like hierarchical tensor networks, the accuracy drops, but not as compared to the as compared to the classical models. So the conclusion is quantum tensor network global model can still get a better performance as compared to the local client models, even with a smaller number of parameters, even in the presence of how the data is distributed among the hospitals, but the global model is still performing better. And we are getting around 98% AUC on high dimensional medical images, even in the federated learning. And at the end, I would like to thank Professor Sabri Kais and Alam, with whom I have presented this, published these two papers. Like this is a hybrid version of the presenting work, in which we have proposed a hybrid model, quantum machine learning model in a federated fashion. Thank you.
Thank you very much.
Yeah.
Do we have any questions from the audience? So what platform did you use to run the quantum algorithms?
We are using the Google Search Simulator.
Okay.
Yeah, and now we are implementing on an IonQ hardware.
Okay.
Yeah.
Okay, great. Thank you very much. So our next speaker is Vahagan Mahitarian from Purdue University.
Hi, everyone. Before Mustafa sets everything up. So yeah, my name is Vahagin. Surname is Mahitarian. I know it's a bit hard to pronounce it, but
I did a good job.
I can't do much with that. So I'm going to present our current work in the group. It's not a completed work yet, but it's a short presentation. So I thought I could share with our vision and what we're planning to do. And yeah, and it's a project devoted to study strong light matter interaction by coupling 2D van der Waals materials with the electric cavities that are topologically optimized to achieve certain performance, meaning to achieve a high confinement with relatively high Q. What is it?
Is this yours? No.
What? It's not mine, yeah. Just open the PDF. Sorry about that.
Which one's your PDF?
Let's see. Yeah, I think that's good enough. Yep, sorry about that. Yeah, so this is a project where several of my group members are involved. Owen is primary PhD student who works on the project, is doing all the fabrication. Omer was helping with simulations, optical simulation. Colton with the optical setup that I'll speak about. And Brendan was helping with the 2D material transfer. And as I said, it's an ongoing project, so I'll be showing, oops, I guess I will have to scroll it. Yeah, so the project has two main objectives. One is to study phonon polartones in polartonic materials, like phonon polartonic materials like HBN, coupled to specifically design cavities that can support extremely high quality mode. But the second part, which I'll be focusing today, is devoted to study the excitonic material coupling to the topologically optimized cavities that can enhance light matter interaction because of extreme confinement of light into very small, sorry about that, domain. And topology optimization normally is done through the inverse design. Well, the optimization cavity is done through inverse design, and there are two types of inverse design approaches. One is the shape optimization, when there should have been animation, but since I converted it to PDF, I'm sorry about that. You deform the object iteratively, and you look at the performance of your device, and based on that, you optimize the whatever performance you want to achieve. In that case, you're not adding any extra holes, any extra domains and dielectric domains in your structure, but you just deform the structure. That's called shape optimization. But you also can add holes in your structure or add new dielectric materials in your structure. And in that case, you are changing the topology of your materials. That's where the name comes, topology optimization. And sorry again, this is very inconvenient. So this is becoming very recent. Topic in photonics. Different people in different groups are trying to use these methods to design different optical devices with different functionalities, from beam splitters to optimizing the gaps in the 3D photonic crystals. Or our group was focused on trying to optimize couplers of single photon emitters into waveguide mode, and demonstrate high performance couplers. So I decided to use the expert in the group to study light matter interaction and see if we can use topology optimization for achieving strong light matter interaction. And you would ask why would you go to this topology optimization and such a hard process of designing cavities if people were already doing strong coupling experiments with 2D materials coupled to this simple DBR structures. And the reason is that in the DBR structures, you are not breaking translational invariance, meaning that you are not localizing your electromagnetic field into a finite domain. Your mode, electromagnetic mode, in principle lives across the whole sample, and that limits your applicability because you know that in order to achieve strong coupling, you want also the mode volume of your electromagnetic field to be shrink down. And people were in this community where people were using DBRs, they were also proposing this kind of modified concave type of DBRs where you would curve one of the mirrors in your DBR structure that would act as a lens that would focus your mode into much smaller spatial domains. But it's hard experimentally. You can imagine it's hard to make this kind of structures. And even if it's not hard, the mode volumes are still significantly large. It's the radius of curvature here is 10 microns. So your mode lives in a couple of micron region, which is still not enough if you want to achieve very strong interaction. Other strategies people were using were coupling the 2D materials to more confined modes like photonic crystal cavities. And in this case, they were showing very interesting physics appearing, like lowering the threshold of lasing in the first paper, or achieving, if you pattern the material itself, like in this case, in this perovskite, you can use the pattern perovskite to achieve the condensation physics at room temperature. So by leveraging the high quality factors and the cavity effect that you can produce by patterning the structures. So our motivation came from this paper from 2022. Were by a group of Ole Zygmunt and his collaborators, where they proposed that by using topology optimization, you can in principle localize the electromagnetic field to extremely sub-wavelength regions. For the ref, you can see on the picture, SEM picture, on the cut picture, the localization region is 8 nanometer for a wavelength of electromagnetic wave being telecom wave. And this extreme localization is important as Purcell factor, for example, depends on the ratio of the wavelength cube to the mode volume. And by shrinking the mode volume, you can significantly increase the interaction strength, Purcell factor. In addition, you are using dielectric materials because people were achieving extremely high localization also with plasmonic materials, but the Q in plasmonic materials is limited. In this kind of approach, you can benefit both from very strong localization and on top of what you may have high Q structures. Essentially, you're optimizing both parameters that are necessary for strong coupling studies. And we took that approach and we designed, with the help of Omer, some topologically optimized cavities. We chose to work with silicon, but we are working at 730 nanometer where our excitonic material has excitonic resonances. The reason is that we are limited with the materials in our lab, current lab. So we decided to compromise the material quality. Silicon is much lossier in this wavelength range, but we will be able to fabricate it. And second is we still will be doing better compared to plasmonic structures that will be much lossier. Okay, but this what I will be showing. The Purcell factor theoretically calculated is 2,000, 3,000 is not limited by the design. It's just limited by the material choice because we incorporated realistic material losses in the calculation. In addition, topology optimization can allow you to control the state of light. For example, you can generate extremely localized spots, cavity modes that can be having chirality, and chirality can be significantly enhanced. And in principle, that can be a parameter also controlling your interaction with matter. And that's another thing that we would consider in future. So right now we are in the process of optimizing the fabrication process for these cavities. It's again, there's animation showing the whole progress. Unfortunately, I converted it to PDF. But so essentially, it's extremely challenging to do lithography at these scales because these cavities that your unit cells that you're looking at are one wavelength in size, so 700 nanometer or a bit bigger than 700 nanometer. And these features that you have to fabricate are extremely small. It can be down to 10, 20 nanometer. And it's hard to do EBL and get consistent results. So we're spending last couple of months to try to optimize the structure. And this is important because from simulations, we already know by controlling the gap size in this bow tie region that's highlighted in the center, you can achieve much higher confinement if you have better control over the gap size. And that normally is not very easy to achieve in the lithography. So we're in this process of optimizing, looking at what conditions of the EBL we should use to get more symmetric structures, etc. That's a work in progress. In parallel, we are developing the techniques for the measurements. For most of this light matter coupling physics, you would want to know energy momentum dispersion. And this kind of information can be achieved by Fourier imaging. When you look at the Fourier space of your scatter light, that will give you, you do that in energy resolve. So you can get information both on the momentum of your modes, so your excitation and modes, and you can get the wavelength information, energy information. And will reveal some of the hidden physics that you don't normally see when you're integrating the spectrum in moment. Okay, so we did the transfer tests on some of the test samples, and we successfully transferred the flakes on top. We developed a technique that allows us to do large-scale transfer of these 2D materials, and we did some preliminary measurements on the structure, and already from here, although the cavities were suboptimal, it's not yet optimal because we measured the spectra before transfer, and it's not what we simulated yet. But even in that case, we already see enhancement in the photoluminescent spectrum as compared to the flat region. So you can see in this example, we have a flake, this circle with this green light, green curve. It partially falls on the pattern region, partially falls on the flat region, where just flat silicon. And if you look at the line, this red line, say cut the photoluminescence intensity, you can see that in the flat region, for the same thickness, you see almost no photoluminescence. But if you go to the flake region where the flake falls on the pattern region, you can start seeing these hotspots that are because of these localized modes that you have in the metasurface cavity. And we already see the enhancement, but a lot more needs to be done because the reason for this, it can be several. One is electromagnetic, as I discussed, but there's also strain effect, as Andres spoke about. Your flake on the pattern structure will experience some strain, and strain can be also contributing, enhancing the fluorescence. So we have to double check all this physics that participate in the emission process. But yeah, we already have the initial clues that we might expect some interesting physics coming with this coupling. So.
Thank you very much, Vahagn, for the great talk. Do we have any questions? So just a quick question. You have very strong localized chiral field, and which should be good for biological sensing applications as well. Do you have any plans for that, or any chemical sensing?
Not for now, and also the cavities that you see now coupled to the flakes are just regular cavities without chirality. But we plan to use chiral cavities to couple to chiral physics because some of the excitonic physics is valley dependent in this material, so you can excite one valley better than the other.
Thank you. Let's thank Vahagn again.
Hello, everyone. Good afternoon. First of all, I would like to thank you, everyone, for providing this opportunity to speak about our current ongoing project. So I will start with my introduction. My name is Mandeep Karsaki. I'm working as a postdoctoral in Professor Sevai's lab. So for this event, I will talk about my current research ongoing projects, which is drug discovery, quantum AI multi-omic with biomarker discovery, and quantum fidelity learning for medical image analysis. So for this event, I would like to explain about that we are exploring the quantum algorithm machine learning for scientific proving on the drug discovery process, so that we are exploring with a different application with industry and academia point of view. So I will explain about the drug discovery process. So what is drug discovery? So drug discovery, it has a great potential in the industries from the number of spanning of years, where it reached up to 1.5 trillion by 2023, and still it's expanding in drug discovery. So many of the researchers, they are spending their number of years to identifying a specific molecules to create a medicine for a specific treatment and the disease. For this, I will take an example that is that the analogy of hit key and the lock. For example, let's say your body cell are like a room, and we are finding the exact drug so that we can find the target key to best fit. If it best fit for the exactly molecules, which means it has some correct reaction, and or if it doesn't, it correct reaction, how we may find the molecules. For this drug discovery, as I explained, that it's spanning the number of years for the first stage, which is the discovery, where we are trying to find the ADME toxicity properties. So I will explain from here this image that we can see the drug discovery process will taking the target identification. We are finding the specific drug and then creating some optimization for the special efficiency of the patient. For example, let's say in this process, we have to find the phase for preclinical process where the first process, the drug molecules will applicable on the animals, and after that they apply those molecules over the healthy people and the diseased patients. So in this case, we have find the some of the challenges which has carrying with the new drug discovery is it very time consuming and complicated, and for the limited access of failures as well as safety concerns and for the complex data analysis. So in this case, we have find that one of the very beautiful ADME toxicity property that we can predict by different molecules by using this TDC website. We have acquired this data set from this website based on simple molecules. So our agenda of this work is we have taken this data set from TDC over ADME and toxicity. So what is ADME and toxicity? ADME, it will help us to identify that how drug molecules are behavior, so that if drug is absorbed in our body, how it eliminated from the body, and the toxicity will tell you that according to the drug that is some side effects. So this is a beautiful combination of ADME and toxicity. So now for this quantum machine learning algorithm, we have, first of all, we apply the support vector classifier, which is the classical machine learning algorithm, specially designed for this type of problem, which is classification and the regression problem. So what is a support vector classifier? Let's say example, X is representing as a students. So students are appearing their exam and they got some GPA. So here blue points are representing as a positive GPA and green represent as a negative GPA, which is we are separating the high GPA and low GPA students by creating a decision support layer, which is we can say that separating the boundary between two type of data points. So now next, because this support vector classifier is not only applicable for linear problems, it works for non-linear problems also, where we have designed this support vector classifier where this kernel function, when we see the data from the center point, it actually create a hyperline to make a separate, and for the quantum classifier, it similarly work on the quantum kernel function. So we have just used the classical data that transform over the quantum classifier with the kernel, and we use this SVC, that is a support vector classifier, for the prediction purpose. So I will explain with the few steps here. This is the data set which I have already explained, that ADME and toxicity. So the problem was each molecule has a long sequence of length. Now the thing is how we can proceed for quantum algorithm. So for that we have designed one of the technique we use, that can we reduce the each sequence with number of steps with dimensions. So we use the PCA that reduce the each molecule sequence of string into 2 dimension, 4 dimension, 6 dimension, or 16 up to any time. So after that, reducing each sequencing in a PCA, we apply the quantum classifier not only over classical simulation, but we have checked their performance over quantum IBM. So I will explain the, and also we got the chance to present our work as a front cover in Journal of Chemical Information and Modeling, which I have already designed and it's published. So the result, yes, so in the results, we have checked our performance of model with this quantum state vector, quantum simulator, without noise and with noise. We have applied the depolarization noise channel with quantum hardware. So here we can see this pink line is representing as the benchmarking with the full sequence of data with classical support vector classifier performance, which achieve a 95% accuracy. So we are trying to see, can we benchmark or can we get close to reach up to this accuracy? So with our experiments, we have observed that with the state vector of quantum, we have achieved by planning making this dimension of 2, 4, 8, and 16, we are achieving, as we increasing the size of data, we are getting the accuracy. So processing this data and this whole experimenter, we have used 4 data set by dividing the data set into k-fold cross-validation, and we can expand this work for drug target interaction prediction for the future. So now we'll talk about my second project, which is related to the multi-omic cancer detection, where we are detecting the different type of disease-based healthy people and non-healthy people, which is a cancer patient and non-cancer patient. Can we do this? Yes. With only single multi-omic, it's only tells you some of the functionality, but with the multi-omic integration, we are integrating genetic data, gene expression, RNA, mRNA, and DNA for the long sequence, and also to identify the associated biomarker that will tell you that what kind of disease it has. For example, and so it has some challenges because of the high dimensional space of data, which has a number of genes with a low number of samples. So we have designed some of the approaches, which I'm going to explain in further slides. So, sorry. So this is. So we have designed this proposal where we are acquiring the data from the NIH website, which is the TCGA and GDC, and we are processing the data with feature processing, with feature engineering, where we are trying to make a significant and non-significant data, and then we are applying the feature selection process, and then applying the quantum algorithm for the specific primary tumor versus a subtype. And these are the mostly results of getting some of the attribute of function, and these are the visualization where we can see the different type of diseases, how it actually represent. This is the framework which we have seen our results by applying the feature selection method, which is the random forest, for reducing the data of long sequence, which is the million of DNA sequences. We reduce that within the 64 features, and then by integrating those multi-omics data with subsection, we are just distinguish between tumor and normal patient by applying the amplitude encoding and some classical layer. Now I'm adding about the dense layer of last layer, which is purposely used to get the biomarkers. So here is the data, and these are the results which we have found with this 2 type of dimension, which we have shown with the 16 features as well as of over 64 features. And we have found some of the very good biomarker, which is the mix of multi-omic. The first one initially represent the RNA, mRNA data set. Then we got some of the biomarker from the DNA, and the third one, we got some of the biomarker from the RNA, which represents some associated survival people that can act as a distinguish between that. We can actually say that we can now classify with most correlated features. And this is for the fair comparison, we have compared our training data set of samples and with the testing data samples. Here you can see that how much it's a difference is between tumor patient and the normal patient. It is all about the expression that associate with the samples. And also we have designed this experiment without any applying feature selection method, where we have applied by using only significant and non-significant And the third project, which we are trying to see the multi-model integration with the clustering of the multi-omic data with clinical features as well as the medical image analysis. So I would like to thank you, my Professor Sebre Kais and Dr. Humaira Gohar, for their keep supporting me and guidance on my project. Thank you so much.
Thank you very much, Mandeep. I think we are a little bit short on time, so Alex, we can continue.
Hello, everyone. My name is Alex Enichev. I'm a postdoc here at Purdue University, and I work in the group of professors Alexander Baltasova and Vladimir Shalaev. And if you attended the morning lecture by Professor Shalaev, this is going to be an excellent recap of the topic. And today I want to present an overview of our effort in our group on advancing quantum photonic materials with engineered single photon emitters. So the advancement of quantum technologies, which include quantum computing, quantum sensing, and quantum communication, depends on various building blocks or quantum resources, which include, and you will hear about them, I believe, during the school, ions, photons, atoms, superconducting circuits, and topological qubits. And I will specifically focus in my talk on photon-based platforms, because it's not clear right now which platform is going to be the leading platform in computing, communication, or sensing, but it's clear that in near term, photons appear to be most well-positioned. And the reason is, first of all, photon-based platforms is one of the only two platforms that are able to claim quantum computational advantage, meaning that quantum computer was able to perform certain operations and outperform classical computer. So also photon-based platform can also use for scalability and rapid growth existing photonic technologies such as optical fiber communication. And also photons are fast, exhibit low decoherence, and can preserve coherence at room temperature, which simplifies certain infrastructure, making photons are excellent for quantum communication and quantum internet. And also photons allow to use many degrees of freedom for encoding the quantum information. So the challenge with quantum photonic approach that it's important to move from the bulk free space optics, which for example was used for demonstration of quantum computational advantage with photons, to more compact and on-chip solutions, which would allow scalable and reconfigurable generation, manipulation, and detection of quantum states of light. And this transition requires the realization of different optical elements on chip, and the challenge of the full integrated system is unique material requirements to realize of different elements. So I will not speak about all of these elements, but I will start with the point of departure of any quantum photonic chip is the source of single photons. And there are different sources. I will not speak about nonlinear sources, probabilistic sources, but I will focus more on quantum emitters in solids, which are promising to be more deterministic sources and on-demand sources of indistinguishable photons. And typically such quantum emitters in solids are represented by either semiconductor quantum dots or defect in wide bandgap materials. Even though there is a huge progress separately on integrated photonics and development of quantum emitters in solids, combining these two techniques is still a challenge and requires significant effort, which also leads to the challenges of unique material requirements. And talking about materials, it appears that silicon nitride is most promising material platform to realize quantum photonic integrated circuits. And the reason is that silicon nitride can provide ultra-low loss waveguides. It's a wide transparency window, so we can work with different wavelengths from visible to telecom. It's high refractive index, good mode confinement. Silicon nitride itself has nonlinear properties, so they can be used for quantum frequency conversion, and most important, material CMOS compatible and foundry friendly, which makes it scalable. So that's why silicon nitride is the material of choice for realization of state-of-the-art quantum photonic processors by industry leaders such as QX Quantum and Xanadu. And in the heart of these quantum photonic processors are actually low-loss silicon nitride waveguides. What has been missing so far in these material platforms is the existence of intrinsic sources of single photons. So that's why the silicon nitride was combined either with probabilistic sources or using heterogeneous approach. And that's where our group makes a contribution by first discovering intrinsic quantum emitters in silicon nitride and developing methods for their creation. And in my talk, I will go through some of the processes, how we create these emitters and what are their properties. So it starts with the silicon nitride material, and it's important that the host material doesn't emit background photons. So that's why it was important to move from the stoichiometric silicon nitride, which typically exhibits strong fluorescence in the visible, to low after fluorescing nitrogen-rich silicon nitride. The second important part was to form the silicon nitride to silicon dioxide interface. And by doing this, for example, by CVD growth, in our case, it was high density plasma chemical vapor deposition, we prepared the material stack, and high temperature annealing of this material stack leads to formation of isolated bright spots, which we could then observe in the photoluminescence intensity map. As you can see here, the background is low, so the host material doesn't emit much, but there are isolated bright spots that were then confirmed to be single photon sources. So what we know about these emitters, so from the photoluminescence spectral point of view, we know that at room temperature, these emitters typically exhibit broad emission lines, but when we cool down to cryogenic temperatures, we see the rise of the sharp emission lines and quite complicated spectrum. But what's important, we were able to identify zero phonon lines, the fundamental transition from the excited to the ground state. And by studying the position of ZPL in collaboration with the theory group in Technical University of Denmark, we tried to understand the possible structure of this defect. And since we know that they are formed on the interface between silicon nitride and silicon dioxide, and plus supported by the simulation showing that the defect, which includes the substitution with oxygen atom, leads to from the simulation point of view, the transition at 536 nanometers, which is very close to what we observe in our experiment. Though it's ongoing work, we are trying to put more effort to understand better the structure, especially to also be able to describe all other sharp lines appearing in the photoluminescence spectra at cryogenic temperatures. So, but most importantly, what we learned at room temperature, so these emitters are perfect single photon sources. So typically it's characterized by the second order autocorrelation function, and we were able to identify emitters which emit one photon at a time with probability of 92%. If you take one of the best emitters, but also on average, they show very good numbers. They provide linear polarized emission, and most important, they're bright. So we typically can see 3 million counts per second close to the state of the art, what is typically for quantum meters and solids. If we play some additional tricks to improve the collection efficiency, for example, using solid immersion lens, we can increase even further the brightness of these emitters, and we were able to demonstrate up to 12 million counts per second while still having excellent single photon source. This room temperature, and this is important, that it's all the room temperature properties, and these room temperature properties make these emitters promising and material sources of single photons for some applications which do not require indistinguishability. For example, certain protocols for quantum key distribution where we can use a train of photons and encode information in polarization. It was previously demonstrated other quantum emitters in solids like in V centers, scalar centers in HBN and organic molecules. But what we believe is silicon nitride, we hit most of the requirements for this application: high brightness, single photon purity 90%, stability and linear polarization and operation at room temperature. Though for the brightness, there is room for improvement because gigahertz would be much more useful, and that can be done not only by improving the collection efficiency, but using also photonic and plasmonic cavities to enhance spontaneous emission rate. So this is for room temperature, yes, but what makes us different, that's most important, that silicon nitride will allow for on-chip integration for potentially more scalable and compact devices. And here, just a little bit overview of the current effort, what else we are doing. We were able, since one of the advantage of having this emitter silicon nitride is integrate with photonic structures, and we were able to integrate these emitters with planar waveguides. The current effort led by our grad student, Sam Piana, which is already like a postdoc, is to do more deterministic site-controlled fabrication of these emitters to integrate with more complex structures like topology optimized couplers. You heard about them from the Vahagan talk. We also work on efficient high-speed generation using photonic and plasmonic cavities. And third is for other application in quantum photonics, it's important to generate indistinguishable photons. We start first exploring this at cryogenic temperatures, but hopefully the plasmonic cavities would also allow us to go slightly higher temperatures above the liquid, at least liquid helium temperatures, so we'll simplify the infrastructure. Well, with this, I would like to thank you for your attention, and our group and all the grad students and postdocs involved in this project. And I'm happy to answer your questions. I will stop on this slide. Thank you.
Thank you, Alex. Maybe we have time for one quick question. So I think one of the biggest issues is the line width. And do you have any ideas on how to improve that?
Yes, so when we talk about line widths, of course, the spectrum is broad at room temperature, and it's typical for most of the quantum meters and solids due to the interaction with phonons. What we are more interested in the width of the zero phonon line, which we observe at cryogenic temperatures. So far we were able to see that one of the sources of broadening is spectral diffusion, so it should be improved because homogeneous broadening due to the interaction with phonons can be suppressed by low temperatures. So now I think the effort to suppress spectral diffusion and be able to probe the widths with photon excitation spectroscopy, because the measurements that were done before actually the resolution of the standard grating type of spectrometers were limited, and we were able actually to see the spectrometer resolution limited line widths. So this is an ongoing effort, and today looks very promising to generate indistinguishable photons, at least at cryogenic temperatures.
All right, great. Thank you very much, Alex. So next we have Misha Shalayev from Duke University.
Good afternoon, everyone. Thanks for a chance to present here. My name is Misha Shalayev. I'm from Duke University, and I work with Professor Chris Monroe. And I'm working on scaling up ion trap-based quantum computers with photonic interconnects. So in our group, we are working with trapped ion based quantum computers. And here you can see on the picture around 80 ions that are hovering around nanofabricated chip. And it's held since ions are charged. So you can trap them with electric field, and then you can control them with laser light. So you can control internal quantum states of the ions. And why ions are so good is because this platform actually has the longest coherence time with more than hours, and also the highest fidelity of single photon and two photon qubit gate, and also the best state preparation and measurement out of all the platforms for the quantum computing. So I also would like to mention that, of course, these experiments are only for single or two ions. And there are several ways how to scale up this approach. So one of the way is when you break your ion chain to a smaller chains, and then you can shuttle your ions between the different sites where you can do your gates, ion storage, and so on. So this way you can scale up to around maybe 100 or 1,000 of ions per one chip. But then there is another approach, which is, well, it's not necessarily competing with the other one, but rather complemented, where you can use a photonic interconnect, and you can entangle the ions in a different quantum processing units together. And this way, actually, these ions act like a local ones. And this is one of the ways how you can scale up, let's say, at a different level. So, and in our group, we're focusing on this approach with the photonic interconnects. And first of all, I wanted to motivate and wanted to show you what is the relation between the local operations with the remote operations. First of all, we can see there are two metrics, which are the rate of the entanglement generation and also fidelity. So if we compare the local entangling gates and the remote ones, there are 2 orders of magnitudes difference in the rate that's been achieved, and also the fidelity of the local gates is also higher. So for successfully scaling the quantum computing, it is required to have actually both the rate and the fidelity being high. So, and this is the plot of the state of the art right now for the photonic interconnects. And as I said, we want to be up here to the right corner where the entanglement rate is high, but at the same time, the fidelity is also high. So, and these 2 points right here is actually with the trapped ions. And later on, I will show you where our latest result land on this plot. So first of all, I wanted to show how we actually can entangle 2 ions that reside in different vacuum chambers. So on the first step, we shall create single photons, each of which is entangled with the internal quantum state of the ion. Here is up and down state, and we entangle it with the horizontal and vertical polarizations. So how we do it, we first prepare our ion in this state, and then we use a pulsed excitation from which it can spontaneously emit a single photon, which will be either H or V photon that is entangled with one of these internal states. So then what we can do, once we generate 2 single photons, then we can interfere them on the beam splitter. And what beam splitter does, it removes wedge path information. So then we can follow up by detection of 2 photons, each of which is, one of them is H and another of them is V. And because we remove wedge path information, we don't know from which quantum memory this photon came from. This way we create a Bell state, one of the Bell state, depending on which of these 4 detectors have clicked. So, and I wanted you to pay attention here to this is actually quite crucial part of our setup, is the collecting the optics with which we collect our single photons. For example, in this experiment, which has highest rate, they use high numerical aperture optics, which collects around 10% of the emission. So in our new experiment, we designed the quite unique chamber that have two lenses that are residing in vacuum, and each of them collect 20% of emission. And I would like to mention that the entanglement rate actually goes as a square of the collection efficiency. And well, here I would like to summarize our results. So we've been able to, with this largest collection efficiency, which actually was the largest one with the refractive optics of the 4.5%, we were able to achieve the highest entanglement rate of 250 per second, and also having a high fidelity of above 93%. So, okay, since we already spoken about how we improve the rate, next I would like to focus on improving the fidelity of our remote entanglement. And I wanted to mention that for this work that have a highest fidelity, the polarization qubit being used when the photonic qubit is encoded with horizontal and vertical polarization. So, and actually this is a leading error for the fidelity. So what we tried in our lab, we actually used what's called time bin encoding, when the internal state of the atom is entangled with either early or late time bin of a single photon. So you basically have a 50% chance to detect photon in early and late time bin. So this allows you to remove this polarization error. And this is our experiment. In this case, we used two vacuum chambers. And here is the protocol. So first we prepared our ion in a quantum superposition of states, and here's an optical qubit between S and D manifold. Then we did a pulse excitation to promote our ion to this excited state from which it can spontaneously decay back. And this way we generate our first time being. And then we swap these two states and we repeat the same procedure to generate a second time being. And again, we interfering that two single photons on the same beam splitter. The only difference now, we are not detecting H and V polarization, but rather early and late single photons, again, removing the wedge path information. And by doing this, we create, again, maximally entangled Bell states. And well, the other thing that we actually can do with this protocol is we end up with error being in one of our ion states, and we can post-select on that. So this is our preliminary results, and I believe that we demonstrated remote entanglement with time-bin qubits for the first time with trapped ions. And this allowed us to avoid the polarization error. And we observed 96 and 96.6 fidelity as compared to 93.7% with the polarization qubit. So, and this is updated state-of-the-art plot. And this is not the final result. I hope we can improve maybe a little bit on top of what I just showed you now. So with that, I would like to conclude that I have shown you two experiments in our lab. First is where we demonstrated the remote entanglement with polarization qubit and having the largest collecting efficiency with refractive optics, which allowed us to demonstrate a high remote entanglement rate at high fidelities. And also, we have demonstrated for the first time remote entanglement with the time-being photonic qubits, where we were able to avoid the polarization error and demonstrate high fidelity of our entangled state. On that, I would like to thank our team at Duke Quantum Center, and especially my supervisor, Chris Monroe, and we'll be happy to take questions.
Do we have any questions from the audience?
So I have actually two questions. First, are there any ways how to improve collection efficiency, like using not refractive optics? And the second, do you use something as a quantum memory, like a nuclear spin or whatever in your system? Yeah.
Okay, for the first question, you can use actually a cavity for collecting single photons. But then if you use cavity, you also alternate shape of your photon. So your photon may become longer and it may take longer time to collect this photon. So there are some trade-offs between these approaches. And another problem with cavities is since it's a trapped it's an ion that is charged, so you cannot really use dielectric cavities very close to the ion. And usually this cavity tend to become larger, so your photon is really bouncing back a longer time. And then because of that, it also limits your rate. So it's just a more simpler approach just to use a bigger optics. And for your other question, what we use as a quantum state, basically it's an orbital on the ion. This is what we use as a quantum state. So we use actually several. There are actually many levels that you can use. For example, in the second part of my talk, I shown we use some states in D level, and we have 6 of them. And for example, we can use them as a quantum memory, and we can use them for what's called QDITs. When you go beyond 2 states, you can have more than 2 states. You can have 0, 1, 2, 3, 4, 5, and 6. So you can actually have more states than just 0 and 1.
Thank you very much. So we have our final speaker, Dimit Sichov. You can keep that.
Okay. Okay. So my name is Dimit Sichov, and I'm a postdoc in Purdue University in Vlad Shalaev and Alexander Boltasov groups. So today I'm going to talk about our recent experiment, which we are trying to do in our lab. So as already been mentioned by Alex and others and previous speakers, so quantum photonics now is a very big field with big potential implication for quantum computing, sensing, communication. So, and as was mentioned before, photons are the best for transferring quantum information over long distance, which cannot be achieved with any other platforms. That's why photons are always will be used for communications. At the same time, there are big challenges in terms of scalability, because photons are very lossy, and it's prevented for like building big machines, big scalable machines, and using it for big scaled quantum computers, for example. So one of the aspects are losses, but losses can be compensated in a number of ways. One of the ways is using silicon nitride platform. which like Alex already mentioned. And the second approach, which we are talking about, is controlling the like rate of clock rate of your photonic system. So any optical circuitry, in principle, can be presented in 3 elements, like single photon sources, single photon detectors on another end, and linear interferometer in between to do some procedures with these single photons. So, and high rate of operation is preferable because it allows, first of all, just to work with high speed, like higher rates, clock rates. Second, it allows making your photonic circuitry more dense, because when your photons are long, it means that the circuitry itself should be corresponding to duration of your single photon. For example, 1 nanosecond of time duration of single photon corresponds to several meters in real space. That's why you cannot put too many elements very close to each other. And to other things, you can beat decoherence if you have high enough speed. And the fourth one, that you, in principle, can try to do some sensing, like at much faster scale, which can be useful for investigating all processes in chemistry or biology. So, as for quantum emitters, the best emitters are solid-state emitters. Of course, there are emitters based on spontaneous parametric Dynamic conversion, where you use Chi2 process to split your photons into pairs and use one photon for one photon of this pair for your further operations. But this process is naturally probabilistic, and second, it requires lots of energy to produce a small amount of photons, which you cannot say about solid-state emitters, because they consume less energy, and potentially they, in principle, deterministic. Even though it's very hard to achieve on practice, you can cool down your system and achieve very high quantum efficiencies. So, and usually emitters, solid-state emitters, people are applying with photonic cavities, which allows first increase the efficiency of emission, and second, it allows to control their duration of your photons out of these photon emitters. So here you see the time scales for different approaches. If you take bare solid-state emitters, usually it's from 1 to 10 nanosecond. Photonic cavities allows you to get a Parcel factor of about 100. So, and like from 10 to 100, and you can get up to half of a nanosecond. So, and the record high Parcel factor using plasmonic cavities has been demonstrated, like for photons, and photons with duration of 10 to 100 picosecond has been demonstrated. So if you want to go further, other methods should be applied, and one of the ideas which we're currently working on is based on nonlinear optical conversion of these photons. When you take your single photon and overlap this photon with ancillar laser beam in a Chi2 crystal, and this single photon is being converted, is being converted to a single photon on a different frequency. But what is more important, you can control not only frequency, but also a time shape of this photon. So in principle, you can go as low as femtosecond pulses. So of course, it will has much lower efficiency compared to initial single photon emission rate, but this problem potentially can be compensated by multiplexing. So on another end, aside from producing photons with high enough speed, you want to detect photons with high enough speed. And for this idea, which already has been presented today, can be used of all optical modulation. So, so just to slightly update you, it's idea where instead of a single photon detector, a single photon avalanche detector, you are reading out this avalanche not by electronic, but by another probe beam. So, and potentially this beam can be as, yeah, just to recall this idea. So in standard avalanche, single photon avalanche detectors, the beam is produced by single photon, and this avalanche is read out electrically. So, and in this process, one single electron absorbed by single photon creates like up to 1 million of new electrons. And these electrons creates a current which you can read out electrically. But if you do the same with another probe beam, you potentially can make it much faster. So, and here is the idea of how to do it with already in a different structure, when one photon creates avalanche, and this avalanche is being probed by the near-infrared probe beam, and instead of like waiting for some time when avalanche is quenched, we immediately can detect the second avalanche, because since they're in parallel, it can be used for much faster detection. And here are some estimation, like if you align your cavity for a few picosecond lane width, like 1.5 nanometer line width, which inversely proportional, if you calculate it in a time required for reading out this avalanche, it requires a few picosecond. And when you create avalanche, it transits this region of photonic cavity with a drifting speed velocity of 10 in the power of 7 centimeters per second. So, and if you calculate the speed, the time required for these electrons to transit this region, it is about 3 picoseconds. So it's approaching 1 terahertz frequency of subsequent detecting of electrons. Okay, so that's all what I wanted to tell you about. So one idea is about detecting, and one idea about generation of picosecond single photons. Thank you.
Thank you very much, Dimit. Do we have any questions from the audience? Okay, so I have a question. So you are creating a big change in the index with a single photon. So can this design be used for a single photon level nonlinearity for modulating single photons, where your probe is also a single photon beam?
For modulating, say it again.
So do you use a single photon to create the change? Can you also probe it with a single photon and like a single photon level?
Yes, you can probe it with a single photon as well. Yes.
All right. Thank you. So that was the end of our postdoc talks. Let's thank all of our speakers today. And we have our poster session down the hall, I think, room 206. And we have the welcome dinner tonight at 6:30 p.m. at Lafayette Brewing Company. And we all hope to see you all there. Thank you.